Good evening. I'm Atlas Reid, and this is the Nocturnal Astronomer, your guide to the cosmos as you drift towards sleep. In this collection, we'll journey beyond the boundaries of our small blue world to explore the gentle mysteries that fill the universe. We'll visit stellar nurseries where infant stars ignite within clouds of ancient dust and drift alongside rogue planets that wander the void without a sun to call home. We'll trace the invisible threads of the cosmic web that connects all galaxies, listen to the silent songs of gravitational waves rippling through space-time, and stand at the very edge of everything, the boundary where our observable universe dissolves into the unknown. You'll discover how Earth's magnetic shield paints the sky with auroras, how the atoms in your body have been recycled through countless stellar generations, and why time itself flows differently depending on where you are in the cosmos. We'll compress 13.8 billion years of history into a single calendar year to glimpse humanity's brief but luminous moment, explore the Goldilocks zones where distant worlds might harbor life, and follow our own Milky Way as it drifts slowly toward a mysterious gravitational anomaly called the Great Attractor. Each episode is designed to ease your mind, expand your perspective, and remind you that you are made of star stuff, intimately connected to everything you're about to explore. If these cosmic journeys help you find peace under the stars, consider giving this video a thumbs up and subscribing to the Nocturnal Astronomer for more. Let's get started. In the vast expanse between stars, enormous clouds of gas and dust drift through space like celestial cotton candy. These molecular clouds, as astronomers call them, are the fundamental ingredients for star formation. They contain primarily hydrogen, the universe's most abundant element, mixed with traces of helium and heavier elements forged in the hearts of previous stellar generations. These clouds are truly immense. A typical molecular cloud might span 50 to 300 light years across and contain the mass of 10,000 to 10 million suns. To put this in perspective, imagine a cloud so large that light, traveling at 186,000 miles per second, would take centuries to cross from one side to the other. Yet despite their enormous size, these clouds are incredibly tenuous, with densities far lower than the best vacuum we can create on Earth. The temperature within these stellar nurseries hovers around 10 to 20 degrees above absolute zero, making them among the coldest places in the universe. At these frigid temperatures, atoms move sluggishly, and molecules can form more easily. Water, ammonia, methanol, and dozens of other compounds freeze onto tiny dust grains, creating microscopic snowflakes that drift through the cosmic void. These dust particles, though minuscule, play a crucial role in star formation. Each grain is smaller than the particles in cigarette smoke, yet they serve as shields, protecting the cloud's interior from the harsh radiation of nearby stars. This protection allows the gas to cool even further and begin the slow process of gravitational collapse. The Orion Nebula, visible to the naked eye as a fuzzy star in the constellation Orion, represents one of the most studied stellar nurseries in our galaxy. Located about 1,300 light years from Earth, this glowing cloud of gas and dust spans roughly 24 light years and contains enough material to form thousands of new stars. Within the Orion Nebula, astronomers have identified dense cores where star formation is actively occurring. These cores, typically a few light years across, contain several times the mass of our Sun concentrated into a relatively small volume. As we'll explore in our journey, these dense regions are where the magic of stellar birth truly begins. The beauty of stellar nurseries extends beyond their scientific importance. When viewed through telescopes, these cosmic clouds reveal intricate structures painted in ethereal colors. The red glow comes from hydrogen gas energized by nearby young stars, while blue regions often indicate reflected starlight bouncing off dust particles. Dark lanes and cavities carved by stellar winds create dramatic silhouettes against the glowing backdrop. The process of star formation within these nurseries unfolds over millions of years, a timescale that dwarfs human civilization but represents merely a moment in cosmic history. Understanding these processes helps us comprehend not only how stars form, but also how planetary systems, including our own solar system, came into existence billions of years ago. Gravity, the weakest of nature's four fundamental forces, becomes the dominant sculptor in the quiet realm of molecular clouds. Unlike the dramatic explosions and violent collisions we often associate with space, star formation begins with the gentlest of touches. Imagine gravity as a patient gardener, slowly gathering cosmic seeds over millions of years. Within a molecular cloud, gravity works constantly to pull every particle toward every other particle. However, this attraction is incredibly weak when dealing with such diffuse material. A single hydrogen atom in a molecular cloud experiences gravitational forces billions of times weaker than what we feel standing on Earth's surface. Yet given enough time, these tiny tugs accumulate into something profound. For gravity to overcome the natural tendency of gas to expand and disperse, the cloud must reach a critical threshold known as the Jeans mass, named after physicist James Jeans, who first calculated this relationship in 1902. Think of it like a cosmic tipping point. Below this mass, the cloud's internal pressure and turbulent motions keep it stable. Above this threshold, gravity gains the upper hand and collapse begins. The Jeans mass depends on both temperature and density. Colder clouds have lower Jeans masses, meaning they can begin collapsing with less material. This is why the frigid temperatures in molecular clouds are so important. At 10 degrees above absolute zero, a cloud needs only about one solar mass of material concentrated in a region roughly 1 light year across to begin gravitational collapse. But molecular clouds rarely exist in perfect isolation. They're stirred by various disturbances that can trigger or accelerate star formation. Shock waves from nearby supernovae, the gravitational influence of passing stars, or collisions between clouds can create density enhancements that push regions over the Jeans threshold. The Eagle Nebula, made famous by the Hubble Space Telescope's Pillars of Creation image, demonstrates this process beautifully. The towering columns of gas and dust are being sculpted by intense radiation from nearby massive stars. As this radiation evaporates material from the pillar surfaces, it reveals denser knots within that are actively forming new stars. Once gravitational collapse begins, it proceeds slowly at first. The initial contraction of a molecular cloud core takes roughly 100,000 years, a mere blink of an eye in cosmic terms, but still longer than all of human history. During this phase, the cloud remains nearly transparent, and its temperature stays constant as heat radiates away into space. As the cloud contracts, its gravitational field strengthens, accelerating the infall of material. Particles that started light years apart gradually spiral inward, following paths determined by the cloud's rotation and magnetic field. This process resembles water circling a drain, but stretched across distances that dwarf our solar system and timescales that span geological ages. The magnetic fields threading through molecular clouds add another layer of complexity to this cosmic choreography. These fields, though incredibly weak by terrestrial standards, can support the cloud against gravitational collapse for extended periods. Only when the magnetic field lines become sufficiently tangled or when the density increases enough to overwhelm magnetic support can collapse proceed unimpeded. As gravitational collapse continues, the once diffuse molecular cloud core begins its transformation into something more recognizable as a stellar precursor. This marks the birth of a protostar, though it bears little resemblance to the brilliant suns we see shining in our night sky. Instead, imagine a cosmic cocoon, hidden within layers of dust and gas, slowly awakening to its stellar destiny. The collapse accelerates as the core becomes denser. Material falls inward at speeds reaching several kilometers per second, carrying with it the angular momentum of the original cloud's rotation. Just as a figure skater spins faster when pulling in their arms, the contracting core begins to rotate more rapidly. This rotation prevents all the material from falling directly onto the central object, instead forming a flattened disk around the growing protostar. These circumstellar disks, also called protoplanetary disks, are where planets will eventually form. The disk serves as a cosmic conveyor belt, gradually feeding material onto the central protostar while providing the raw ingredients for future worlds. Our own solar system formed from such a disk roughly 4.5 billion years ago, making these structures particularly fascinating to astronomers seeking to understand planetary formation. The protostar itself remains hidden behind thick veils of dust during its early development. The infalling material heats up as it approaches the central object, but this heat is quickly absorbed and re-radiated by surrounding dust grains at much longer infrared wavelengths. To optical telescopes, the protostar remains invisible, detectable only through its infrared glow and the effects it has on surrounding material. During this embedded phase, which lasts roughly 100,000 years, the protostar grows primarily through accretion. Material from the surrounding disk spirals inward, releasing gravitational potential energy that heats both the disk and the central object. The protostar's surface temperature rises to several thousand degrees, hot enough to glow red if we could see through the obscuring dust. Not all the infalling material reaches the protostar's surface. Some is ejected in powerful bipolar jets that punch through the surrounding envelope at speeds of hundreds of kilometers per second. These jets, guided by magnetic fields, carry away excess angular momentum and help regulate the accretion process. The Herbig-Haro objects scattered throughout star-forming regions are shock waves created when these jets collide with surrounding gas. The protostar's internal structure during this phase resembles a layered onion. At the center, temperatures and pressures rise steadily but remain far below the levels needed for nuclear fusion. The core consists of molecular hydrogen slowly dissociating into atomic form as temperatures climb above 2,000 degrees. Surrounding layers contain a mixture of gas and dust, with the outer envelope still cold enough for molecules to survive. As the protostar continues to accrete material, its central temperature and pressure inexorably increase. The object becomes fully convective, meaning hot material from the interior rises to the surface while cooler material sinks inward. This convection efficiently transports heat throughout the protostar, maintaining a relatively uniform temperature gradient. The protostar phase represents a delicate balance between gravitational collapse and internal pressure. Unlike main sequence stars, which derive their energy from nuclear fusion, protostars are powered entirely by gravitational contraction. As the object shrinks, gravitational potential energy converts to heat, keeping the protostar warm and preventing further rapid collapse. After hundreds of thousands of years hidden within its dusty cocoon, the young protostar begins to assert its presence more dramatically. The surrounding envelope of gas and dust that once completely obscured the forming star starts to thin and disperse, marking the beginning of a crucial transition phase in stellar evolution. This clearing process occurs through several mechanisms working in concert. The protostar's increasing luminosity heats the surrounding dust, causing it to radiate energy and gradually evaporate. Stellar winds, streams of charged particles flowing outward from the protostar's surface, push against the remaining envelope material. Meanwhile, the powerful jets we discussed earlier continue to carve cavities through the surrounding medium. As the envelope clears, astronomers can finally observe the protostar directly at optical wavelengths. What emerges is a T-Tauri star, named after the first example discovered in the constellation Taurus. These young stellar objects are characterized by their variability, strong stellar winds, and the presence of circumstellar disks. They represent stars in their cosmic adolescence, no longer hidden infants but not yet mature main sequence stars. T-Tauri stars are remarkably active compared to older stars like our Sun. Their surfaces are covered with enormous magnetic field loops that can extend several stellar radii into space. These magnetic fields accelerate charged particles, creating powerful stellar winds that flow outward at hundreds of kilometers per second. The interaction between these winds and the surrounding material creates beautiful shock fronts visible in telescope images. The circumstellar disk plays a crucial role during this phase. While the star continues to accrete material from the inner disk regions, the outer portions begin the slow process of planet formation. Dust grains stick together through electrostatic forces, gradually building larger and larger aggregates. Over millions of years, these dust bunnies grow into pebbles, then boulders, and eventually planetesimals large enough for gravity to take over. The disk structure becomes increasingly complex as the young star evolves. Gravitational instabilities create spiral arms and gaps, while magnetic fields channel material along specific pathways. The inner regions, heated by the central star, become a realm of rocky materials, while the outer, cooler zones harbor water ice and other volatile compounds. During this phase, the young star's energy output comes from a combination of continued gravitational contraction and the accretion of disk material. The star has not yet reached the temperatures and pressures necessary for sustained nuclear fusion, so it continues to slowly shrink under its own gravity. This contraction releases energy that keeps the star shining, though much more dimly than it will during its main sequence lifetime. The clearing of the stellar nursery is not uniform or instantaneous. Different regions of the original molecular cloud core disperse at different rates, creating complex, evolving structures. Some material may linger in the system for millions of years, while other regions clear relatively quickly. This uneven process creates the beautiful, intricate shapes we observe in young stellar objects and their surrounding nebulae. Observations of nearby star-forming regions like the Taurus molecular cloud have revealed populations of T-Tauri stars at various stages of this clearing process. Some remain heavily embedded and detectable only at infrared wavelengths, while others have emerged as visible stars surrounded by thin, nearly transparent disks. This diversity allows astronomers to study stellar evolution as if watching a time-lapse movie of star formation. Deep within the contracting protostar, a momentous transformation approaches. For millions of years, the young star has derived its energy solely from gravitational contraction, slowly shrinking and heating as it converts potential energy into thermal energy. But as the core temperature climbs toward 10 million degrees, the star approaches the threshold for nuclear fusion, the process that will power it for billions of years to come. The journey to nuclear ignition is gradual and inevitable. As the protostar continues to contract under its own gravity, the atoms in its core are squeezed ever closer together. At temperatures below 10 million degrees, the electrical repulsion between positively charged hydrogen nuclei prevents them from approaching close enough to fuse. But as thermal energy increases, a small fraction of nuclei gain enough speed to overcome this electromagnetic barrier. The first nuclear reactions occur sporadically, like scattered sparks before a fire catches. Individual hydrogen nuclei, moving at tremendous speeds due to the extreme temperature, occasionally collide with enough energy to fuse together. These initial reactions release energy and helium nuclei, but the rate remains too low to significantly affect the star's energy balance. Think of this process like trying to start a campfire with damp wood. The first few sparks may catch briefly but quickly die out. Only when enough heat builds up does the fire become self-sustaining. Similarly, the star must reach a critical temperature where nuclear reactions generate enough energy to maintain the conditions necessary for continued fusion. The specific nuclear process powering stars like our Sun is called the proton-proton chain. In this sequence of reactions, four hydrogen nuclei ultimately combine to form one helium nucleus, releasing energy in the form of gamma rays and neutrinos. The gamma rays are gradually absorbed and re-emitted by the stellar material, eventually reaching the surface as visible light. The neutrinos, barely interacting with matter, stream directly out of the star at the speed of light. When nuclear fusion finally becomes self-sustaining, typically when the core temperature reaches about 15 million degrees, the star undergoes a fundamental change in character. The energy generated by fusion creates an outward pressure that exactly balances the inward pull of gravity. This equilibrium marks the star's arrival on the main sequence, the stable phase that will dominate most of its lifetime. The transition to main sequence status doesn't happen overnight. The star must adjust its structure to accommodate the new energy source at its core. Convection patterns change, the stellar atmosphere settles into a more stable configuration, and the violent variability characteristic of T-Tauri stars gradually subsides. This adjustment period can take several million years for stars like our Sun. The newly ignited star's appearance changes dramatically during this transition. The chaotic brightness variations of the T-Tauri phase give way to steady, reliable energy output. Strong stellar winds diminish as the star's magnetic field becomes more organized. The circumstellar disk, no longer fed by active accretion, begins its final evolution toward a mature planetary system. Nuclear ignition also marks the beginning of the star's long-term evolution. The fusion of hydrogen into helium in the core gradually changes the star's internal composition and structure. Over billions of years, this process will drive the star through various evolutionary phases, ultimately determining its final fate as a white dwarf, neutron star, or black hole. For stars with masses similar to our Sun, the main sequence phase lasts approximately 10 billion years. More massive stars burn through their nuclear fuel much more quickly, existing fast and dying young in cosmic terms. The most massive stars may exhaust their hydrogen fuel in just a few million years, while the smallest red dwarf stars can continue fusing hydrogen for trillions of years. Most stars are not born alone. The molecular clouds that serve as stellar nurseries typically fragment into multiple dense cores, leading to the formation of stellar clusters containing dozens, hundreds, or even thousands of young stars. These cosmic families, born from the same parent cloud, share similar ages and chemical compositions while displaying a fascinating range of masses and evolutionary paths. The process of cluster formation begins during the initial collapse of a molecular cloud. Rather than contracting uniformly, the cloud develops density fluctuations that grow over time. Turbulence within the cloud creates a complex web of filaments and knots, each potentially capable of forming one or more stars. Computer simulations of this process reveal intricate, branching structures resembling cosmic river deltas or neural networks. As individual cores within the fragmenting cloud begin their own gravitational collapse, they compete for the available material. Cores that start with slight advantages in mass or density can grow more rapidly, sometimes capturing material that might otherwise have formed individual stars. This competitive accretion helps explain why stellar clusters exhibit such a wide range of stellar masses. The Pleiades, visible to the naked eye as a tight grouping of bright blue stars in the constellation Taurus, represents a beautiful example of a young stellar cluster. Located about 440 light-years from Earth, this cluster contains over 1,000 stars formed from the same molecular cloud roughly 100 million years ago. The brightest members are hot, massive stars that shine with brilliant blue-white light, while fainter red dwarf stars make up the majority of the cluster's population. Open clusters like the Pleiades are loosely bound by gravity and gradually disperse over hundreds of millions of years. As the cluster orbits through the galaxy, gravitational encounters with other stars and molecular clouds slowly strip away members. Eventually, the cluster dissolves completely, leaving its former members scattered throughout the galactic disk as field stars. More tightly bound are globular clusters, ancient stellar cities containing hundreds of thousands to millions of stars packed into spherical volumes just tens of light years across. However, these represent a different population of stars, formed during the early history of our galaxy when conditions were quite different from those in present-day stellar nurseries. The formation of stellar clusters has profound implications for planetary system development. In the dense environment of a young cluster, gravitational interactions between stars can disrupt planetary formation or strip away newly formed planets. Close encounters might scatter comets and asteroids, potentially delivering water and organic compounds to inner planets or, conversely, removing these materials entirely. Binary and multiple star systems are common products of cluster formation. When two or more protostars form close together, they can become gravitationally bound, orbiting around their common center of mass. Roughly half of all stars in our galaxy are members of binary or multiple systems, making our solitary sun somewhat unusual. The study of stellar clusters provides crucial insights into star formation and early stellar evolution. Since all members of a cluster formed at essentially the same time and from the same material, differences between cluster stars reflect primarily their different masses. This allows astronomers to test theories of stellar evolution by observing stars at various stages of development within a single cluster. Young clusters also serve as laboratories for understanding the initial mass function, the distribution of stellar masses produced during star formation. Observations consistently show that low-mass stars vastly outnumber high-mass stars, with the most massive stars being extremely rare. This pattern appears universal, suggesting fundamental physical processes govern how molecular clouds fragment and form stars. The dispersal of stellar clusters plays an important role in galactic chemical evolution. Massive stars in young clusters exist brief but spectacular existences, ending in supernova explosions that scatter heavy elements throughout the surrounding interstellar medium. These enriched materials become incorporated into future generations of stars and planets, gradually increasing the metallicity of the galaxy over cosmic time. As we reach the end of our peaceful journey through stellar nurseries, it's worth reflecting on the profound cyclical nature of star formation. The process we've explored, from the initial stirring of molecular clouds to the nuclear ignition of newborn stars, represents just one movement in a cosmic symphony that has played for billions of years and will continue for billions more. The stars born in these nurseries will themselves become agents of change in the galaxy. The most massive among them will exist spectacular but brief existences, fusing hydrogen into helium, then helium into carbon, oxygen, and heavier elements in their cores. When these stellar giants exhaust their nuclear fuel, they'll explode as supernovae, blasting their enriched material back into the interstellar medium at tremendous speeds. These supernova shock waves serve multiple purposes in the galactic ecosystem. They heat and stir the interstellar gas, creating the turbulence that helps trigger new episodes of star formation. They also enrich the gas with heavy elements forged in stellar cores, providing the raw materials for rocky planets and, ultimately, biological processes. Every atom of carbon in our bodies, every molecule of oxygen we breathe, was created in the nuclear furnace of a star that existed and died before our sun was born. Even stars like our sun, too small to explode as supernovae, contribute to this cosmic recycling. During their final evolutionary phases, they'll puff off their outer layers as planetary nebulae, returning roughly half their mass to the interstellar medium. These gentle stellar exhalations carry the products of nuclear burning back to the galactic community, ready to be incorporated into future stellar generations. The molecular clouds themselves are not permanent features. Over timescales of tens of millions of years, they form, evolve, and disperse. Some are disrupted by the very stars they create, as stellar winds and radiation gradually erode the parent cloud. Others are torn apart by galactic tidal forces or collisions with neighboring clouds. Yet new molecular clouds continuously form from the cooling and condensation of hot interstellar gas. This eternal cycle connects us intimately to the cosmos. The calcium in our bones was forged in the core of a dying star. The iron in our blood was created during a supernova explosion. The water we drink contains hydrogen atoms that may have drifted through multiple molecular clouds before becoming part of the disk from which Earth formed. We are, quite literally, made of star stuff. Modern astronomy continues to refine our understanding of stellar birth through increasingly sophisticated observations and computer simulations. Space telescopes like Spitzer and Herschel have peered through dust clouds to reveal protostars in their earliest stages. The Atacama Large Millimeter Array has mapped the intricate structures of protoplanetary disks with unprecedented detail. Future missions will undoubtedly reveal new aspects of this ancient process. Perhaps most remarkably, the formation of stars and planets appears to be a common, even inevitable, consequence of the laws of physics operating in our universe. Wherever we find the right conditions of gravity, temperature, and density, stellar nurseries emerge. This suggests that the cosmos is filled with worlds, some perhaps harboring biological processes that, like us, are composed of elements forged in stellar cores and wondering about their place in the universe. The gentle processes we've explored tonight, playing out over vast scales of space and time, remind us of our connection to something far grander than our daily experience suggests. In the quiet darkness between the stars, new suns are always being born, continuing a story that began billions of years ago and will continue long after our own star has faded to a cold white dwarf. And on that note, we conclude our serene voyage through the stellar nurseries where baby stars are born. We've drifted through molecular clouds vast beyond imagination, witnessed the patient work of gravity as it gathers cosmic dust into newborn suns, and observed the eternal cycle that connects every atom in our bodies to the nuclear furnaces of distant stars. From the initial stirring of gas and dust in the depths of space to the moment when nuclear fusion ignites in a protostar's core, we've followed the gentle transformation that turns the simplest ingredients into the brilliant lights that illuminate our night sky. These processes, unfolding over millions of years across distances measured in light years, remind us that the universe operates on scales both humbling and beautiful. All objects we observe today lie inside what astronomers call the particle horizon, which forms the boundary of the observable universe. If an object lies beyond this particle horizon, then the universe is not old enough for its light to have had enough time to reach us. Think of this cosmic boundary like an enormous sphere surrounding us in every direction, but it's not made of any physical material. Instead, it's made of time itself. Picture yourself in a vast theater where the lights have just been turned on after being dark for countless eons. The light from the stage reaches your eyes almost instantly, but light from the back row takes a fraction longer. Now imagine this theater is so enormous that even traveling at the speed of light, some illumination from the furthest seats hasn't reached you yet. This is exactly what happens on a cosmic scale. Our universe is approximately 13.8 billion years old, which means we can only see objects whose light has had that much time to travel to us. This creates what we call the observable universe, a sphere roughly 28 billion light years across, with Earth sitting right at the center. But here's where it gets fascinating. This isn't because we're special or located in some privileged position. Every observer in the universe sits at the center of their own observable sphere. The boundary isn't a wall in the traditional sense. There's no cosmic construction material blocking our view, no galactic curtain hanging in space. Instead, it's a horizon of information, a limit imposed by the fundamental nature of light and time. Beyond this boundary, galaxies, stars, and entire cosmic structures may exist, but their stories remain forever hidden from us. Their light simply hasn't had enough time since the Big Bang to complete its journey to our telescopes. What makes this boundary even more intriguing is that it's not static. This expansion means that the cosmic horizon is not a fixed boundary but a dynamic limit that changes over time. Every second that passes, light from slightly more distant objects crosses this threshold and becomes visible to us for the first time. Our universe is constantly revealing new chapters of its story, one photon at a time. This cosmic horizon represents one of the most fundamental limits in physics. Unlike barriers we might encounter on Earth, this one cannot be overcome through better technology or more powerful rockets. It's woven into the very structure of space-time itself, a boundary that emerged from the moment our universe began its expansion from that initial, incomprehensibly hot and dense state we call the Big Bang. The most remarkable thing about our cosmic boundary isn't what lies beyond it, but what we can actually observe at its edge. The cosmic microwave background is the cooled remnant of the first light that could ever travel freely throughout the universe. This fossil radiation was released soon after the Big Bang. When we look toward the edge of our observable universe, we're not peering into empty space, but rather witnessing the afterglow of creation itself. Imagine the early universe as a thick fog so dense that light couldn't travel more than a tiny distance before hitting something. For the first 380,000 years after the Big Bang, the universe was filled with a hot plasma where photons constantly scattered off free electrons, creating a cosmic soup that was completely opaque. Then something extraordinary happened. As the universe expanded and cooled, electrons and protons combined to form the first hydrogen atoms, and suddenly the fog cleared. Light could finally travel freely through space. This moment, called recombination, marked the universe's transition from opacity to transparency. The light that was released during this cosmic dawn is what we observe today as the cosmic microwave background radiation. This very uniform glow of microwaves was emitted by the infant universe more than 13 billion years ago. Every direction we look in the sky, we see this ancient light, cooled and stretched by billions of years of cosmic expansion. Think of it like looking at the surface of the sun, but instead of seeing the surface of a star, We're seeing the surface of the entire universe at its moment of transparency. This radiation fills every cubic centimeter of space, a constant reminder of our cosmic origins. Radio telescopes detect approximately 400 photons of this primordial light in every cubic centimeter of empty space, making it the most abundant form of radiation in the universe after starlight. The temperature of this cosmic afterglow tells us an incredible story. Today it measures just 2.7 degrees above absolute zero, but when it was first released, it glowed at a temperature of about 3,000 degrees. The dramatic cooling occurred because the expansion of space itself stretched the wavelengths of these ancient photons, shifting them from visible light into microwaves. This stretching is like a cosmic Doppler effect, where the expansion of space itself redshifts the light. According to the Planck mission data, the age of the universe is 13.8 billion years old, and this ancient light provides our most precise measurement of that age. The patterns and tiny temperature variations in this background radiation act like fossilized sound waves from the infant universe, preserving information about the density and composition of matter in those earliest moments. These fluctuations, smaller than 1 part in 100,000, were the seeds that eventually grew into galaxies, stars, and everything we see today. To truly understand our cosmic boundary, we need to grasp how space itself behaves on the largest scales. The universe isn't expanding into some pre-existing empty space, rather space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. This expansion creates some of the most counterintuitive phenomena in all of physics, fundamentally altering how we think about distance and time on cosmic scales. Consider two galaxies separated by a vast distance. If space between them expands, they move apart without actually traveling through space. They're carried apart by the expansion of space itself. This might seem like a subtle distinction, but it has profound implications for what we can observe. Some regions of space are now moving away from us faster than the speed of light due to this expansion, making them forever unobservable from Earth. This creates what cosmologists call the cosmic event horizon, which is different from our particle horizon. While the particle horizon represents the distance light has traveled since the Big Bang, the event horizon represents the boundary beyond which events happening now will never be observable to us, no matter how long we wait. It's roughly 16 billion light-years away, and galaxies beyond this distance are receding so quickly due to cosmic expansion that their light will never catch up to us. Picture yourself on a giant cosmic treadmill that's speeding up. Even if you run towards someone ahead of you, if the treadmill itself is moving backwards, you'll actually move further apart despite your efforts. This is what happens to light from very distant galaxies. The photons race toward us at the speed of light, but space expands so rapidly between us and those distant sources that the light gets carried further away even as it travels in our direction. The geometry of space itself plays a crucial role in these cosmic boundaries. Current observations suggest our universe is geometrically flat, meaning parallel lines remain parallel and the angles of triangles add up to 180 degrees, just as they do in everyday Euclidean geometry. However, this flatness extends only across the observable portion of the universe. The global geometry of the entire cosmos remains unknown and might be fundamentally unknowable. This flat geometry has important implications for infinity. In a flat, infinite universe, every possible arrangement of matter and energy would repeat infinitely many times. There would be infinite copies of our galaxy, our solar system, and even infinite versions of you. However, these cosmic duplicates would lie far beyond our observable horizon, separated by distances so vast that no information can ever travel between them. The cosmic boundary thus becomes a fundamental limit not just on what we can see, but on what can causally influence us. The question of what exists beyond our cosmic horizon represents one of the deepest mysteries in all of science. By definition, we cannot observe anything beyond this boundary, yet theoretical physics provides several compelling possibilities for what might lie in those unreachable regions. Each scenario carries profound implications for our understanding of reality itself. According to one theory, the universe extends infinitely in all directions. In an infinite universe, our observable region would represent an infinitesimally small fraction of the total cosmos. Beyond our horizon, galaxies, stars, and planetary systems would continue indefinitely, following the same physical laws that govern our local cosmic neighborhood. The cosmic microwave background would extend everywhere, and the same processes of star formation and galactic evolution would play out across boundless space. An infinite universe raises fascinating questions about repetition and uniqueness. In truly infinite space, every possible arrangement of matter would occur not just once, but infinitely many times. This means there would be perfect copies of our galaxy located at unimaginably distant locations, complete duplicates of our solar system, and even exact replicas of Earth with identical histories. These cosmic twins would exist beyond our causal horizon, forever unreachable yet identical in every detail. The multiverse theory assumes that there are many universes that may have different properties. Our cosmic horizon might represent just the boundary of one universe among countless others, each with potentially different physical constants, laws of nature, and evolutionary histories. Some of these parallel universes might have stronger or weaker gravity, different values for the speed of light, or alternative configurations of fundamental particles that lead to entirely different forms of matter and energy. Another possibility involves curved spacetime. Space can be closed, like the surface of a sphere returning to the initial point. If our universe has positive curvature, it might wrap back on itself like the surface of a hypersphere. In such a universe, if you could travel far enough in any direction, you would eventually return to your starting point, similar to how you can circumnavigate the Earth. Our cosmic horizon would still exist due to the finite age of the universe, but beyond it would lie more regions of the same universe, possibly including distant views of our own cosmic neighborhood. Perhaps most intriguingly, some theories suggest our entire universe might exist within a higher dimensional structure. The hypothesis states that our universe in general may be part of a black hole in another dimension. In this scenario, what we experience as the Big Bang and cosmic expansion might be the formation and growth of a black hole as viewed from a higher dimensional perspective. Our cosmic horizon would then represent a boundary in this higher dimensional space, beyond which lie realms operating under completely different physical principles. Each of these possibilities reminds us that our cosmic boundary represents not just a limit on observation, but a fundamental constraint on knowledge itself. Our cosmic boundary isn't frozen in place, it's constantly evolving as the universe ages and expands. Understanding how this horizon changes over time reveals the dynamic relationship between cosmic expansion, the speed of light, and the ultimate fate of our observable universe. This evolution tells a story of both revelation and loss, as new regions come into view while others slip forever beyond our reach. Every second, light from objects roughly 300,000 kilometers further away crosses our particle horizon for the first time, adding new volume to our observable universe. This might seem like we're constantly expanding our view of the cosmos, and in one sense we are. Previously invisible galaxies and cosmic structures continuously emerge from beyond the horizon, their ancient light finally completing journeys that began billions of years ago. However, The story of our expanding view is complicated by the acceleration of cosmic expansion. Observations of distant supernovae revealed that the expansion of space is actually speeding up, driven by a mysterious force cosmologists call dark energy. This acceleration means that while our particle horizon grows larger, our event horizon, the boundary of what we can ever hope to see, actually shrinks. The cosmic microwave background provides a perfect example of this evolution. The radiation we observe today was emitted when the universe was only 380,000 years old, from a region that was then about 42 million light-years away from the matter that would eventually become our galaxy. However, due to cosmic expansion, those same regions are now estimated to be about 46 billion light-years away, well beyond what we might naively expect for a 13.8 billion-year-old universe. As we look toward the far future, the cosmic horizon will continue its complex dance of expansion and limitation. In the very distant future, perhaps 100 billion years from now, the accelerating expansion will have carried most galaxies beyond our event horizon. Future astronomers in our galaxy will observe a much lonelier universe, with only the galaxies in our local cluster remaining visible. The cosmic microwave background will have cooled and faded, and the evidence for the Big Bang itself may become difficult to detect. This evolutionary perspective adds a poignant dimension to cosmology. We exist during a special epoch when the universe is old enough to have developed complex structures like galaxies and stars, yet young enough that we can still observe the cosmic microwave background and distant galaxies that tell us about cosmic history. Our position in time is as privileged as our position in space for understanding the cosmos. Determining the exact size and properties of our cosmic horizon represents one of the greatest measurement challenges in science. Unlike distances we can measure with rulers or even radar, cosmic distances require ingenious methods that push the boundaries of observational astronomy. Each technique reveals different aspects of our cosmic boundary while highlighting the profound difficulties of measuring the unmeasurable. Astronomers use what they call the cosmic distance ladder, a series of interconnected measurement techniques that allow us to gauge distances across increasingly vast scales. It begins with parallax measurements of nearby stars, where we observe how their positions shift as Earth orbits the Sun. This provides direct geometric distances to stars within a few hundred light-years, creating the foundation for all other cosmic distance measurements. The next rung involves Cepheid variable stars, whose brightness pulses in a predictable pattern related to their intrinsic luminosity. By measuring how bright these stars appear compared to how bright they actually are, astronomers can calculate their distances. This technique extends our reach to nearby galaxies, including the Andromeda Galaxy and other members of our local galactic neighborhood. For the most distant objects near our cosmic horizon, astronomers rely on Type 1a supernovae, thermonuclear explosions of white dwarf stars that reach nearly identical peak brightness. These cosmic lighthouses can be seen across billions of light years, allowing us to measure distances to galaxies when the universe was much younger. The observations of distant supernovae in the 1990s revealed that cosmic expansion is accelerating, fundamentally changing our understanding of the universe's fate. The cosmic microwave background provides our most precise tool for measuring cosmic parameters. Tiny temperature variations in this ancient light create patterns across the sky that depend on the fundamental properties of the universe, including its age, composition, and geometry. The Planck mission measured the age of the universe as 13.8 billion years old, providing our most accurate determination of when cosmic time began. However, measuring our cosmic horizon involves more than just distance. Because space itself expands, we must carefully distinguish between different types of distances. The light travel time distance tells us how long light has been traveling to reach us. The comoving distance accounts for how far objects have moved due to cosmic expansion since they emitted their light. The angular diameter distance describes how large objects appear in the sky, while the luminosity distance determines how bright they appear. These multiple distance definitions create a complex picture of cosmic geometry. An object whose light has traveled for 10 billion years is not necessarily 10 billion light years away today. Due to cosmic expansion, it's actually much further. This expansion also means that the most distant objects we can observe emitted their light when they were much closer to us than they are now. Recent measurements have revealed tensions between different methods of determining cosmic distances and expansion rates. These discrepancies, sometimes called the Hubble tension, suggest either systematic errors in our measurements or new physics beyond our current understanding of cosmology. Resolving these tensions remains one of the most important challenges in modern astronomy. Our cosmic horizon represents far more than just an observational limit. It embodies fundamental truths about the nature of reality, causality, and our place in the cosmos. The existence of this boundary raises profound questions about knowledge, infinity, and the very meaning of existence on the largest possible scales. Understanding these implications transforms how we think about everything from physics to philosophy. The horizon creates what physicists call causal disconnection. Events occurring beyond our cosmic boundary cannot influence us in any way, nor can we affect them. This isn't simply a matter of current technological limitations, it's a fundamental feature of spacetime itself. Two regions of the universe separated by more than the horizon distance exist in complete causal isolation, as if they were separate universes entirely. This challenges our intuitive notion that all of space is somehow connected and unified. Consider the implications for the nature of physical laws. We observe that physics appears remarkably uniform across our observable universe. The same atomic spectra appear in galaxies billions of light years away, suggesting that the fundamental constants of nature are identical everywhere we can look. But what about beyond the horizon? We have no way of knowing whether the same laws apply in those unreachable regions. The cosmic boundary thus represents the limit of empirical science itself. The horizon problem in cosmology illustrates these deep puzzles. Different regions of the cosmic microwave background, separated by angles larger than about 2 degrees on the sky, were never in causal contact during the early universe. Yet these regions show nearly identical temperatures, as if they somehow coordinated their properties despite never being able to exchange information. This puzzle led to the development of cosmic inflation theory, which proposes that the early universe underwent a brief period of exponential expansion that brought distant regions into causal contact before stretching them beyond the horizon. Our cosmic boundary also illuminates questions about infinity and uniqueness. If the universe extends infinitely beyond our horizon, then every possible configuration of matter and energy occurs infinitely many times. This includes exact duplicates of our galaxy, solar system, and even ourselves. But if the universe is finite, we might represent truly unique arrangements of matter and energy. The cosmic horizon prevents us from ever knowing which scenario is correct. The concept of cosmic horizons also appears in other areas of physics, most notably in black hole physics. Black holes have event horizons beyond which nothing can escape, creating boundaries that are remarkably similar to our cosmic horizons. Some physicists suggest deep connections between these different types of horizons, hinting at fundamental principles that govern the flow of information in the universe. The holographic principle proposes that all information contained within a volume of space can be encoded on its boundary, suggesting that our three-dimensional reality might somehow be encoded on our cosmic horizon. Perhaps most remarkably, our cosmic boundary serves as a mirror reflecting our own significance and limitations. We exist as conscious observers in a universe vast beyond comprehension, capable of contemplating boundaries we can never cross. The very fact that we can conceive of and study our cosmic horizon represents one of the greatest achievements of human curiosity and intelligence. We have used mathematics, physics, and careful observation to map the unmappable and measure the unmeasurable. As we reach the end of our journey to the edge of everything, we find ourselves confronting the most profound boundary in existence. The cosmic horizon stands as both a wall and a window, limiting what we can know while revealing the magnificent scope of cosmic history. This invisible boundary, forged in the first moments after the Big Bang, continues to evolve as our universe expands and ages, constantly reshaping our view of reality itself. We've discovered that our cosmic horizon isn't simply empty space waiting to be explored, but rather the afterglow of creation itself, preserved in the ancient light of the cosmic microwave background. We've seen how the expansion of space creates multiple types of horizons, some bringing new regions into view while others carry distant galaxies forever beyond our reach. We've explored the profound challenges of measuring distances on cosmic scales and the deep implications of living in a causally bounded universe. Perhaps most importantly, we've learned that the cosmic horizon represents the ultimate expression of both our capabilities and our limitations as conscious beings. Through careful observation and brilliant reasoning, we've mapped the boundary of the knowable universe, yet that very boundary reminds us that some questions may forever remain beyond our reach. The horizon humbles us while simultaneously celebrating the remarkable fact that we can contemplate such vast scales at all. In the end, the edge of everything teaches us that we inhabit a universe of breathtaking scope and beauty, one where the journey of discovery is as important as any destination. Every photon that crosses our cosmic threshold carries with it a story from the deep past, connecting us to the very origins of space and time. The story of rogue planets begins not with telescopes pointed at distant stars, but with a mystery. In the 1990s, astronomers began noticing something peculiar during their surveys of star-forming regions. They found dim infrared signatures that resembled planets in temperature and size, but these signatures appeared in places where no parent star existed nearby. These were the first hints that planets could exist without suns. The confirmation came through a technique called gravitational microlensing. Think of space itself as a fabric, like a bedsheet pulled taut. When a massive object passes through this fabric, it creates a dip, much like placing a bowling ball on that bedsheet. If light from a distant star passes near this dip, the light bends around it, briefly brightening the star as seen from Earth. In 2011, astronomers published findings describing a survey that detected multiple microlensing events consistent with planetary mass objects floating freely through the Milky Way. These detections suggested that rogue planets might be astonishingly common, possibly outnumbering stars themselves. These worlds remained theoretical curiosities until better detection methods emerged. The difference between seeing a planet next to a bright star and seeing one in empty space is like the difference between spotting a firefly next to a searchlight versus spotting one against a dark forest. Alone in space, these planets became slightly easier to detect through their infrared emissions, the faint heat they still radiate from their formation billions of years ago. By 2015, astronomers had cataloged several candidate rogue planets, including one discovered floating between star systems roughly 100 light-years from Earth. This particular world showed characteristics suggesting it was between 4 and 7 times the mass of Jupiter, with a temperature around 400 degrees Celsius, still glowing from the heat of its formation. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, is expected to revolutionize rogue planet detection. This observatory will conduct an extensive microlensing survey, potentially discovering thousands of these wandering worlds. Scientists predict it will help answer fundamental questions about how common rogue planets truly are and what sizes they typically possess. Current estimates, based on microlensing surveys and extrapolations from known detection methods, suggest there could be billions of rogue planets drifting through our galaxy alone. Some models propose there might be twice as many rogue planets as there are stars, making them one of the most numerous types of planetary bodies in the cosmos, yet also among the most invisible. Understanding how a planet becomes untethered from its star requires us to imagine the chaotic early days of solar system formation. When stars are born, they emerge from collapsing clouds of gas and dust, surrounded by rotating disks of material. Within these disks, planets gradually coalesce from countless collisions between smaller bodies. But this process is far from orderly. Multiple planets forming in close proximity create a gravitational dance that can turn violent. Picture a game of planetary billiards happening over millions of years. When 3 or more planets form in a young solar system, their gravitational interactions can become unstable. Computer simulations run by astronomers show that these multi-planet systems often undergo periods of dramatic reshuffling. A planet might swing too close to a larger neighbor, receiving a gravitational boost that flings it onto a different orbit. If this boost is strong enough, the planet can be ejected entirely from the solar system, sent tumbling into interstellar space at speeds of dozens of kilometers per second. Research published in the Astrophysical Journal indicates that these ejection events are particularly common in systems with multiple gas giants, where the massive planets gravitationally bully each other until one or more are cast out. Another pathway to becoming a rogue involves stellar close encounters. Young star systems often form in clusters where stars are born together, packed relatively close in cosmic terms. When 2 star systems pass near each other, their gravitational fields can interact, potentially stripping planets away from one system or the other. Think of it like 2 people walking past each other in a crowded space, where one person's bag might get caught on the other's arm and pulled away. These stellar encounters were likely more common in the early universe when star-forming regions were denser and more active. There's also a more dramatic origin story, the destruction of the parent star itself. When massive stars reach the end of their existence, they can explode as supernovae, devastating events that release more energy in seconds than our sun will emit over its entire 10 billion-year lifespan. Any planets orbiting such a star face an uncertain fate. Some are vaporized by the explosion's energy, but others, particularly those in distant orbits, might survive and be flung into space by the sudden loss of their star's gravitational anchor. These planets would carry with them the scars of their violent liberation, potentially bearing surface evidence of the intense radiation they endured during their star's death throes. Finally, some rogue planets may never have orbited a star at all. In the densest parts of star-forming clouds, pockets of gas might collapse directly into planetary mass objects without ever accumulating enough material to ignite fusion and become stars. These objects, sometimes called sub-brown dwarfs, blur the line between planet and star. They form in isolation, born as wanderers from the very beginning, never knowing the warmth of a parent sun. To understand what conditions exist on a rogue planet, we must first appreciate what a star provides. Our sun delivers roughly 1,300 watts of energy to every square meter of Earth facing it. This energy drives our weather, powers photosynthesis, and maintains our planet's surface temperature at an average of about 15 degrees Celsius. Remove the sun, and Earth would undergo a catastrophic transformation. Within days, surface temperatures would plummet below freezing. Within weeks, the oceans would begin to freeze. Within a year, the atmosphere itself would start condensing and snowing down as frozen nitrogen and oxygen. This is the fate that awaits any Earth-like world ejected into interstellar space. Studies modeling the thermal evolution of rogue planets indicate that a rocky world similar to Earth would rapidly lose its surface heat to the cosmic background radiation, which permeates all of space at a frigid 2.7 degrees above absolute zero. The planet's atmosphere would collapse onto its surface as layers of frozen gases. Any water would become ice harder than granite. The surface would settle into a temperature equilibrium just slightly above the background temperature of space itself, warmed only by the faint trickle of heat from radioactive decay in the planet's core and the residual warmth from its formation. But here's where the story becomes more interesting. A planet doesn't stop being geologically active just because it loses its star. Earth's interior remains hot not because of the sun, but because of heat left over from its violent formation 4.5 billion years ago, combined with the ongoing decay of radioactive elements like uranium, thorium, and potassium deep in the mantle and core. These heat sources are completely independent of sunlight. A rogue planet of Earth's size would retain significant internal heat for billions of years after its ejection, just as Earth has maintained its molten core despite radiating heat into space since its formation. This internal heat has profound implications. On Earth, this geothermal energy drives plate tectonics, volcanic activity, and hydrothermal vents on the ocean floor. These processes would continue on a rogue Earth, hidden beneath the frozen surface. Consider the subsurface oceans we've discovered in our own solar system. Jupiter's moon Europa possesses a global ocean beneath an ice shell several kilometers thick, kept liquid by tidal heating from Jupiter's gravity and by its own internal heat. Saturn's moon Enceladus similarly harbors an ocean that erupts through cracks in its ice, forming geysers visible from space. A rogue planet could maintain similar conditions without any external heat source at all, relying solely on its internal thermal reserves and the insulating properties of an ice layer potentially tens of kilometers thick. The ice layer itself would act as a blanket. Ice is an excellent insulator, which is why igloos work and why animals in cold climates often burrow into snow for warmth. On a rogue planet, the thick crust of frozen water and atmospheric gases would trap heat trying to escape from below, creating a stable temperature gradient. At the surface, temperatures might hover around 30 degrees above absolute zero, but descend through the ice, and temperatures would steadily rise. At the boundary between ice and liquid water, temperatures would reach the melting point, similar to conditions beneath Antarctica's ice sheet. Deeper still, near volcanic vents or hydrothermal systems, temperatures could climb to hundreds of degrees Celsius, creating warm pockets in an otherwise frozen world. Finding a planet that emits no reflected light and drifts through empty space represents one of astronomy's most difficult challenges. These worlds are naturally dark, invisible to conventional telescopes that rely on detecting light reflected from a star. To find rogue planets, astronomers have developed specialized techniques that exploit subtle physical phenomena. The primary method, gravitational microlensing, works by detecting the temporary brightening of a background star when a massive object passes between that star and Earth. Einstein's theory of general relativity predicts that mass warps spacetime, bending light rays that pass nearby. When a rogue planet drifts in front of a distant star from our perspective, the planet's gravity acts like a lens, focusing the star's light toward us and making the star appear brighter for a brief period. The duration of this brightening event depends on the planet's mass and speed. A Jupiter-mass rogue might cause a brightening lasting several days, while an Earth-mass rogue might produce an effect lasting only hours. The challenge is that these events are non-repeating and unpredictable. Unlike planets orbiting stars, where we can predict future transits once we've detected one, a rogue planet will never pass in front of the same background star again from our perspective. This means astronomers must monitor millions of stars simultaneously, watching and waiting for the telltale brightening pattern that signals a microlensing event. The Optical Gravitational Lensing Experiment Survey has monitored stars in the galactic bulge for decades, detecting numerous microlensing events. By analyzing the precise shape and duration of these brightening curves, astronomers can determine whether the lensing object is a star, a planet orbiting a star, or a rogue planet traveling alone. Direct imaging offers another detection avenue, but only for young, massive rogues. When a planet forms, the gravitational collapse generates enormous heat, which the planet radiates away slowly over billions of years. Young rogue planets, those only a few million years old, still glow brightly in infrared wavelengths from this formation heat. Giant planets like those several times Jupiter's mass can remain detectable in infrared for tens of millions of years after formation. Surveys using infrared telescopes have discovered several candidate young rogue planets this way, identifying isolated planetary mass objects in or near star-forming regions. These infrared surveys face their own challenges. First, they can only detect the most massive and youngest rogues, missing the vast population of older or smaller wandering worlds. Second, distinguishing a young rogue planet from a low-mass brown dwarf, a failed star that never gained enough mass to sustain fusion, remains difficult. Both appear similar in infrared observations, and the boundary between a massive planet and a low-mass brown dwarf is somewhat arbitrary. Astronomers generally classify objects below about 13 Jupiter masses as planets, but this distinction becomes murky for objects that formed in isolation rather than in a protoplanetary disk. The upcoming Nancy Grace Roman Space Telescope will combine a wide field of view with exquisite sensitivity to conduct the most comprehensive microlensing survey yet attempted. Its mission includes a dedicated program to search for rogue planets down to Mars' mass, potentially discovering thousands of these wandering worlds. By statistically analyzing the frequency and mass distribution of detected rogues, astronomers will be able to estimate the total population of free-floating planets in the galaxy and better understand the dynamics of planetary system formation and evolution. One of the most intriguing questions about rogue planets concerns the possibility of habitability. At first glance, this seems absurd. How could anything survive on a frozen world drifting through the void, far from any star's warmth? Yet scientists have identified several scenarios where rogue planets might harbor conditions suitable for certain forms of existence. The key lies beneath the ice. As we discussed earlier, a sufficiently large rogue planet would retain internal heat for billions of years. If that planet possessed water, the combination of insulating ice above and heat sources below could maintain liquid water oceans in the darkness. On Earth, we've discovered thriving ecosystems around deep-sea hydrothermal vents, places where superheated water rich in minerals erupts from the ocean floor. These ecosystems operate without any input from sunlight. Instead, microorganisms use chemosynthesis, deriving energy from chemical reactions involving compounds like hydrogen sulfide, methane, and iron. These microorganisms form the base of a food chain that includes tube worms, crabs, fish, and other creatures, all existing in complete darkness. A rogue planet with active geology could support similar chemosynthetic ecosystems. Research published in the International Journal of Astrobiology has explored this possibility, modeling the long-term habitability of subsurface oceans on rogue planets. The studies suggest that a planet roughly Earth's mass with sufficient water and radioactive elements could maintain habitable conditions for billions of years. The ice layer would need to be thick enough to provide insulation, but thin enough to allow some exchange of materials through cracks and convection. Hydrothermal vents on the ocean floor would provide both heat and chemical nutrients, creating potential oases in the dark. The atmosphere, or rather the lack of a traditional one, presents both challenges and opportunities. On a rogue planet, most atmospheric gases would freeze and accumulate on the surface. However, if the planet retains volcanic activity, it would continuously replenish the atmosphere with gases erupted from the interior. These gases, including water vapor, carbon dioxide, and methane, would partially freeze but could create a thin, dynamic atmosphere. The interplay between volcanic outgassing and atmospheric freezing would establish an equilibrium unique to each rogue planet, depending on its size, composition, and level of geological activity. There's another intriguing possibility involving hydrogen atmospheres. Hydrogen is the lightest element and remains gaseous at extremely low temperatures compared to other compounds. A rogue planet with a thick hydrogen atmosphere could trap enough heat to maintain significantly warmer surface temperatures through greenhouse warming. Calculations suggest that a rocky planet with a hydrogen atmosphere a few percent of its total mass could keep surface temperatures above freezing despite receiving no starlight whatsoever. The hydrogen would need to be thick enough to create a powerful greenhouse effect, warming the surface through pressure and the gas's infrared absorption properties. Such planets might possess liquid water on their surfaces, sheltered beneath dense hydrogen skies. Even more speculative is the possibility of rogue planets retaining large moons. If a planet is ejected from its solar system but manages to keep one or more substantial moons, tidal interactions between the planet and its satellites could generate additional heat. This tidal heating, similar to what keeps Europa's ocean liquid, would supplement the planet's internal heat sources. A rogue planet with a large moon might experience ongoing volcanic activity, possibly even more vigorous than it would have experienced while orbiting a star. The tidal forces would flex and squeeze both bodies, converting orbital energy into heat through friction in their interiors. The journey of a rogue planet through the galaxy is one of profound solitude, yet also of constant, subtle interaction with its cosmic environment. When first ejected from its home system, a rogue planet travels at high velocity, typically tens of kilometers per second. To put this in perspective, that's fast enough to cross the distance from Earth to the Moon in just a few hours. Yet even at these speeds, the distances between stars are so vast that a rogue planet might travel for millions of years before passing anywhere near another stellar system. As it travels, the rogue planet encounters the interstellar medium, the thin soup of gas and dust that fills the space between stars. This medium is extraordinarily tenuous, with densities averaging around 1 atom per cubic centimeter, compared to Earth's atmosphere, which contains about 10 to the 19th atoms per cubic centimeter. Despite this extreme thinness, over astronomical distances and timescales, interaction with the interstellar medium can have measurable effects. The planet essentially experiences a very gentle headwind, with individual atoms striking its surface or atmosphere at high relative velocities. For planets with residual atmospheres, this constant bombardment could slowly erode the outer layers, stripping away the lightest gases over billions of years. Cosmic rays, high-energy particles accelerating through space, constantly bombard the rogue planet's surface. Without a parent star's magnetic field to provide some shielding, and depending on whether the planet maintains its own magnetic field, these particles would rain down continuously. For a planet with a thick ice layer, this radiation would penetrate the upper meters of ice, breaking molecular bonds and creating interesting chemistry. Studies of radiation chemistry in ice, relevant to understanding similar processes on Europa and other icy moons, show that radiation can produce hydrogen peroxide, oxygen, and various organic compounds. A rogue planet's ice shell would become a vast laboratory for this radiation-driven chemistry, accumulating complex molecules over millions of years. The galaxy itself is not a uniform environment. Rogue planets would pass through different types of regions during their wandering. Some might drift through the galactic plane, where dust and gas are more concentrated, while others might arc through the less dense galactic halo. Passing through dense molecular clouds, regions where new stars are forming, would temporarily increase the planet's interaction with surrounding material. The planet might accumulate new layers of frost as it sweeps through the cloud, collecting molecules like water, methane, and carbon dioxide onto its surface. These encounters might even provide enough material to slightly replenish a depleted atmosphere, though most accumulated gases would quickly freeze. Occasionally, perhaps once every few 100 million years, a rogue planet might pass through the outskirts of another solar system. These encounters would be brief, lasting perhaps thousands of years as the planet swings through the outer reaches where comets typically orbit. Such a passage would have minimal effect on the rogue planet itself, but it might disturb the comets of the system it's passing through, potentially sending some of them cascading inward toward the system's planets. From the perspective of any inhabitants of that system, the rogue planet would appear as a dark visitor, detectable only by its gravitational effects, moving silently through their sky before disappearing back into the void. Over truly vast timescales, spanning billions of years, the rogue planet's orbit around the galactic center evolves. Just as planets orbit stars, stars orbit the galaxy center, and rogue planets follow their own galactic orbits. These orbits gradually change due to gravitational interactions with passing stars and giant molecular clouds, slowly randomizing the planet's trajectory through the galaxy. A planet ejected from a system in the galactic disk might eventually find itself in a highly elliptical orbit that takes it far above and below the disk, providing a perspective on the galaxy that no planet orbiting a star could ever experience. The sheer number of rogue planets represents one of the most startling revelations in modern astronomy. Early estimates based on microlensing surveys suggested these worlds might be relatively rare curiosities, perhaps numbering in the millions galaxy-wide. But as detection techniques improved and theoretical models became more sophisticated, astronomers realized the true population could be staggering. Current estimates, based on the frequency of microlensing events and simulations of planetary system dynamics, suggest there could be 1 to 2 rogue planets for every star in the Milky Way. With our galaxy containing between 100 billion and 400 billion stars, this implies there might be hundreds of billions of rogue planets drifting through the darkness. Some models push these numbers even higher. Simulations of planetary system formation published in the monthly notices of the Royal Astronomical Society indicate that ejection events might be the norm rather than the exception during the chaotic, early evolution of multi-planet systems. These simulations show that for every planet that remains in a stable orbit, 1 or more siblings might be ejected during the system's first 100 million years. If this holds true across the galaxy, rogue planets could outnumber bound planets by a significant margin, making them perhaps the most common planetary bodies in existence. The implications are profound. If we imagine taking a census of all planet-sized bodies in the Milky Way, we might find that the majority exist not in the warm, illuminated zones around stars, but in the cold darkness between them. The typical planet in our galaxy might be a frozen wanderer, not a world basking in stellar light. This realization shifts our perspective on what constitutes a normal planetary existence. The planets of our solar system, stably orbiting our sun for billions of years, might represent the fortunate minority. This population of wanderers also affects our understanding of how matter is distributed throughout the galaxy. Rogue planets contribute to the overall mass budget, though their contribution remains small compared to stars and dark matter. More significantly, they represent a previously unaccounted for repository of heavy elements. When stars form, they're composed primarily of hydrogen and helium. The heavier elements, everything from carbon to uranium, are created in stellar interiors and supernova explosions, then incorporated into planets during system formation. Rogue planets carry these processed elements with them as they wander, slowly redistributing enriched material through the galaxy in ways we're only beginning to appreciate. There's also the question of what happens to these planets over the galaxy's lifetime. Our galaxy is approximately 13.6 billion years old. The oldest rogue planets might have been wandering for more than 10 billion years, ejected from the first generation of planetary systems that formed when the galaxy was young. These ancient rogues would have traveled immense distances, potentially crossing the galaxy multiple times, witnessing the births and deaths of countless stars. Others are newly minted, ejected just yesterday in cosmic terms, still cooling from the heat of their formation and recent ejection. As our galaxy eventually collides and merges with the Andromeda Galaxy in about 4 billion years, the populations of rogue planets from both galaxies will intermix. Some rogues might even find new homes, captured by stars during the complex gravitational dance of the merger. A wanderer that has drifted alone through the darkness for billions of years might suddenly find itself pulled into orbit around a new sun, beginning a second chapter in its existence as a bound planet once again. The study of rogue planets challenges us to expand our definition of what a planet can be and where planets can exist. These worlds demonstrate that planets are not inextricably tied to stars, that they can exist independently as free agents navigating the galaxy. They remind us that the universe contains multitudes we're only beginning to discover, that between the bright points of light we see in the night sky drift countless dark worlds, each with its own story of formation, ejection, and endless journey through the cosmic dark. And on that note, we come to the end of our exploration of rogue planets, those silent wanderers drifting between the stars. We've journeyed from their violent ejections and lonely births, through the frozen darkness of their surfaces and the potential warmth beneath, to their vast numbers scattered throughout our galaxy. These worlds remind us that the universe is far stranger and more diverse than we ever imagined, filled with places and phenomena that challenge our assumptions about how planets exist and where we might find them. We begin our cosmic calendar at midnight on January 1st. At this moment, the universe explodes into existence in what we call the Big Bang. But this is not an explosion in space. Rather, it is the expansion of space itself. In the first trillionth of a trillionth of a trillionth of a second, the universe undergoes inflation, expanding faster than the speed of light. Think of it like a balloon being inflated, except the balloon is all of space and time, and it grows from smaller than an atom to larger than a galaxy in an instant so brief that no clock could measure it. By 1 second after midnight, the universe has cooled enough for the first particles to form. Quarks bind together to create protons and neutrons. The temperature is still an incomprehensible 10 billion degrees, far hotter than the core of any star. If you could somehow observe the universe at this moment, you would see nothing but a dense, hot fog of fundamental particles and radiation. There is no structure, no atoms, nothing that would be recognizable to us. 3 minutes into January 1st, nuclear fusion begins throughout the entire universe. Protons and neutrons combine to form the first atomic nuclei, primarily hydrogen and helium. This is Big Bang nucleosynthesis, and it creates the raw materials that will eventually build everything we see. However, these are not yet complete atoms. The universe remains too hot for electrons to attach to these nuclei. The cosmos is still opaque, a glowing plasma where light cannot travel freely. For the next 380,000 years, roughly 2 weeks on our cosmic calendar, the universe continues to expand and cool. Nothing particularly dramatic happens during this period. The temperature gradually drops, and space keeps stretching. Then, around January 14th, something remarkable occurs. The universe has cooled to about 3,000 degrees, cool enough for electrons to combine with atomic nuclei and form the first complete atoms. This moment is called recombination, though that name is misleading since these electrons and nuclei were never combined before. When recombination occurs, the universe suddenly becomes transparent. Light can finally travel freely through space without being scattered by free electrons. The photons released at this moment will travel for billions of years, eventually reaching Earth as the cosmic microwave background radiation. This radiation is the oldest light in the universe, a baby picture of the cosmos when it was just 380,000 years old. But the universe of mid-January is still a dark place. There are no stars yet, no galaxies, no structure. Only vast clouds of hydrogen and helium gas drifting through expanding space. The universe has entered what cosmologists call the cosmic dark ages, a period that will last for several more weeks on our calendar. During this time, gravity slowly pulls matter together. Small variations in density, tiny wrinkles in the fabric of space left over from inflation, become the seeds of future galaxies. These density variations act like gravitational wells, drawing in surrounding gas. Slowly, imperceptibly, structure begins to emerge from the primordial chaos. Around late January, approximately 100 million years after the Big Bang, the Dark Ages begin to end. In the densest regions of space, where gravity has pulled together enough hydrogen gas, pressure and temperature rise to critical levels. The first stars ignite. These are nothing like our sun. The earliest stars are massive, perhaps 100 times more massive than our sun, burning blue and white hot. Astronomers call them population 3 stars, though none have ever been directly observed since they existed so long ago. These ancient giants burn through their fuel quickly, perhaps lasting only a few million years before exploding as supernovae. These first stars are crucially important because they create the first heavy elements. Inside their cores, nuclear fusion forges carbon, oxygen, nitrogen, and other elements beyond hydrogen and helium. When they explode, they scatter these elements into space, enriching the surrounding gas clouds. This is the origin of the chemical diversity we see today. Every atom of carbon in your body, every oxygen molecule you breathe, was created inside a star. We are, quite literally, made of stardust, though that stardust had to be created first by these ancient stellar furnaces. By early February, the first galaxies begin to take shape. These are small, irregular clumps of stars, nothing like the grand spiral galaxies we see today. Think of them as building blocks. Over time, these small galaxies will merge and combine, growing larger through cosmic collisions. Gravity acts as the architect, pulling structures together on ever larger scales. The universe is becoming a web, with galaxies forming along filaments of dark matter, divided by vast empty voids. Our own Milky Way galaxy begins to form around mid-February, though it looks very different from its current appearance. It starts as several smaller galaxies that gradually merge together. The process is violent and chaotic. Stars are flung in all directions. Some are ejected into intergalactic space, becoming lonely wanderers. Others are drawn toward the center, where a supermassive black hole begins to grow, feeding on gas and stars that venture too close. This black hole now contains the mass of 4 million suns. Throughout February and March, galaxy formation continues at a rapid pace. The universe is a bustling place, filled with star formation and galaxy collisions. Quasars appear, which are supermassive black holes at the centers of galaxies actively feeding on tremendous amounts of matter. These quasars shine brighter than entire galaxies, visible across vast cosmic distances. They represent a phase in galaxy evolution, a youth when central black holes grew quickly by consuming everything around them. Around early March, the first spiral galaxies begin to appear. The chaotic, irregular galaxies of earlier times start to settle into rotating disks. Conservation of angular momentum, the same principle that causes a spinning ice skater to rotate faster when pulling in their arms, shapes these galaxies into flattened spirals. Gas clouds orbit the galactic center, periodically collapsing to form new generations of stars in the spiral arms. The universe is beginning to look more familiar, though we still would not recognize most of it. By the end of March, the universe is about 3 billion years old. Galaxies continue to grow and evolve. The rate of star formation across the cosmos reaches its peak. More stars are being born now than at any other time in cosmic history. However, this golden age of star formation will not last forever. As the universe continues to expand, the density of matter decreases. Galaxies spread farther apart. The rate of galaxy collisions and mergers begins to slow. The universe is gradually settling down, though it remains far more active than it is today. Dark matter plays a crucial role in all of this, though we cannot see it directly. This mysterious substance, which does not emit or absorb light, makes up about 85% of all matter in the universe. It provides the gravitational scaffolding that allows galaxies to form and hold together. Without dark matter, galaxies would spin so fast that they would tear themselves apart. Computer simulations show that the visible universe we see is just the tip of the iceberg, floating within vast halos of invisible dark matter. The nature of dark matter remains one of the biggest mysteries in physics, though its gravitational effects are undeniable. We now skip ahead to early September on our cosmic calendar. The universe is now 9 billion years old. Most galaxies have formed, and the frantic pace of the early cosmos has slowed considerably. The Milky Way has grown into a grand spiral galaxy containing hundreds of billions of stars. In one of the outer spiral arms, about 26,000 light years from the galactic center, something important is about to happen. A large cloud of gas and dust, called a molecular cloud, drifts through this region of space. Molecular clouds are the wombs where stars are born. This particular cloud contains the remnants of previous generations of stars, enriched with heavy elements from ancient supernovae. Something disturbs this cloud, perhaps a shock wave from a nearby exploding star. The disturbance causes the cloud to collapse under its own gravity. As it collapses, it begins to spin faster, just like that ice skater we mentioned earlier. On September 2nd, Approximately 4.6 billion years ago, the center of this collapsing cloud becomes hot and dense enough for nuclear fusion to begin. Our sun is born. But the sun is not alone. Surrounding it is a swirling disk of leftover gas and dust, the protoplanetary disk. This disk is where the planets will form. Think of it like a cosmic pizza dough spinning in space, with our newborn sun sitting at the center. In the inner regions of this disk, close to the hot young sun, temperatures are too high for volatile substances like water ice to exist. Only rocky materials and metals can remain solid. Tiny dust grains begin to stick together through a process called accretion. These grains grow into pebbles, pebbles into boulders, boulders into planetesimals the size of asteroids. Eventually, these planetesimals collide and merge to form planetary embryos. The process is violent. Impacts are constant. Some collisions destroy both bodies. Others result in mergers, building ever larger protoplanets. By mid-September, the inner rocky planets are taking shape. Mercury, Venus, Earth, and Mars form from the rocky and metallic materials that could withstand the heat near the sun. Meanwhile, farther out in the colder regions of the disk beyond what we call the frost line, water and other volatiles can freeze solid. This gives the outer planets much more material to work with. Jupiter forms first, growing massive enough to dominate the outer solar system. Saturn, Uranus, and Neptune follow. These gas and ice giants capture thick atmospheres of hydrogen and helium from the surrounding disk. Earth at this point is still a hellish place. It is constantly bombarded by asteroids and planetesimals. The surface is molten, an ocean of liquid rock glowing red hot. Around September 10th, about 4.5 billion years ago, Earth suffers its most catastrophic collision. A Mars-sized body called Theia slams into the young Earth at an oblique angle. The impact is so violent that it vaporizes Theia and liquefies Earth's surface. Debris from the collision is thrown into orbit around Earth. This debris gradually coalesces to form our moon. The moon starts out much closer to Earth than it is today, appearing enormous in the sky. The debris disk that formed it is so hot that it glows, creating a luminous ring around Earth. Over millions of years, this material gradually clumps together. The moon begins as a molten ball itself, slowly cooling and solidifying. Its formation has profound effects on Earth. The moon stabilizes Earth's axial tilt, giving us relatively stable seasons. Its gravitational pull creates tides, which may have played a role in the eventual emergence of life. Through late September, the solar system continues to settle. Jupiter's gravity acts like a cosmic vacuum cleaner, either ejecting small bodies into the outer solar system or capturing them. Many of the asteroids that remain in the asteroid belt between Mars and Jupiter are prevented from forming a planet by Jupiter's disruptive gravitational influence. The young sun goes through a phase called the T-Tauri phase, during which it produces powerful stellar winds that blow away most of the remaining gas in the protoplanetary disk. The era of planet formation is largely over, though impacts and collisions will continue for hundreds of millions of years. As September transitions into October, Earth begins to cool. The bombardment of asteroids and comets continues but gradually decreases in intensity. Water vapor in the atmosphere condenses and falls as rain. It rains for millions of years, filling the basins and creating the first oceans. By late September, around 4 billion years ago, Earth has liquid water on its surface. This is a crucial development because water is essential for life as we know it. The early Earth atmosphere is nothing like today's. It contains no oxygen. Instead, it is rich in nitrogen, carbon dioxide, methane, and water vapor. Volcanic activity is intense, constantly releasing gases from Earth's interior. Lightning storms crackle across the sky. The sun is actually dimmer than it is today, about 30% less luminous, yet Earth remains warm enough for liquid water due to the greenhouse effect from its thick atmosphere. Somewhere in the early oceans, perhaps around late September or early October on our calendar, something extraordinary happens. The exact date is uncertain, and scientists continue to debate the details, but the earliest evidence suggests that life emerges on Earth by about 3.8 to 4 billion years ago. How this happens remains one of science's greatest questions. Perhaps it begins near hydrothermal vents on the ocean floor, where hot mineral-rich water provides energy and chemical building blocks. Perhaps it starts in shallow tidal pools where cycles of wetting and drying concentrate organic molecules. Or perhaps the ingredients for life arrive from space aboard comets and asteroids. The first biological forms are simple single-celled organisms similar to modern bacteria. They are prokaryotes, cells without nuclei or other internal compartments. These early microbes are chemotrophs, deriving energy from chemical reactions rather than sunlight. They metabolize the chemicals available in their environment, transforming the planet through their activities. Biology at this stage is entirely microscopic and confined to the oceans. The land remains barren, devoid of any presence of organisms. Around early October, perhaps 3.5 billion years ago, photosynthesis evolves. Cyanobacteria develop the ability to capture energy from sunlight and use it to convert carbon dioxide and water into sugars and oxygen. This is one of the most important innovations in the history of biology. However, the oxygen produced by these early photosynthesizers does not immediately accumulate in the atmosphere. Instead, it reacts with dissolved iron in the oceans, causing the iron to precipitate out and settle to the ocean floor. These ancient deposits, called banded iron formations, can still be found today in rocks billions of years old. For hundreds of millions of years, photosynthetic bacteria multiply and spread through the oceans, slowly pumping out oxygen. Around November 15th, roughly 2.4 billion years ago, something dramatic occurs. The oceans become saturated with oxygen. The dissolved iron has all precipitated out. Suddenly, oxygen begins to accumulate in the atmosphere. This is the Great Oxygenation Event, and it transforms Earth completely. The atmosphere changes from a reducing to an oxidizing environment. For many of the anaerobic organisms that evolved in the oxygen-free world, this is a catastrophe. Oxygen is toxic to them. Some go extinct. Others retreat to oxygen-free refuges deep underground or in oxygen-poor waters where they persist to this day. But the Great Oxygenation Event also creates opportunities. Oxygen enables more efficient forms of metabolism. Aerobic respiration, which uses oxygen to break down food molecules, yields far more energy than anaerobic processes. Complex biology requires this energy boost. Around late November, perhaps 2 billion years ago, another crucial innovation occurs. Some cells begin to engulf other cells without digesting them. Instead, they form a symbiotic relationship. The engulfed cells become mitochondria, the powerhouses of the cell. This is the origin of eukaryotic cells, cells with nuclei and internal compartments. All complex organisms, including plants, animals, and fungi, descend from these early eukaryotes. This process of one organism incorporating another is called endosymbiosis. For most of November and into December, biology remains microscopic. Eukaryotic cells diversify into various forms, but they do not become much larger or more complex. The reasons for this delay are unclear. Perhaps environmental conditions were not yet suitable. Perhaps certain genetic innovations had not yet evolved. Whatever the reason, Earth's oceans are filled with single-celled organisms for billions of years. Then, around December 14th, approximately 600 million years ago, something changes. This is when the first animals appear in the fossil evidence. The Ediacaran fauna, named after the Ediacara Hills in Australia where they were first discovered, are strange soft-bodied creatures unlike anything alive today. Some look like quilted mattresses lying on the seafloor. Others resemble fronds or discs. They are multicellular organisms, among the earliest animals, though their exact relationships to modern animal groups remain debated. Most are immobile, absorbing nutrients directly from the water or hosting photosynthetic microbes within their tissues. Then, around December 17th, roughly 540 million years ago, the Cambrian explosion begins. In a relatively brief period, perhaps 20 million years, most major animal groups appear in the fossil evidence. Suddenly, the oceans are filled with creatures that have shells, jointed legs, eyes, and complex body plans. Trilobites scuttle across the seafloor. Predators like Anomalocaris hunt smaller prey. This diversification is so rapid and dramatic that it puzzled Charles Darwin himself. Why did complex animal biology appear so suddenly after billions of years of single-celled existence? Several factors likely contributed to the Cambrian explosion. Oxygen levels in the atmosphere and oceans reached a threshold that could support larger, more active animals. The evolution of predation created an evolutionary arms race, with prey evolving defenses like shells and predators evolving tools to overcome those defenses. Genetic innovations, particularly the evolution of Hox genes that control body plan development, gave evolution new building blocks to work with. Whatever the exact combination of causes, the result is clear. By the end of December 17th, the oceans are teeming with animal biology. Plants and animals colonized the land starting around December 21st, about 470 million years ago. This is another major transition in Earth's history. The land has been barren rock and soil for billions of years. The first colonizers are plants, probably similar to modern mosses and liverworts. They face enormous challenges. On land, there is no water to provide buoyancy and support. Organisms must deal with gravity, drying out, and intense ultraviolet radiation from the sun. Plants evolve roots to anchor themselves and absorb water, vascular tissues to transport water and nutrients, and protective coatings to prevent water loss. Arthropods follow plants onto land. Millipedes, centipedes, and early insects find new opportunities in this terrestrial realm. They feed on the plants and detritus, establishing the first land-based food chains. Around December 22nd, vertebrates emerge from the water. The first tetrapods, four-legged vertebrates, are fishy creatures that retain many aquatic features like gills, but they have weight-bearing limbs and can breathe air. Tiktaalik, discovered in Arctic Canada in 2004, is a famous transitional fossil from this period, showing features intermediate between fish and land-dwelling vertebrates. By December 23rd, about 360 million years ago, forests cover the land. Giant ferns, club mosses, and horsetails grow to enormous sizes. Some reach heights of 30 meters or more. Amphibians diversify and spread through these forests. The first reptiles appear, distinguished by their scaly skin and hard-shelled eggs that can survive away from water. These amniotic eggs are a key innovation, freeing reptiles from the need to return to water to reproduce. The late Paleozoic era, around December 24th, sees the supercontinent Pangaea form as Earth's landmasses collide and merge. This has profound effects on climate and evolution. At the end of the Permian period, around December 26th, the largest mass extinction in Earth's history occurs. The Permian-Triassic extinction, often called the Great Dying, wipes out roughly 90% of marine species and 70% of terrestrial vertebrate species. The causes are debated but likely include massive volcanic eruptions in what is now Siberia, which released enormous amounts of carbon dioxide and toxic gases, triggering rapid climate change and ocean acidification. Biology recovers from the Great Dying, though it takes millions of years. By December 27th, about 230 million years ago, the Mesozoic era is underway. This is the age of dinosaurs. The first dinosaurs are relatively small, bipedal creatures. But over time, they diversify into an astonishing array of forms. Some remain small and swift. Others evolve into the largest land animals ever to walk the earth. Sauropods like Argentinosaurus may have weighed up to 100 tons, as much as 15 large elephants. During the Jurassic period, around December 28th, dinosaurs dominate terrestrial ecosystems. Meanwhile, other reptile groups take to the seas and skies. Ichthyosaurs and plesiosaurs patrol the oceans. Pterosaurs, the first vertebrates to achieve powered flight, soar through the skies. The first birds appear during this time, evolving from small feathered dinosaurs. Archaeopteryx, discovered in Germany in 1861, is perhaps the most famous transitional fossil, showing features of both dinosaurs and birds. Mammals also appear during the Mesozoic, but they remain small and relatively inconspicuous. The earliest mammals evolve around the same time as the first dinosaurs, but in a world dominated by reptiles, mammals remain mostly small, nocturnal creatures. Some resemble modern shrews, others are more like rodents. They occupy ecological niches that the larger dinosaurs ignore, feeding on insects and other small prey. Their small size and nocturnal habits may have been adaptations to avoid competing with or being eaten by dinosaurs. The Mesozoic era comes to an abrupt end on December 26th at about 2:30 p.m., 66 million years ago. A 10-kilometer wide asteroid strikes Earth near what is now the Yucatan Peninsula in Mexico. The impact releases energy equivalent to billions of nuclear bombs. A crater 180 kilometers wide is blasted into the Earth. Tsunamis race across the oceans. The impact throws so much dust and debris into the atmosphere that sunlight is blocked for months or years. Temperatures plummet. Photosynthesis shuts down. Food chains collapse. This is the Cretaceous-Paleogene extinction event, which wipes out the non-avian dinosaurs along with about 75% of all species on Earth. The pterosaurs vanish. The large marine reptiles disappear. But some groups survive. Birds, the descendants of small feathered dinosaurs, make it through. Mammals survive. Crocodiles and turtles endure. The survivors inherit a devastated but recovering planet. Over the following millions of years, they will diversify to fill the ecological niches left empty by the extinct dinosaurs. Mammals undergo an explosive radiation in the aftermath of the extinction. Without the dinosaurs to compete with or flee from, mammals grow larger and more diverse. By December 27th, about 50 million years ago, most modern mammal groups have appeared. Whales evolved from land-dwelling ancestors and returned to the sea. Bats take to the air. Primates, the group that will eventually include humans, appear in fossil evidence as small tree-dwelling creatures with forward-facing eyes and grasping hands. Around December 30th at about 6 a.m., roughly 7 million years ago, the lineage that will lead to modern humans splits from the lineage that leads to chimpanzees and bonobos, our closest surviving relatives. The early members of the human lineage are called hominins. They are still quite ape-like, but they have begun to evolve some distinctive features. Most notably, they are becoming bipedal, walking upright on two legs. The reasons for this transition are debated. Perhaps it freed their hands for carrying food or tools. Perhaps it was more energy efficient for traveling long distances in the open savanna environments where many early hominins dwelt. Perhaps it helped them spot predators or prey from a greater distance. Whatever the reason, bipedalism becomes a defining feature of our lineage. As we approach the end of December, hominid evolution accelerates. Multiple species of hominins coexist in Africa, each with slightly different adaptations. Australopithecines, like the famous Lucy fossil discovered in Ethiopia, walk upright but still have relatively small brains. Around December 31st at about 9 a.m., 2.6 million years ago, the first stone tools appear in archaeological evidence. These are simple but effective, made by striking one rock against another to create sharp flakes. Tool use marks the beginning of what we call the Paleolithic or Old Stone Age. The genus Homo, our own genus, appears around December 31st at about 10:30 a.m., roughly 2.5 million years ago. Early Homo species have larger brains than the Australopithecines and show signs of more sophisticated tool use. Homo habilis, or handyman, is one of the earliest members of our genus. These early humans are still confined to Africa, but they are beginning to develop the characteristics that will allow their descendants to spread across the globe. Around December 31st at about 2 p.m., 1.8 million years ago, Homo erectus appears. These humans are taller and more robust than earlier species, with even larger brains. Crucially, they are the first hominins to leave Africa. Fossils of Homo erectus have been found in Georgia, China, and Indonesia. They persist for over 1 million years, an impressive run by any measure. Evidence suggests that Homo erectus may have been the first hominin to control fire, a technology that would transform human evolution by providing warmth, protection, and the ability to cook food. As the afternoon of December 31st progresses, several other human species appear. The Neanderthals, Homo neanderthalensis, evolve in Europe and Western Asia around 11 p.m., roughly 400,000 years ago. They are powerfully built, adapted to the cold climates of Ice Age Europe. They have large brains, actually slightly larger on average than modern humans. They make sophisticated tools, bury their dead, and create simple ornaments and cave art. For many years, Neanderthals were portrayed as brutish and primitive, but modern research reveals them as intelligent, capable humans who survived in harsh environments for hundreds of thousands of years. Our own species, Homo sapiens, appears in Africa around 11:40 p.m. on December 31st, roughly 300,000 years ago. The oldest known fossils of anatomically modern humans come from Jebel Irhoud in Morocco, dated to about 315,000 years ago. Early Homo sapiens look much like people today, though there is considerable variation in skull shape and other features. For much of their early history, Homo sapiens remain in Africa, gradually developing more sophisticated tools and behaviors. Around 11:56 p.m., about 100,000 years ago, some groups of Homo sapiens began to migrate out of Africa. They spread into the Middle East and eventually reach every corner of the globe except Antarctica. As they spread, they encounter other human species that had left Africa earlier. In Europe and Western Asia, they meet Neanderthals. In Asia, they encounter the Denisovans, another human species known primarily from fragmentary fossils and DNA evidence. These meetings sometimes result in interbreeding. Most people alive today who have ancestry outside Africa carry small amounts of Neanderthal DNA in their genomes, typically 1 to 2%. Some populations also carry Denisovan DNA. By 11:58 p.m., about 50,000 years ago, human culture undergoes what some call the Upper Paleolithic Revolution. There is an explosion of sophisticated tool-making, art, and symbolic behavior. People create cave paintings like those at Lascaux in France and Altamira in Spain. They carve figurines from ivory and stone. They make jewelry from shells and teeth. They develop elaborate burial practices. Musical instruments appear in archaeological evidence. Whether this represents a true revolution or simply better preservation of evidence from this period is debated, but there is no question that human culture becomes more complex and varied. The last ice age reaches its peak around 11:58 and 30 seconds p.m., about 20,000 years ago. Massive ice sheets cover much of North America and Europe. Sea levels drop by over 100 meters as water is locked up in glaciers. Land bridges appear, connecting regions that are today underwater. Humans cross from Siberia to Alaska over the Bering Land Bridge, eventually spreading throughout the Americas. Australia had already been reached much earlier, requiring sea crossings even when sea levels were lower. Around 11:59 and 20 seconds p.m., about 12,000 years ago, the last ice age ends. The climate warms rapidly. The great ice sheets retreat. Sea levels rise, flooding coastal areas and severing land bridges. In the Middle East, at about 11:59 and 30 seconds, roughly 11,000 years ago, agriculture begins. People start deliberately planting and harvesting crops like wheat and barley. They domesticate animals like sheep, goats, and cattle. This is the Neolithic Revolution, and it fundamentally transforms human society. Agriculture allows for larger, more settled populations. Villages grow into towns and eventually cities. Social structures become more complex. Specialization of labor emerges, with some people farming, others making tools or pottery, still others becoming priests or rulers. Writing is invented in Mesopotamia around 11:59 and 52 seconds p.m., roughly 5,000 years ago. The historical period begins as humans start keeping written accounts of events. In the final seconds of December 31st, human civilization develops at an extraordinary pace. The pyramids of Egypt are built at 11:59 and 53 seconds, about 4,600 years ago. The classical civilizations of Greece and Rome flourish around 11:59 and 57 seconds, roughly 2,000 years ago. The Middle Ages, the Renaissance, the Age of Exploration, the Industrial Revolution, all of these occur in the final second of the cosmic calendar. The entire span of human history and writing, everything from the first cuneiform tablets to the present day, occupies only the last 10 seconds of the cosmic year. Your grandparents were born about 0.03 seconds ago. The Apollo moon landings occurred 0.001 seconds ago. On this scale, an individual human lifetime is briefer than a blink of an eye, less than a fifth of a second in a year spanning 13.8 billion years. Yet in this vanishingly brief moment, humanity has achieved remarkable things. We have decoded the structure of DNA, split the atom, sent probes to the edge of the solar system and beyond. We have looked back through time using telescopes and discovered the story of the cosmic calendar itself. We have transformed the planet, for better and worse, in ways that no other species has. We have created art, music, literature, philosophy, and science. We have pondered our place in the cosmos and attempted to understand the vast scales of time and space that dwarf us. Standing here at the very end of the cosmic year, we can look back across the entire sweep of cosmic history and marvel at the journey that brought us here. From the first fraction of a second after the Big Bang to the formation of atoms, from the birth of stars and galaxies to the formation of our solar system, from the emergence of biology in Earth's oceans to the rise of consciousness and civilization, each step built upon what came before. We are not outside this story looking in. We are part of it, made from the same atoms forged in ancient stars, governed by the same physical laws that shaped the cosmos. And on that note, we reach the end of our journey through the cosmic calendar. 13.8 billion years of history, squeezed into a single year, reveals both the immensity of cosmic time and the remarkable brevity of the human moment within it. Nearly 3,000 kilometers beneath the surface where you rest, something extraordinary is happening. Deep in Earth's core, a vast ocean of molten iron and nickel churns in eternal motion, generating the magnetic field that makes life as we know it possible. This process has a name that sounds almost mythological: the geodynamo. To understand the geodynamo, picture Earth as a layered sphere. At the very center lies the inner core, a solid ball of iron and nickel about 759 miles thick. The temperature here rivals the surface of the sun, approximately 6,000 degrees Celsius. But despite this incredible heat, the pressure is so immense that the metal remains solid, squeezed by the weight of the entire planet above it. Surrounding this solid inner core is the outer core, a shell of liquid metal roughly 1,400 miles thick. Here, temperatures range from about 3,800 degrees at the outer edge to 6,000 degrees near the inner core. The iron and nickel in this layer flow like water, driven by heat escaping from the inner core below. This is where the magic happens. As Earth cools over billions of years, heat flows outward from the incredibly hot inner core toward the cooler mantle above. This heat drives convection currents in the liquid outer core, similar to the rolling motion you see when water boils in a pot. Hotter, less dense metal rises from deeper regions. As it reaches the outer parts of the core, it cools slightly, becomes denser, and sinks back down. This creates a continuous cycle of rising and falling currents throughout the outer core. But Earth doesn't just sit still. Our planet spins on its axis once every 24 hours. This rotation adds a twist to the flowing metal through something called the Coriolis effect, the same force that causes hurricanes to spiral. The Coriolis effect organizes the chaotic flows in the outer core into spiraling columns of metal that align roughly parallel to Earth's rotational axis. Now here's where it becomes truly remarkable. The outer core is not just any liquid, it's an excellent electrical conductor. As this conductive metal flows through any existing magnetic field, even a weak one from outside sources like the sun, electrical currents are induced in the metal. These electrical currents then generate their own magnetic field, just as the current flowing through a wire creates magnetism around the wire. This newly created magnetic field affects the flow of the conductive metal, which generates more electrical current, which strengthens the magnetic field, which affects the flow even more. It's a self-sustaining feedback loop, a natural dynamo that has been running for at least 3.5 billion years. The process maintains itself because the energy from Earth's cooling interior constantly drives the convection that keeps the system going. The magnetic field produced by this geodynamo behaves much like a giant bar magnet buried at Earth's center, tilted about 11 degrees from our rotational axis. Field lines emerge from near the geographic South Pole, arc through space, and return to Earth near the geographic North Pole. This is why compass needles point north. They're aligning with these invisible field lines that surround our planet. The geodynamo isn't perfectly stable. The magnetic field wanders and changes strength over time. The magnetic North Pole, first precisely located in 1831, has drifted more than 600 miles since then, and its speed has increased from about 10 miles per year to 34 miles per year. Even more dramatically, the field occasionally reverses completely, with North and South poles switching places. These reversals happen at irregular intervals, averaging several 100,000 years between events. If you could see Earth's magnetic field with your eyes, if those invisible field lines glowed like neon tubes in space, you might expect to see something symmetrical and elegant. Perhaps perfectly nested shells of magnetism encircling the globe, field lines arching gracefully from pole to pole in a tidy, organized pattern. But space is not a vacuum. Our sun sees to that. And the solar wind shapes our magnetic field into something far stranger and more dynamic. The magnetosphere, the region of space where Earth's magnetic field dominates over the interplanetary magnetic field, extends from about 60 kilometers altitude out into space. But its shape is far from spherical. Imagine a teardrop in space, or better yet, imagine the shape of water flowing around a rock in a stream. That's what our magnetosphere looks like, and for precisely that reason, something is flowing around it. On the side facing the sun, the day side of our magnetic shield, constant pressure from the solar particles crushes the magnetosphere inward. The boundary where Earth's magnetic pressure balances the pressure of the solar wind is called the magnetopause. On the day side, this boundary sits at about 6 to 10 Earth radii from our planet's center, roughly 37,000 to 62,000 miles above the surface. That might sound like a lot, but remember, without the solar wind, our magnetic field would extend infinitely outward, growing weaker with distance but never truly ending. The solar wind doesn't just push on the magnetosphere. At a distance of about 56,000 miles on the sunward side, something dramatic happens. The supersonic solar wind encounters our magnetic field and suddenly slows down in a shock wave called the bow shock. It's similar to the shock wave that forms in front of a supersonic jet. Between the bow shock and the magnetopause lies a turbulent region called the magnetosheath, where solar wind plasma has been heated and slowed, but not yet fully deflected around our planet. On the night side, away from the sun, the picture changes dramatically. Here, the solar particles drag Earth's magnetic field lines out into space, stretching them into a vast tail called the magnetotail. This tail extends at least 1,000 Earth radii downstream, perhaps much farther. No one knows exactly where it ends because spacecraft have never reached that far. If Earth's magnetosphere were visible, you'd see field lines streaming away into darkness like hair blown back by an eternal cosmic breeze. The magnetotail has structure within it. It consists of two lobes, northern and southern, separated by a region called the plasma sheet. In the northern lobe, magnetic field lines point toward Earth. In the southern lobe, they point away. These lobes are relatively empty, containing few particles. But between them, in the plasma sheet, the magnetic field weakens and particle density increases. This is where some of the most dynamic processes in the magnetosphere occur, processes that can ultimately produce the aurora. Earth's rotation adds another asymmetry. As our planet turns, it drags the magnetosphere slightly, creating what scientists call dawn-dusk asymmetry. The magnetosphere is somewhat compressed on the side facing the direction of Earth's orbital motion through space. Within this complex structure, different regions have different characteristics. The plasmasphere, beginning at about 60 kilometers altitude and extending to 3 or 4 Earth radii, is a donut-shaped region containing relatively cool, low-energy plasma. This region rotates with Earth. Beyond it, conditions become more dynamic and less tied to our planet's rotation. The whole structure breathes and flexes constantly as the solar particles vary in speed and density. During quiet periods, the magnetosphere expands. When the sun becomes active, hurling plasma and magnetic fields toward us, the magnetosphere can be severely squeezed inward. The boundary can move inward by thousands of miles, and the entire system can enter a storm state with dramatic consequences both in space and on the ground. On the last day of January in 1958, the United States launched its first satellite into space. Explorer 1 was a modest spacecraft, pencil-shaped and about 80 inches long, carrying minimal scientific instruments including a Geiger counter designed by physicist James Van Allen. The satellite's mission was straightforward: measure cosmic rays in space. What it discovered instead was completely unexpected. As Explorer 1 climbed above 900 miles altitude, the Geiger counter began clicking at an astonishing rate, registering radiation levels 1,000 times higher than anyone predicted. Then, as the satellite rose higher still, the clicks suddenly stopped. Scientists were baffled. The instrument appeared to have failed. But it hadn't failed. It had been overwhelmed. The radiation levels were so high that the detector couldn't keep up with the particle counts. Explorer 1 had stumbled into a region of space where Earth's magnetic field traps vast numbers of high-energy particles. These regions, quickly confirmed by additional satellites and named the Van Allen radiation belts, form two enormous donut-shaped zones encircling Earth. The inner belt begins roughly 3,000 kilometers above Earth's surface and is thickest at about 5,000 kilometers altitude. It contains primarily high-energy protons, some with energies reaching hundreds of millions of electron volts. These particles, trapped by Earth's magnetic field, spiral around field lines, bouncing between the magnetic mirror points in the northern and southern hemispheres several times per second. The outer belt lies much farther out, centered around 16,000 to 58,000 kilometers from Earth's surface. This belt consists mainly of high-energy electrons that can reach several million electron volts. Between the two belts lies a relatively empty space, though even this region contains more radiation than you'd want your spacecraft to experience for long. But in 2012, something remarkable happened. NASA launched two identical spacecraft called the Van Allen probes into orbits designed to spend all their time within the radiation belts. Within days of launch, the probes detected something no one expected: a third radiation belt. This temporary belt appeared as a narrow ring between the inner and outer zones and persisted for 4 weeks before merging back into the outer belt. This discovery revealed that our magnetosphere has even more complex structure than scientists had imagined. Where do these trapped particles come from? Two main sources contribute. Solar wind particles manage to enter the magnetosphere through various processes, particularly during magnetic storms. The second source is our own atmosphere. The ionosphere, the ionized upper atmosphere, constantly releases particles upward along magnetic field lines. Once particles enter the magnetosphere, they can become trapped, spiraling around field lines, bouncing between northern and southern hemispheres, and drifting eastward or westward depending on their charge. The radiation belts are not static. They change dramatically during magnetic storms. Sometimes the number of electrons increases by factors of 10 or more within hours. Other times, particles are lost from the belts just as rapidly, scattered into the atmosphere or out into space. The Van Allen probes discovered that electromagnetic waves play a crucial role in these processes. Waves in the lower frequency Whistler mode chorus can accelerate electrons from tens of thousands of electron volts up to 10 million electron volts in just minutes. For satellites and spacecraft traveling through the radiation belts, these particles pose a serious hazard. High-energy electrons can penetrate spacecraft walls and damage sensitive electronics. Protons can cause similar damage. Communications satellites in high geosynchronous orbits sit right at the edge of the outer radiation belt and must be shielded accordingly. The International Space Station orbits well below the belts and benefits from significant protection. Astronauts traveling to the moon must pass through the Van Allen belts quickly to minimize radiation exposure. James Van Allen himself calculated that spacecraft could safely transit through the weaker regions of the belts, and the Apollo missions proved him correct. The Sun is not a calm, steady source of light and heat. Its surface roils with magnetic activity. Massive loops of magnetism arc through the solar atmosphere, sometimes becoming so twisted and stressed that they snap, releasing enormous amounts of energy in explosive events that can affect Earth hundreds of millions of miles away. A solar flare is essentially an enormous explosion on the Sun's surface. X-rays and ultraviolet light from the flare race across space at the speed of light, reaching Earth in just over 8 minutes. These energetic photons slam into Earth's upper atmosphere, heating it and causing it to expand. This expansion increases drag on satellites in low Earth orbit, making them slow down and gradually lose altitude. The radiation also disrupts the ionosphere, that electrically charged layer of the upper atmosphere, degrading or even blocking high-frequency radio communications that bounce signals off the ionosphere. But flares, as disruptive as they can be, are not the magnetosphere's greatest challenge. That honor belongs to coronal mass ejections, or CMEs. A coronal mass ejection is an enormous eruption that hurls billions of tons of plasma and embedded magnetic field from the Sun's outer atmosphere into space. A large CME can blast outward at speeds of 1 to 2 million miles per hour, though many travel more slowly. Unlike the radiation from a flare, which arrives in minutes, a CME takes anywhere from 1 to 3 days to reach Earth, depending on its speed. When a CME reaches our planet, it slams into the magnetosphere like an ocean wave hitting a seawall. The impact depends critically on the orientation of the magnetic field carried within the CME. If that field points southward, opposite to Earth's magnetic field, the interaction is strong and disruptive. The interplanetary magnetic field can actually merge with Earth's field at the magnetopause in a process called magnetic reconnection. This allows solar particles and energy to flow into the magnetosphere much more efficiently than normal. The magnetosphere responds violently to this intrusion. Electric currents surge through space. The magnetotail becomes highly disturbed. Particles are accelerated to high energies and injected deeper into the magnetosphere. The whole system can enter a state called a geomagnetic storm. During such storms, the number of particles in the radiation belts can increase dramatically. Powerful electric currents flow through the ionosphere and can even be induced in the ground below, flowing through electrical transmission infrastructure and potentially damaging transformers and other electrical equipment. The most powerful geomagnetic storm ever documented struck Earth in September of 1859. Known as the Carrington event, after the astronomer who observed the triggering solar flare, This storm induced electrical currents strong enough to shock telegraph operators and set telegraph paper on fire. Auroras were seen as far south as Hawaii and the Caribbean. If a storm of similar magnitude struck today in our electrically dependent civilization, the consequences could be severe. More recently, in March of 1989, a geomagnetic storm caused the collapse of the Hydro-Quebec power grid in Canada. 6 million people lost power for 9 hours. In October of 2003, a series of powerful storms damaged more than a third of NASA's satellites. And in May of 2024, an extreme geomagnetic storm, the strongest in over 20 years, caused power grid irregularities, disrupted satellite operations, and increased atmospheric drag enough to make satellites' orbits change unexpectedly. Space weather forecasting has become a critical activity. Multiple satellites monitor the sun constantly, watching for flares and CMEs. The SOHO satellite and others sit at a special point in space about 1 million miles from Earth toward the sun, where they can detect incoming CMEs and provide warnings with about 15 to 45 minutes of lead time. It's not much time, but it allows satellite operators to switch their spacecraft into safe modes and power grid operators to take protective measures. Imagine standing in the darkness near the Arctic Circle on a clear winter night. The temperature hovers far below freezing, your breath crystallizes in the still air, and the only sound is the quiet crunch of snow beneath your boots. Then, slowly at first, the northern horizon begins to glow. A pale green arc stretches from east to west, hanging perhaps 100 miles above the Earth's surface. As you watch, the arc brightens and begins to move, rippling like a curtain caught in an invisible breeze. More colors appear, purple along the lower edge, red higher up, and the green intensifies until the entire sky seems to be alive with flowing light. This is the Aurora Borealis, the Northern Lights, one of the most spectacular natural phenomena on Earth. Near the South Pole, the same process creates the Aurora Australis, or Southern Lights. Both are visible manifestations of the complex interactions between our magnetosphere and particles from the Sun. The aurora begins with solar particles and geomagnetic activity. When conditions are right, particularly when a coronal mass ejection or high-speed solar stream interacts with Earth's magnetosphere, particles are accelerated down magnetic field lines toward the polar regions. These particles, primarily electrons, rain down into the upper atmosphere at altitudes between about 60 and 250 miles. There they collide with oxygen and nitrogen atoms. The collision excites these atmospheric atoms, bumping their electrons into higher energy states. This excited state is unstable. Within fractions of a second, the electrons drop back to their normal energy levels, and in doing so, they emit light. The color of that light depends on which type of atom was struck and at what altitude the collision occurred. The most common aurora color is a yellowish green, produced by oxygen atoms at altitudes around 100 kilometers. This green light has a wavelength of 558 nanometers, and it appears because excited oxygen takes about 1 second to emit its light. At higher altitudes, above 200 kilometers, oxygen produces a red glow. This red light requires very energetic particles to reach those altitudes, so it typically appears only during intense auroral displays. The red comes from a different transition in the oxygen atom that takes longer, up to 2 minutes, to produce light. Nitrogen produces blue and purple colors. Ionized nitrogen that has lost an electron, creates blue light. Neutral nitrogen produces purple. These colors often appear along the lower edges of auroral curtains where the atmospheric density is slightly higher. The aurora is not just beautiful, it's dynamic. Auroral curtains can move across the sky at walking pace or faster. They develop waves that seem to propagate along their length. During intense magnetic storms, the aurora can cover the entire visible sky with writhing forms and shifting colors. These rapid changes reflect the complex, turbulent physics occurring as particles stream down from the magnetosphere and interact with the atmosphere. Auroras normally occur in oval-shaped regions around the magnetic poles. These auroral ovals typically sit at latitudes of about 65 to 70 degrees. During quiet times, the ovals remain close to the poles, and the aurora is dim. But during geomagnetic storms, the ovals expand toward the equator and the aurora becomes brighter and more active. Powerful storms can push the aurora as far south as the Caribbean or as far north as Europe's Mediterranean coast. There's even evidence that auroras can produce sound. Researchers have detected crackling and popping noises during auroral displays. The sounds may result from static electricity in a temperature inversion layer about 80 meters above the ground, discharging during geomagnetic storms. Whether this sound is common enough to be part of the typical auroral experience remains a subject of ongoing study. To truly appreciate the magnetosphere, consider what Earth would be like without it. Look at Mars, our smaller planetary neighbor. Mars once had liquid water on its surface. River valleys still visible today testify to ancient flowing streams. The planet likely had a thicker atmosphere, perhaps even conditions suitable for life. But Mars is much smaller than Earth, and its interior cooled more quickly. Without sufficient heat to drive convection in its core, the Martian geodynamo shut down. The planet's global magnetic field disappeared. Without a global magnetosphere to shield it, the Martian atmosphere became vulnerable to the solar particles. Over hundreds of millions of years, the sun's constant barrage of charged particles and radiation slowly stripped away the Martian atmosphere. Today, Mars has an atmosphere only about 1% as dense as Earth's. Any liquid water on the surface would immediately boil away into the thin air. The planet is cold, dry, and bathed in harmful radiation. This is the fate Earth might have suffered without its protective magnetic field. The magnetosphere shields us in several critical ways. First, it deflects most of the solar particles around Earth, preventing those fast-moving particles from directly striking our atmosphere. The solar stream carries about 1 to several protons per cubic centimeter, traveling at speeds from 250 to 500 miles per second. This might not sound like much, but integrated over the enormous area of Earth's cross-section, the momentum and energy in the solar stream would be formidable if allowed to impact the atmosphere directly. Second, the magnetosphere protects us from cosmic rays. These high-energy particles, some originating from exploding stars far across the galaxy, carry enormous energies. A single cosmic ray particle can have as much energy as a well-hit baseball, all concentrated in a space smaller than an atom. Many cosmic rays are deflected by the sun's magnetic field, which extends throughout the solar system. But those that penetrate to Earth's vicinity are further deflected by our own magnetosphere. Without this protection, the surface radiation environment would be much harsher, potentially affecting living organisms and certainly complicating life's evolution on our planet. Third, the magnetosphere moderates solar storms. Even a powerful coronal mass ejection, carrying billions of tons of plasma and magnetic field, doesn't simply punch through our magnetic shield. The magnetosphere absorbs the impact, disturbing and compressing, but ultimately containing most of the solar fury. The particles and energy do affect us, creating geomagnetic storms, disrupting communications, and occasionally causing problems for power grids. But these effects are minor compared to what would happen if the plasma hit our atmosphere directly. The magnetosphere has likely been protecting Earth for most of our planet's history. Paleomagnetic evidence, the record of magnetism frozen into ancient rocks, shows that Earth's magnetic field has existed for at least 3.5 billion years. This is almost as long as life has existed on Earth. It's possible, even likely, that the magnetosphere played a crucial role in allowing life to develop and flourish. By maintaining a thick atmosphere and blocking harmful radiation, the magnetic field helped create stable conditions for life's long evolutionary journey. The International Space Station orbits at about 400 kilometers altitude, well within the protective embrace of the magnetosphere. Astronauts there receive radiation doses higher than on Earth's surface, but still quite manageable. But astronauts traveling to the Moon or Mars will venture beyond this protection for extended periods. They'll need spacecraft shielding to protect against solar storms and will have to carefully time their missions to avoid periods of high solar activity. Future Mars colonists will need to construct habitats underground or with substantial shielding to protect against the radiation that constantly bathes the Martian surface. Earth is not unique in having a magnetosphere. Most planets with substantial magnetic fields generate their own protective bubbles, each shaped by the balance between the planet's internal magnetic field and the external pressure of the solar wind, or, for very distant planets, the interstellar medium. Jupiter has the solar system's most powerful magnetosphere. The giant planet's rapid rotation, turning once every 10 hours, and its large metallic hydrogen layer create a magnetic field 14 times stronger than Earth's at its cloud tops. Jupiter's magnetosphere is enormous, extending out to between 3 and 7 million kilometers on the sunward side, depending on solar wind pressure. If you could see Jupiter's magnetosphere from Earth, it would appear several times larger than the full moon in our sky. The Jovian magnetosphere is filled with particles from Io, Jupiter's volcanically active moon. Io spews tons of sulfur and oxygen into space each second, and these atoms become ionized and trapped in Jupiter's magnetic field. As these particles are forced to rotate with Jupiter's magnetic field, they create powerful radiation belts far more intense than Earth's Van Allen belts. These radiation belts are so strong that they would deliver a lethal dose to an unshielded astronaut in just hours. Saturn also has a substantial magnetosphere, though much weaker than Jupiter's and more similar to Earth's in structure. What makes Saturn's magnetosphere particularly interesting is its interaction with the particles from the planet's rings and icy moons. These interactions create fascinating phenomena, including a hexagonal pattern of clouds at Saturn's north pole, apparently driven by processes connected to the magnetosphere. Mercury, the solar system's smallest planet, has a weak magnetic field and a tiny magnetosphere, only about 5% the size of Earth's. Yet Mercury's magnetosphere is remarkably dynamic because the planet sits so close to the Sun. The solar wind pressure at Mercury's distance is about 10 times stronger than at Earth, and the small magnetosphere responds violently to solar activity. Venus, nearly Earth's twin in size and mass, has no significant magnetic field. Its slow rotation, taking 243 Earth days to turn once, apparently prevents the establishment of a self-sustaining geodynamo despite the planet likely having a molten core. Without a magnetosphere, Venus's upper atmosphere is directly exposed to the solar wind. The interaction creates a kind of induced magnetosphere, where the solar wind itself drapes around the planet, but this provides far less protection than a true magnetic field. Mars, as mentioned earlier, lost its global magnetic field long ago. Small patches of magnetism frozen into ancient crust hint that Mars once had a dynamo, but today the planet is essentially unprotected. The solar particles interact directly with the upper Martian atmosphere, slowly stripping it away even now. Beyond our solar system, astronomers have detected magnetic fields around other stars and have begun to investigate exoplanets that might have their own magnetospheres. The presence of a magnetic field could be crucial for a planet's habitability. A rocky planet in the habitable zone of its star, where liquid water could exist on the surface, might still be uninhabitable if it lacks a protective magnetosphere. The star's stellar wind could strip away the atmosphere over time, just as happened to Mars. Some exoplanets might have even more powerful magnetospheres than Earth. Large, rapidly rotating rocky planets or planets closer to their stars might generate very strong fields. On the other hand, planets tidally locked to their stars, keeping one face always toward their sun and rotating very slowly, might fail to generate magnetic fields at all. The study of magnetospheres throughout the universe connects planetary interiors, atmospheric science, and space physics. It reminds us that a planet is not just a sphere of rock or gas, but a complex system where the interior, surface, atmosphere, and surrounding space environment all interact in ways that ultimately determine whether that world could support life. And on that note, as we float here in the darkness thinking about these invisible shields that protect worlds across the cosmos, our own journey through the magnetosphere comes to a close. The concept of a habitable zone, sometimes called the Goldilocks zone, is beautifully simple at its core. Just as the porridge in the fairy tale needed to be neither too hot nor too cold, a planet needs to orbit at just the right distance from its star to maintain liquid water on its surface. Too close, and water boils away into steam. Too far, and it freezes into ice. This narrow band around a star represents the sweet spot where temperatures allow water to remain in its liquid state, at least theoretically. The idea itself dates back to the 1950s and 60s, when astronomers first began seriously considering where life might exist beyond our solar system. Scientists like Su Huang proposed that each star would have its own region where conditions could be suitable for life. The boundaries of this zone depend entirely on how much energy a star radiates. A hotter, brighter star pushes the habitable zone farther out. A cooler, dimmer star brings it much closer in. Think of it like a campfire on a cold night. If you're sitting too close, you'll be uncomfortably hot. Too far away, and you won't feel the warmth at all. There's a perfect distance where you're just comfortable enough. That distance changes depending on how large and hot the fire is burning. A roaring bonfire requires you to sit much farther back than a small campfire to feel that same comfortable warmth. Our own Earth sits comfortably within the Sun's habitable zone, orbiting at about 93 million miles away. This distance gives us an average temperature that keeps our oceans liquid and our atmosphere stable enough to support the incredible diversity of life we see today. Venus, our inner neighbor, orbits too close. Its surface temperature exceeds 800 degrees Fahrenheit, hot enough to melt lead. Mars, our outer neighbor, sits near the edge of the habitable zone where conditions are much colder, though scientists believe it may have had liquid water on its surface billions of years ago when it was warmer. The boundaries of a habitable zone aren't sharp lines, but rather fuzzy regions where conditions gradually transition. Astronomers define the inner edge as the point where a planet would experience a runaway greenhouse effect, causing all water to evaporate into the atmosphere. The outer edge is where carbon dioxide, even at maximum atmospheric pressure, would freeze out of the atmosphere entirely, making it impossible for the greenhouse effect to warm the planet enough to maintain liquid water. These calculations require astronomers to consider many factors. The star's luminosity, or total energy output, is the primary factor. But planetary characteristics matter too. A planet with a thick atmosphere can trap more heat, potentially making it habitable even farther from its star. A planet with no atmosphere at all might be frozen even within what we'd normally consider the habitable zone. The presence of greenhouse gases, reflective clouds, and even the planet's rotation rate all play roles in determining whether liquid water can actually exist. Stars come in an astonishing variety of sizes, temperatures, and brightnesses. Astronomers classify them using a system based on their surface temperature, ranging from the hottest O-type stars, which burn blue and white, through cooler B, A, F, and G types, down to the coolest M-type stars, which glow a dim red. Each type of star creates a different habitable zone, and understanding this diversity is crucial to our search for potentially inhabited worlds beyond our solar system. Our Sun is a G-type star, sometimes called a yellow dwarf, though its light actually appears white when viewed from space. With a surface temperature around 10,000 degrees Fahrenheit, the Sun represents a middle ground in the stellar spectrum. It's neither the hottest nor the coolest, neither the brightest nor the dimmest. This middle position has important implications for Earth's habitability, giving us a stable, long-burning star that will shine steadily for billions of years. At the hotter end of the spectrum, we find the massive, luminous stars that burn through their fuel at incredible rates. An O-type star might shine with the brightness of 1,000,000 suns, flooding space with intense radiation. The habitable zone around such a star would extend incredibly far out, potentially dozens of times Earth's distance from the Sun. However, these brilliant stars are rare and short-lived, burning through their fuel in just a few million years. Life as we know it requires billions of years to evolve, making these stellar giants poor candidates for hosting inhabited worlds, despite their expansive habitable zones. Moving down the scale, we encounter stars more similar to our Sun. F-type stars burn slightly hotter and brighter, pushing their habitable zones somewhat farther out. K-type stars, orange dwarfs, burn cooler and dimmer, pulling their habitable zones closer in. These stars are particularly interesting to astronomers because they're numerous and long-lived. A K-type star might burn steadily for 15 to 30 billion years, far longer than our Sun's 10 billion year lifespan, potentially giving life even more time to arise and flourish. The most common stars in our galaxy are the M-type red dwarfs, small, cool stars that burn their fuel so slowly they could theoretically shine for trillions of years. These dim stars make up roughly 75% of all stars in the Milky Way. Their habitable zones hug very close to the star itself, sometimes closer than Mercury orbits our Sun. This proximity creates unique challenges and opportunities that we'll explore further, but the sheer abundance of these stars makes them prime targets in the search for habitable worlds. If even a small fraction of red dwarfs host habitable planets, the galaxy could be teeming with potential homes for life. Temperature isn't the only factor that matters. Stars also vary in their stability. Young stars, regardless of type, tend to be more active, producing powerful flares and varying in brightness. As stars age and settle into their main sequence, the long stable period where they burn hydrogen into helium, they become more reliable sources of energy. Our Sun is currently in this comfortable middle age, having burned steadily for about 4.5 billion years with roughly 5 billion more to go. The color of a star's light also affects how photosynthesis might work on planets around it. Plants on Earth evolved to harness the Sun's yellow and white light, appearing green because they reflect green wavelengths while absorbing red and blue. On a planet around a red dwarf, plants might appear black to capture as much of the dim red light as possible. Around a hotter blue star, Photosynthetic organisms might take on entirely different colors to optimize for the bluer wavelengths available. Determining where the habitable zone lies around any given star requires sophisticated calculations that account for the intricate dance between stellar radiation and planetary atmospheres. Astronomers have developed mathematical models that take a star's properties and translate them into concrete distances where liquid water could theoretically exist. These calculations have evolved considerably since they were first proposed, becoming more nuanced as our understanding of planetary atmospheres has deepened. The most fundamental input to these calculations is stellar luminosity, the total amount of energy a star radiates per second. Luminosity depends on both the star's size and its surface temperature. A star twice as wide as our Sun, but with the same surface temperature, would have 4 times the surface area and therefore emit 4 times as much light. Temperature has an even more dramatic effect. A star with twice the surface temperature radiates 16 times as much energy per unit of surface area. This fourth power relationship makes temperature the dominant factor in determining a star's brightness. Once astronomers know a star's luminosity, they can calculate the habitable zone using the inverse square law of light. This law states that the intensity of light decreases with the square of the distance from the source. Double your distance from a light source, and you receive 1/4 the light. Triple the distance, and you get 1/9. This mathematical relationship allows scientists to find the distances where a planet would receive just the right amount of starlight to maintain liquid water. For the inner edge of the habitable zone, calculations focus on the runaway greenhouse threshold. At this critical point, incoming stellar radiation becomes so intense that water begins to accumulate in the atmosphere as vapor. Water vapor is itself a greenhouse gas, trapping even more heat. This creates a feedback loop where more heat leads to more water vapor, which traps more heat, which evaporates more water. Eventually, all surface water boils away, and the planet ends up like Venus, with a thick, hot atmosphere and a surface too scorched for any liquid water to remain. The outer edge calculations involve the opposite problem: maximum greenhouse warming. Even with a thick atmosphere full of carbon dioxide and other greenhouse gases, there's a distance beyond which a planet simply can't trap enough heat to prevent water from freezing. At these distances, even the most optimistic atmospheric conditions can't maintain temperatures above the freezing point of water. The planet becomes a frozen world, with any water locked away in ice sheets and glaciers. Modern calculations recognize that these boundaries aren't fixed lines, but probability gradients. Some models define a conservative habitable zone, where we're quite confident liquid water could exist, and an optimistic habitable zone, where special conditions might allow it. The conservative zone is narrower and represents the safest bet for finding habitable conditions. The optimistic zone extends farther in both directions, encompassing planets where habitability is possible but requires more favorable circumstances. Astronomers also consider something called the continuously habitable zone, which accounts for how stars change over time. A star like our Sun gradually brightens as it ages, increasing its luminosity by about 10% every billion years. This means the habitable zone slowly moves outward over time. A planet might start out comfortably within the habitable zone when the star is young, but eventually find itself too close as the star brightens. The continuously habitable zone represents the narrow band where a planet would remain habitable throughout the star's entire main sequence lifetime, potentially billions of years. Red dwarf stars present one of the most intriguing and controversial cases in the search for habitable worlds. These small, cool stars are the runts of the stellar litter, with masses as low as 8% that of our Sun. Their low mass means they burn their hydrogen fuel incredibly slowly, allowing them to shine for potentially hundreds of billions or even trillions of years. Given that our universe is only about 14 billion years old, not a single red dwarf has yet reached the end of its natural lifespan. This longevity makes them attractive targets for finding habitable worlds, but their unique properties also create significant challenges. The habitable zone around a red dwarf sits remarkably close to the star. For a star like Proxima Centauri, the nearest star to our Sun, the habitable zone lies only about 5 million miles from the star, roughly 7% of Earth's distance from the Sun. A planet in this zone would orbit its star much faster than Earth orbits the Sun, potentially completing a full year in just 10 to 20 Earth days. From the planet's surface, the red dwarf would appear much larger in the sky than our Sun does from Earth, glowing a deep red or orange color. This proximity creates a phenomenon called tidal locking, similar to how our Moon always shows the same face to Earth. When a planet orbits very close to its star, gravitational forces cause the planet's rotation to slow until it spins once per orbit, keeping one hemisphere perpetually facing the star and the other in eternal darkness. Imagine a world where one side experiences endless day, growing hotter and hotter, while the other side faces endless night, growing colder and colder. The only comfortable region might be the twilight zone between these extremes, a thin band where the sun hangs perpetually at the horizon. However, recent studies suggest that tidal locking might not be as catastrophic as once thought. If the planet has a thick enough atmosphere, winds could transport heat from the day side to the night side, moderating temperatures across the planet. Computer simulations show that atmospheric circulation patterns could create habitable conditions even on tidally locked worlds. Some models even suggest that the permanent twilight zone could provide stable, tempered conditions more favorable than the constantly changing environment we experience on Earth. Red dwarfs are also prone to dramatic stellar flares, sudden explosions of energy that can temporarily increase the star's brightness by orders of magnitude. These flares release intense ultraviolet and X-ray radiation that could strip away a planet's atmosphere or sterilize its surface. Young red dwarfs are particularly active, producing powerful flares regularly. However, as these stars age and their rotation slows, they generally become more placid. A planet around an old, quiet red dwarf might experience a relatively stable environment despite the star's diminutive size. Another concern involves the type of light red dwarfs emit. These stars produce most of their energy in the infrared part of the spectrum, with relatively little visible light. Photosynthesis as we know it might be challenging under such dim, red illumination. However, life is remarkably adaptable. Some scientists propose that organisms on red dwarf planets might evolve to use the infrared light, or they might gather in large colonies to pool the limited light available, similar to how certain bacteria on Earth function in low-light environments. Despite these challenges, the discovery of planets around red dwarfs has accelerated in recent years. The TRAPPIST-1 system, located about 40 light-years from Earth, contains 7 Earth-sized planets orbiting a cool red dwarf. At least 3 of these planets sit within the star's habitable zone, making this system one of the most promising places to search for life beyond our solar system. Proxima Centauri, our nearest stellar neighbor, hosts at least one planet, Proxima b, that orbits within the habitable zone. These discoveries have transformed red dwarfs from astronomical curiosities into primary targets in the search for inhabited worlds. Stars similar to our Sun represent perhaps the most straightforward case for habitability, simply because we have a working example right in our cosmic backyard. These G-type yellow dwarfs, along with their slightly cooler K-type orange dwarf cousins, create habitable zones that are wide, stable, and located at comfortable distances where tidal locking is unlikely to occur. Understanding these stars helps us appreciate why Earth has remained habitable for billions of years and where we might find similar success stories around other stars. The Sun's habitable zone extends from roughly 93 million miles at its inner edge to about 140 million miles at its outer edge, depending on which calculation method you prefer. Earth orbits at 93 million miles, placing us right near the inner edge of this zone. Venus, at 67 million miles, is too close, while Mars, at 142 million miles, sits right at the outer boundary. This positioning explains much about the three planets' vastly different climates. What makes Sun-like stars particularly promising for life is their stability and longevity. These stars burn through their hydrogen fuel at a moderate rate, maintaining steady output for about 10 billion years. This time span is crucial because life on Earth required roughly 4 billion years to evolve from simple microbes to the diverse biosphere we see today. Stars that burn much faster than the Sun might not provide enough time for similar evolutionary processes to unfold. The spectrum of light from Sun-like stars is also well suited for chemistry and biology. These stars emit significant energy across visible wavelengths, from red through violet, along with ultraviolet and infrared radiation. This broad spectrum provides energy for various chemical reactions and photosynthetic processes. The moderate ultraviolet output is enough to drive important atmospheric chemistry, creating an ozone layer that protects surface life from excessive radiation, but not so much that it would sterilize planetary surfaces. K-type orange dwarfs might actually be even better candidates for hosting life than Sun-like stars. These stars are cooler and dimmer, but they're also more numerous and longer lasting. A typical K-dwarf might shine steadily for 20 to 30 billion years, giving life more than twice as long to arise and evolve compared to planets around Sun-like stars. Their habitable zones are closer in than the Sun's, but not so close that tidal locking becomes inevitable. Planets in these zones would still have distinct days and nights, seasons, and weather patterns similar to what we experience on Earth. Scientists have identified numerous Sun-like stars with planets in their habitable zones. Kepler 452b, for instance, orbits a G-type star about 1,400 light-years away. This planet is about 60% larger than Earth and orbits within its star's habitable zone at a distance similar to Earth's orbit around the Sun. It receives about 10% more stellar energy than Earth does, potentially making it slightly warmer, but still within the range where liquid water could exist on its surface. Another promising system is Kepler 186f, which orbits a cooler star and takes 130 days to complete its orbit. This planet sits near the outer edge of its star's habitable zone and receives about 1/3 the light Earth gets from the Sun. If it has a thick atmosphere with sufficient greenhouse gases, it could maintain liquid water despite the reduced sunlight. These examples demonstrate that habitable zone planets around Sun-like stars aren't merely theoretical but actual worlds we can observe and study. The challenge now is determining whether any of these planets actually harbor life. Current telescopes can detect the planets and measure their sizes and orbits, but determining atmospheric composition and surface conditions requires more sophisticated instruments. Future telescopes will analyze the light passing through these planets' atmospheres as they cross in front of their stars, searching for chemical signatures like oxygen, methane, or other gases that might indicate biological activity. At the opposite end of the stellar spectrum from red dwarfs, we find the massive, brilliant stars that illuminate space with dazzling intensity. These hot stars, particularly A and F types, create habitable zones that extend far from the star, sometimes several times the distance between Earth and the Sun. However, despite their expansive habitable regions, these stellar giants present significant obstacles for the development of life. An A-type star might have twice the mass of our Sun and burn with 4 to 5 times the luminosity. This brightness pushes the habitable zone outward to perhaps twice Earth's distance from the Sun or even farther. F-type stars, slightly cooler than A-types but still hotter than our Sun, create similarly expanded habitable zones. A planet in one of these distant habitable zones would receive the same amount of warmth as Earth does despite orbiting much farther from its star, thanks to the star's greater luminosity. The most significant problem with hot stars is their brief lifespans. An A-type star might shine for only 1 to 2 billion years before exhausting its hydrogen fuel and swelling into a red giant. F-type stars last longer, perhaps 3 to 4 billion years, but this is still short compared to the time life required to evolve on Earth. The first billion years of Earth's history saw only simple single-celled organisms. Multicellular life didn't appear until around 600 million years ago, and intelligent life capable of technology arose even more recently. Hot stars might simply not provide enough time for similar evolutionary processes. Another challenge involves stellar activity and radiation. Hot stars emit substantial amounts of ultraviolet radiation, far more than cooler stars produce. While some ultraviolet light is necessary for certain atmospheric chemistry, too much can be harmful. Excessive ultraviolet radiation can break apart water molecules in a planet's upper atmosphere, allowing hydrogen to escape to space. Over time, this process could strip away a planet's water, leaving it dry and barren even if it starts with abundant oceans. The rapid evolution of hot stars also means their habitable zones move dramatically over time. As these stars age and brighten, the habitable zone shifts outward more quickly than around cooler stars. A planet that begins its existence in the habitable zone might find itself too close to the star within a few 100 million years as the star's output increases. This rapid environmental change would challenge any nascent life trying to establish itself. Despite these difficulties, planets around hot stars aren't completely impossible candidates for life. Some scientists propose that life could arise more quickly than it did on Earth under the right conditions. Additionally, advanced civilizations might colonize these systems, appreciating the brilliant light and abundant energy these stars provide. The expanded habitable zones could even accommodate multiple habitable planets, creating solar systems with several Earth-like worlds orbiting at different distances. Detecting planets around hot stars presents technical challenges. These stars spin rapidly and have fewer surface features than cooler stars, making precise measurements difficult. The brilliant light can also overwhelm the faint signal of planets, making them harder to spot. Nevertheless, astronomers have discovered planets around these stars, and some orbit within the habitable zone. Whether any of these worlds could support life remains an open question. One will need better telescopes and more detailed observations to answer definitively. While stellar properties define the basic boundaries of a habitable zone, planetary characteristics determine whether a world within that zone actually maintains habitable conditions. Two planets orbiting at the same distance from identical stars could have completely different climates depending on their size, composition, atmosphere, and geological activity. Understanding these factors helps astronomers refine their search for truly habitable worlds beyond our solar system. Atmospheric composition plays perhaps the most critical role. Earth's atmosphere, composed primarily of nitrogen and oxygen with trace amounts of carbon dioxide and other gases, creates a moderate greenhouse effect that warms our planet by about 60 degrees Fahrenheit above what it would be without an atmosphere. This warming is essential for keeping water liquid across much of the planet's surface. Too little atmosphere, like Mars, and a planet freezes. Too much, like Venus, and it roasts under an extreme greenhouse effect. The presence of water itself profoundly affects habitability. Water has an extraordinarily high heat capacity, meaning it can absorb and store large amounts of heat without changing temperature dramatically. Oceans act as thermal buffers, moderating a planet's climate and preventing extreme temperature swings. Water also plays a crucial role in weathering rocks and regulating carbon dioxide levels in the atmosphere through a feedback mechanism that helps stabilize climate over long timescales. Planetary size matters because it determines surface gravity, which affects a planet's ability to retain an atmosphere. Smaller planets, with weaker gravity, more easily lose their atmospheric gases to space. Mars, with only 1/3 Earth's gravity, has gradually lost most of its atmosphere over billions of years. Larger planets can hold onto their atmospheres more tenaciously, but if they grow too large, they become gas giants that lack a solid surface altogether. The sweet spot appears to be somewhere between half and twice Earth's size. Geological activity, particularly plate tectonics, also contributes to habitability. On Earth, the slow movement of crustal plates recycles carbon between the surface and interior, regulating atmospheric carbon dioxide levels over millions of years. This geological carbon cycle helps maintain stable temperatures despite the sun's gradually increasing brightness. Volcanic activity releases gases that replenish the atmosphere, while subduction zones pull carbon-bearing rocks back into the interior. Planets without active geology might lack these stabilizing mechanisms. A planet's magnetic field provides protection from stellar radiation and solar wind, streams of charged particles that flow outward from stars. Earth's magnetic field, generated by the motion of molten iron in our planet's core, deflects much of this radiation, preventing it from stripping away our atmosphere. Mars lacks a strong magnetic field and has consequently lost much of its atmosphere to space. For planets around active stars that produce intense radiation, a protective magnetic field might be essential for maintaining habitability. Orbital characteristics also influence climate stability. Earth's nearly circular orbit keeps us at a fairly constant distance from the Sun throughout the year. A highly elliptical orbit would cause dramatic swings in the amount of energy a planet receives, potentially making climate unstable. The tilt of a planet's rotational axis creates seasons, which drive atmospheric circulation and help distribute heat around the planet. Too much tilt could lead to extreme seasonal variations, while no tilt would eliminate seasons entirely. Even factors like the presence of a large moon can affect habitability. Our moon stabilizes Earth's axial tilt, preventing dramatic wobbling that would cause severe climate swings. The moon also drives tides that may have played a role in the transition of life from ocean to land. These subtle factors remind us that habitability emerges from a combination of many conditions working together, not just a planet's distance from its star. The search for habitable worlds has evolved dramatically over the past few decades, transforming from theoretical speculation to observational science. As our telescopes become more powerful and our techniques more refined, we're discovering that planets are incredibly common and that many orbit within their stars' habitable zones. The next challenge is determining which of these worlds actually possess conditions suitable for life and whether any of them host biological activity. Current technology allows us to detect planets primarily through two methods. The transit method watches for the slight dimming of starlight when a planet passes in front of its star. The radial velocity method measures the subtle wobble in a star's motion caused by the gravitational pull of orbiting planets. Both techniques have been tremendously successful, revealing thousands of planets around other stars. However, these methods tell us about a planet's size and orbit but reveal little about its atmosphere or surface conditions. The next generation of space telescopes will change this dramatically. These instruments will analyze starlight filtering through planetary atmospheres as planets transit their stars. By examining which wavelengths are absorbed, astronomers can identify atmospheric gases. The presence of oxygen, methane, and water vapor together might indicate biological activity, since these gases react with each other and would normally disappear unless continuously replenished by living processes. Finding such biosignatures would revolutionize our understanding of life's prevalence in the universe. Ground-based telescopes are also becoming more capable. Enormous instruments will have mirrors over 30 meters across, gathering more light than any previous optical telescope. These giants will be able to directly image some planets around nearby stars, capturing actual photographs of these distant worlds. While they'll appear as mere pinpoints of light, even that will allow astronomers to study how the planet's brightness changes, potentially revealing the presence of clouds, oceans, or continents. Our understanding of habitable zones continues to evolve as scientists discover new factors that influence habitability. Recent research suggests that planets with extensive cloud cover might remain habitable much closer to their stars than previously thought, as the clouds reflect incoming starlight. Other studies show that planets with subsurface oceans, like Jupiter's moon Europa or Saturn's moon Enceladus, might harbor life even far outside the traditional habitable zone. These discoveries are expanding our conception of where life might exist. Scientists are also beginning to consider the concept of a galactic habitable zone, a region within the Milky Way galaxy where conditions are most favorable for life. Too close to the galactic center, and frequent supernovae and intense radiation might sterilize planets. Too far out in the galactic outskirts, and there might not be enough heavy elements to form rocky planets. Our solar system sits in what might be a favorable region, about 2/3 of the way from the galactic center, where conditions are just right for life to flourish. The discovery of thousands of planets has also revealed that planetary systems are more diverse than we ever imagined. We've found hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, super-Earths larger than our planet but smaller than Neptune, and systems where multiple planets orbit in tight formation. This diversity suggests that planet formation and evolution are more variable than our single example, the solar system, led us to believe. Each discovery refines our understanding of how planetary systems develop and where habitable worlds might arise. Looking ahead, the search for habitable worlds and potential life beyond Earth will intensify. Within the next few decades, we may detect chemical signs of life in the atmosphere of a planet orbiting another star. We might identify dozens or even hundreds of potentially habitable worlds within a few hundred light years of Earth. Each discovery will help us understand whether life is common or rare, whether Earth is typical or unusual, and whether intelligence like ours emerges readily or represents an extraordinary cosmic fluke. And on that note, we reach the end of our journey through the habitable zones of distant stars. We've explored how these regions of potential habitability change with stellar type, how planetary characteristics determine whether worlds within these zones can actually support liquid water, and how our understanding continues to evolve with each new discovery. The search for habitable worlds represents one of humanity's most profound scientific endeavors, touching on questions about our place in the universe and whether we're alone among the stars. The universe operates on a principle that would make any environmentalist proud. Nothing goes to waste. When a star dies, it doesn't simply disappear into the void. Instead, it releases everything it spent millions or billions of years creating, sending those materials back into the cosmic pool where they can be used again. It's the ultimate recycling program, and it's been running since the first stars ignited in the early universe. In the beginning, right after the Big Bang, the universe was remarkably simple. Hydrogen made up about 75% of all matter, with helium accounting for most of the rest. There were trace amounts of lithium, and that was essentially it. No carbon, no oxygen, no silicon, no iron. None of the elements that make planets possible, let alone life. The periodic table was almost empty. This presented a problem. Those first stars, called population 3 stars, formed from this primordial gas. They were massive, burning bright and fast, but they were chemically simple. When they died, however, something remarkable happened. The intense pressures and temperatures in their cores and during their explosive deaths created heavier elements. Suddenly, the universe had a periodic table with more entries. Each generation of stars has added to this chemical enrichment. Astronomers sometimes talk about metallicity, which in astronomy means any element heavier than helium. The first stars had zero metallicity. Our Sun, a relative newcomer at just 4.6 billion years old, has substantial metallicity because it formed from gas clouds already enriched by countless previous generations of stars. Think of it like composting in a garden. The first garden is only basic soil. But as plants grow, die, and decompose, they enrich that soil with nutrients. Each new generation of plants benefits from the remains of the old. Eventually, you have rich, fertile ground capable of supporting incredible diversity. The universe works the same way, except instead of soil, we're talking about vast clouds of gas and dust floating between the stars. This process of cosmic recycling isn't just interesting from a scientific perspective. It's deeply personal. Every atom in your body, except for some hydrogen, was created in the heart of a dying star. You are a direct product of this cosmic recycling system. Understanding how it works means understanding where we came from and how we got here. To understand cosmic recycling, we first need to understand how stars die, because that's where the recycling begins. Stars are in constant battle against their own gravity. For most of their existence, they maintain a delicate balance. Gravity pulls inward, trying to collapse the star. Nuclear fusion in the core pushes outward through radiation pressure and heat. As long as these forces balance, the star remains stable. Our Sun is currently in this stable phase, fusing hydrogen into helium in its core. It's been doing this for 4.6 billion years and will continue for another 5 billion or so. This is called the main sequence phase, and stars spend the majority of their existence here. It's a comfortable equilibrium, like a perfectly balanced seesaw. But nothing lasts forever. Eventually, a star runs out of hydrogen fuel in its core. When this happens, the outward pressure decreases, and gravity gains the upper hand. The core begins to collapse, and as it does, it heats up. This increased temperature allows helium to begin fusing into carbon and oxygen. The star enters its red giant phase. For stars like our Sun, this is essentially the beginning of the end. The outer layers expand enormously. Our Sun will eventually swell to engulf Mercury, Venus, and possibly Earth. Meanwhile, the core continues its fusion processes, but there's a limit. Stars with the mass of our Sun can't generate enough pressure and temperature to fuse elements heavier than carbon and oxygen. When the helium is exhausted, there's no more fuel to burn. At this point, the outer layers drift away in a relatively gentle process, forming what we call a planetary nebula. Despite the name, these have nothing to do with planets. They're expanding shells of gas, often stunningly beautiful when photographed by telescopes. The core that remains becomes a white dwarf, a dense object about the size of Earth but containing roughly the mass of the Sun. It will cool slowly over trillions of years. This is the fate awaiting most stars, including our Sun. It's a relatively peaceful death, all things considered. The material in those expanding shells returns to interstellar space, enriched with the carbon and oxygen created during the star's red giant phase. This material can eventually help form new stars and planetary systems. But more massive stars, those with at least 8 times the mass of our Sun, face a far more dramatic end. These stellar giants can generate the extreme temperatures and pressures needed to fuse progressively heavier elements. After hydrogen, they fuse helium into carbon and oxygen. Then carbon into neon and magnesium. Oxygen into silicon and sulfur. Finally, silicon into iron. This process creates layers in the star's interior, like an onion. Each layer is fusing different elements, with the heaviest elements toward the center. The problem is that iron is the end of the line. Fusing iron doesn't release energy. It actually requires energy. When the core becomes iron, fusion stops abruptly. Without fusion to provide outward pressure, gravity wins decisively and suddenly. The core collapses catastrophically, going from the size of Earth to perhaps 20 kilometers across in under a second. The collapse happens so fast that the outer layers are still falling inward when the core rebounds. The result is a supernova, one of the most violent events in the universe. In that moment, a single star can briefly outshine an entire galaxy containing hundreds of billions of stars. The energy released in a supernova is almost incomprehensible. In just a few seconds, a supernova releases more energy than our Sun will produce in its entire 10 billion year lifetime. That's the power needed to create and scatter the heaviest elements in the universe. Supernovae are the universe's foundries, the factories where most heavy elements are created. To understand how special they are, we need to look at what happens during those final explosive moments of a massive star's existence. The physics at play is extreme, pushing matter and energy to their absolute limits. When the core of a massive star collapses, it doesn't just fall gently inward. We're talking about a mass greater than our Sun being crushed into a sphere smaller than a city. The density becomes so extreme that protons and electrons are forced together, creating neutrons. This is called neutron degeneracy, and the pressure from these packed neutrons is what finally stops the collapse. The core bounce that happens next is violent beyond imagination. Think of it like dropping a rubber ball. When it hits the ground, it compresses, then rebounds and bounces back up. Except in this case, the ball is the core of a star, and the ground is neutron degeneracy pressure. The rebound sends a shock wave tearing outward through the star at roughly 10% the speed of light. This shock wave encounters all those layers of the star we talked about earlier. The silicon layer, the oxygen layer, the carbon layer, and so on. As the shock wave plows through them, it heats these layers to billions of degrees and compresses them enormously. Under these conditions, nuclear reactions can occur that are impossible anywhere else in the universe. Elements heavier than iron, which couldn't be created through normal stellar fusion, are suddenly possible. Gold, platinum, uranium, and everything in between are synthesized in these extreme conditions. The process happens through something called rapid neutron capture, where atomic nuclei are bombarded with so many neutrons so quickly that they can build up mass faster than they decay. It's worth pausing to appreciate how rare and special this process is. The gold in any jewelry, the uranium in nuclear reactors, the lead in old pipes, all of it was created in supernova explosions. These elements quite literally cannot be made any other way. Every gold atom on Earth was forged in a stellar explosion somewhere in our galaxy billions of years ago. The shockwave doesn't just create these elements. It also blasts them into space at tremendous velocities, often thousands of kilometers per second. In a matter of hours, a supernova can eject more mass than several suns, spreading it across light years of space. This is the key step in cosmic recycling. All those newly created elements, along with the lighter elements from the star's outer layers, are now free to mix with the interstellar medium. Astronomers can actually observe this process happening. The Crab Nebula, for example, is the remnant of a supernova that was observed on Earth in the year 1054. Chinese and Arab astronomers at the time noted a new star so bright it was visible during the day for nearly a month. Today, we can see the expanding cloud of gas, still moving outward at about 1,500 kilometers per second. Inside that cloud are all the elements created during that star's lifetime and death. Spectroscopic analysis reveals oxygen, sulfur, iron, and other elements spreading through space. In a few million years, that material will mix thoroughly with the surrounding gas clouds. Some of it may eventually find its way into new stars and planetary systems. Not all supernovae are the same. The type we've been discussing, called core collapse supernovae, occur when massive stars die. But there's another type, called Type 1a supernovae, that happen when white dwarfs in binary systems accumulate too much mass from a companion star. These explosions are important for creating iron and nickel specifically, while core collapse supernovae produce a broader range of elements. Between the stars, space is not truly empty. There's a thin but incredibly important substance called the interstellar medium, and it's the connecting tissue that makes cosmic recycling possible. This is where supernova ejecta goes, where new stars will eventually form, and where the chemical enrichment of the universe gradually increases over time. The interstellar medium is extraordinarily dilute by earthly standards. On average, there's about 1 atom per cubic centimeter in the space between stars. For comparison, the air you're breathing is about 10 to the power of 19 molecules per cubic centimeter. That's 10 million trillion times denser than the interstellar medium. By our standards, it's essentially a perfect vacuum. But space is so vast that even this incredibly thin material adds up. The interstellar medium makes up roughly 10 to 15% of the total mass of the visible matter in our galaxy. That's billions of times the mass of our sun, just floating around between the stars. Most of it is still hydrogen and helium, but it's increasingly seasoned with heavier elements from countless stellar deaths. The interstellar medium isn't uniform. It exists in different phases, sort of like how water can be ice, liquid, or steam depending on temperature. There are cold, dense molecular clouds where temperatures drop to just 10 degrees above absolute zero. These clouds can be hundreds of light years across and contain enough mass to form thousands or even millions of stars. Then there are warmer, less dense regions called the warm neutral medium and the warm ionized medium. These regions have temperatures of thousands to tens of thousands of degrees. They fill much more volume than the cold clouds but contain less total mass. Light from nearby stars heats these regions and can ionize the hydrogen, stripping electrons away from the atoms. Most surprising are the hot ionized regions, where temperatures reach millions of degrees. These bubbles of superheated gas are created by, you guessed it, supernovae. When a star explodes, it doesn't just send material outward. It also heats the surrounding space to incredible temperatures. These hot bubbles can be hundreds of light years across and take millions of years to cool down. Think of the interstellar medium like the ocean. It has currents and eddies. It has warm spots and cold spots. It has storms in the form of supernova shockwaves. And just like Earth's oceans carry nutrients that support life, the interstellar medium carries the chemical elements that make planets and life possible. Material circulates through it, constantly mixing and evolving. When a supernova explodes, it creates a shock wave that plows through the interstellar medium like a boat moving through water. The shock compresses the gas in front of it, heating it and causing it to glow. This is why supernova remnants are so bright. We're seeing the collision between the expanding debris and the surrounding medium, a collision happening at thousands of kilometers per second. These shock waves do more than just heat gas. They also trigger star formation. When the shock compresses a cold molecular cloud, it can push the density past a critical threshold. Suddenly, parts of the cloud become unstable and begin to collapse under their own gravity. This is one of the ways that stellar death directly leads to stellar birth. The dying star's last act is to help create the next generation. Our own solar system might owe its existence to a nearby supernova. Some scientists believe that a shock wave from an exploding star compressed the molecular cloud that would become our sun and planets. There's even evidence in meteorites of radioactive isotopes that only form in supernovae and decay relatively quickly. Their presence suggests a supernova happened nearby and recently, in cosmic terms, just before our solar system formed. Star formation is one of the most beautiful processes in astronomy, and it begins in those cold, dense molecular clouds we just discussed. These clouds are the nurseries of stars, vast regions where gravity slowly gathers material together, concentrating it until nuclear fusion can ignite. Every star begins this way, including our sun, and the material they form from is thoroughly recycled from previous generations. Inside a molecular cloud, the temperature is frigid, just 10 or 20 degrees above absolute zero. At these temperatures, atoms move sluggishly. Gas that would normally have enough thermal energy to resist gravity finds itself vulnerable. If a region of the cloud is dense enough and massive enough, gravity can overcome the outward pressure of the gas. When this happens, the region begins to collapse. The collapse starts slowly, almost imperceptibly. Over hundreds of thousands of years, the cloud region contracts, gradually becoming smaller and denser. As it does, something interesting happens. The conservation of angular momentum means that any slight rotation in the original cloud becomes faster as it collapses, like a figure skater pulling in their arms during a spin. This rotation flattens the collapsing cloud into a disk. At the center, where material is most concentrated, a protostar forms. This isn't yet a true star because nuclear fusion hasn't begun. It's simply a hot ball of gas being compressed by gravity, glowing from the heat of that compression. Around it, the disk of material continues to swirl, and this disk is where planets will eventually form. The composition of this disk tells the story of cosmic recycling. If this were a first-generation star forming in the early universe, the disk would be almost entirely hydrogen and helium. But for stars forming today, including the stars being born right now in regions like the Orion Nebula, the disk contains all the elements from previous stellar generations. Spectroscopic studies of young stellar systems reveal the presence of carbon, oxygen, silicon, iron, and dozens of other elements in these disks. These are the building blocks of planets. The rocky planets in our solar system, Earth included, are made primarily from these heavy elements. Without the cosmic recycling that enriched the interstellar medium with these materials, rocky planets simply couldn't exist. It takes millions of years for a protostar to gather enough mass and for its core to become hot and dense enough for fusion to begin. The threshold is about 10 million degrees Kelvin for hydrogen fusion. Once this temperature is reached, hydrogen nuclei begin fusing into helium, releasing tremendous energy. The star turns on, and the outward pressure from fusion balances the inward pull of gravity. A new main sequence star is born. The leftover material in the disk doesn't disappear. In the inner regions, where it's warmer, rocky planets can form from the condensation of metals and silicates. Further out, where it's colder, ice can form along with rock, allowing much larger planets to accumulate. These become gas giants like Jupiter and Saturn. Even further out, small icy bodies remain, forming the comets and Kuiper belt items that orbit at the fringes of the system. Our solar system formed approximately 4.6 billion years ago from a molecular cloud that had been enriched by countless previous stars. The oldest materials we've found in meteorites, called calcium-aluminum-rich inclusions, date to right around this time. These tiny grains represent the first solid materials that condensed from the solar nebula, and they contain elements that could only have been created in stars that died before our sun was born. Every star system forming today goes through this same process, using recycled stellar material. The Hubble Space Telescope and other observatories have captured stunning images of this happening in real time. The pillars of creation in the Eagle Nebula show towers of gas and dust where new stars are forming right now, their composition enriched by the deaths of previous stellar generations. Once a star has formed and stabilized, the disk of material around it begins the intricate process of building planets. This is where cosmic recycling becomes tangible, where atoms forged in stellar cores billions of years ago come together to form worlds. The process is chaotic, violent, and ultimately creative, turning a disk of dust and gas into a diverse family of planets. In the beginning, the disk contains countless tiny particles, each just micrometers across. These dust grains are made of whatever materials could condense at that distance from the young star. Close in, only materials with high melting points can remain solid. Metals like iron and nickel, and rocky materials like silicates, can exist here. Further out, it's cold enough for water ice, then ammonia ice, then methane ice to form. The dust grains begin to stick together through a combination of electrostatic forces and gentle collisions. Over time, they grow from micrometers to millimeters, then to centimeters. These larger clumps, called planetesimals, have enough gravity to start attracting more material actively. The growth accelerates. Meter-sized bodies become kilometer-sized bodies. Eventually, some planetesimals grow large enough to dominate their region of the disk. These growing worlds collide and merge in a process called accretion. Sometimes the collisions are gentle enough that the bodies stick together, combining their mass. Other times, the impacts are violent, shattering both bodies and creating debris that must start the process over again. It's a messy, inefficient process, but over millions of years, it produces planets. The composition of these planets directly reflects their distance from the star and the recycled materials available. Close to the star, we get rocky planets made primarily of iron, magnesium, silicon, and oxygen. Earth is a perfect example. Our planet is made largely from elements that didn't exist in the early universe. Every atom of silicon in Earth's crust, Every atom of iron in its core was created in a star that died before our solar system existed. Further from the sun, where ices could remain solid, planets could grow much larger. These worlds accumulated not just rock and metal, but also vast amounts of ice. Once they reached about 10 Earth masses, their gravity became strong enough to capture hydrogen and helium directly from the disk. This is how gas giants like Jupiter and Saturn formed. They have rocky and icy cores, but they're mostly hydrogen and helium, the primordial elements from the Big Bang. As planets grow, they heat up from the energy of impacts and from the decay of radioactive elements. This heating is important because it allows planets to differentiate. The heaviest materials, primarily iron and nickel, sink toward the center, forming a metallic core. Lighter rocky materials float upward, forming a mantle and crust. This is why Earth has the layered structure it does today. The radioactive elements providing much of this heat are themselves products of cosmic recycling. Uranium, thorium, and potassium-40 are all created in supernovae and other stellar processes. They decay over millions and billions of years, generating heat. Without this heat source from long-dead stars, Earth's interior would have cooled quickly. We wouldn't have plate tectonics, and quite possibly life would never have arisen. The final stages of planetary formation in our solar system were particularly violent. Computer simulations and isotopic evidence suggest that Earth was struck by a Mars-sized body about 4.5 billion years ago. The impact was so powerful that it vaporized a large portion of both planets. The debris from this collision coalesced to form our moon. Even Earth's water may have been delivered later by comets, themselves made of ice recycled from dead stars. This entire process, from dust grain to fully formed planet, takes roughly 100 million years. It sounds like a long time, but in cosmic terms, it's remarkably quick. And every step of the way, the process relies on materials recycled from previous stellar generations. The cycle of cosmic recycling doesn't end once planets form. Stars continue to die, supernovae continue to explode, and new stars continue to be born. Each complete cycle takes hundreds of millions to billions of years, but the cycle has been running for nearly the entire history of the universe. We can trace how this has changed the cosmos over time. The universe is about 13.8 billion years old. The first stars formed perhaps just 100 million years after the Big Bang, once the universe had cooled enough for gravity to pull hydrogen and helium together. These first stars were massive, probably hundreds of times the mass of our Sun, and they burned through their fuel quickly, dying in supernovae within just a few million years. Those first supernovae were transformative. For the first time, the universe contained elements heavier than lithium. Carbon, oxygen, silicon, iron, and many others were scattered into space. The next generation of stars formed from gas that was slightly enriched with these heavier elements. When they died, they added even more heavy elements to the mix. This has been going on for over 13 billion years. Each stellar generation has added to the chemical richness of the universe. Astronomers can actually measure this enrichment by looking at stars of different ages. Old stars, formed 10 or 12 billion years ago, have much lower concentrations of heavy elements than young stars forming today. Our Sun sits somewhere in the middle, with a metallicity that suggests it's a third or fourth generation star. The rate of this enrichment has changed over time. In the early universe, star formation was incredibly active. Galaxies were forming and merging, creating bursts of new stars. Supernovae were correspondingly frequent. The enrichment of the interstellar medium happened rapidly during this period. As the universe aged and expanded, star formation gradually slowed. The enrichment continues, but at a more measured pace. Our galaxy, the Milky Way, has its own recycling rate. Astronomers think that it takes several billion years for material to complete one full cycle from star to supernova to interstellar medium to new star. The galaxy produces about 3 solar masses worth of new stars each year, while roughly the same amount of material is returned to the interstellar medium through stellar winds, planetary nebulae, and supernovae. This balance is important. If too much material got locked up in stars and planets permanently, eventually the galaxy would run out of gas to make new stars. Star formation would cease, and the galaxy would slowly fade as existing stars aged and died. Conversely, if stellar recycling were too efficient and all material stayed in the interstellar medium, stars might never form at all. The current rate seems to be a sustainable middle ground. Different types of galaxies have different recycling rates. Elliptical galaxies, which are often older, have used up most of their gas and form few new stars. They're dominated by old, red stars. Spiral galaxies like the Milky Way have ongoing star formation, with new blue stars constantly being born in their spiral arms. Irregular galaxies often have bursts of intense star formation triggered by collisions or mergers with other galaxies. On really long timescales, trillions of years in the future, this cycle will slow down. Red dwarf stars, the smallest type of main sequence star, can burn for trillions of years. Once formed, they lock up their mass for cosmically vast periods. Eventually, most hydrogen will be incorporated into these long-lasting stars or into stellar remnants like white dwarfs and neutron stars. Star formation will become increasingly rare and eventually stop altogether. But that's an unimaginably distant future. For now, and for billions of years to come, cosmic recycling continues. Every day, somewhere in our galaxy, a star dies and returns its enriched materials to space. Every day, new stars ignite, incorporating those materials into themselves and their planetary systems. The cycle continues, as it has for most of the universe's history. We've traced the journey of matter from the cores of dying stars through the interstellar medium to new stellar systems and planets. Now it's time to consider the most profound implication of cosmic recycling. We ourselves are participants in this cycle. The atoms that make up your body have been through this process, some of them multiple times. Think about a single carbon atom in your body. Let's imagine its history. 10 billion years ago, it was part of a massive star somewhere in what would become the Milky Way galaxy. That star fused lighter elements in its core, eventually creating this carbon atom through the triple alpha process, where 3 helium nuclei combined. When the star eventually exploded in a supernova, our carbon atom was blasted into space. For millions of years, it drifted through the interstellar medium, mixing with hydrogen, helium, and other elements from countless other stars. Eventually, it became part of a molecular cloud. That cloud collapsed, forming new stars. Our carbon atom might have been incorporated into a star, only to be expelled again through a stellar wind. Or it might have missed the star entirely and remained in the disk around it. About 4.6 billion years ago, our carbon atom finally found a more permanent home. It became part of the disk around a newly forming yellow star, our Sun. As planetesimals collided and grew, the carbon atom was incorporated into a rocky body. Eventually, that body became part of Earth, perhaps delivered through a later impact with a comet or asteroid. For billions of years, the carbon atom cycled through Earth's geology. It might have been part of a limestone rock, then dissolved in the ocean, then incorporated into a shell of an ancient sea creature, then buried and transformed into sedimentary rock. Eventually, it entered the biosphere. Perhaps it was taken up by a plant through photosynthesis, then eaten by an animal, then released back into the air when that animal died and decomposed. And now, right now, it's part of you. Maybe it's in a protein in your muscle tissue, or part of a strand of DNA, or in a molecule of carbon dioxide you're about to exhale. Soon it will leave your body and continue its journey. It might become part of a tree, or dissolve in the ocean, or remain in the atmosphere for years before being taken up by another organism. This is true for every atom in your body. The hydrogen in your water molecules is mostly primordial, formed in the Big Bang. But the oxygen in that same water was created in stars. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, the sulfur in your proteins, all of it was forged in stellar furnaces billions of years ago. Carl Sagan famously said that we are made of star stuff, and it's not just poetry. It's literal truth. The atoms in your left hand probably came from different stars than the atoms in your right hand. You are an assembly of materials with unimaginably ancient and varied histories, brought together briefly in the form that is you, before they continue their cosmic journey. This perspective can be humbling and awe-inspiring at the same time. We are temporary arrangements of matter, but that matter has existed for billions of years and will continue to exist for billions more. We are connected through this material to the entire history of the universe. Every breath you take contains atoms that were once in the bodies of dinosaurs, of early humans, of the first bacteria on Earth. And before that, they were in stars. The cycle continues beyond us too. 5 billion years from now, our sun will become a red giant, then shed its outer layers and die. The atoms that make up Earth, and everything on it, will be scattered into space. They'll mix with the interstellar medium, already enriched by countless other stellar deaths. Eventually, they'll become part of new stars, new planets, perhaps new forms of life we can't even imagine. And on that note, we've completed our journey through cosmic recycling. From stellar death to supernova explosions, through the interstellar medium to new star formation, to planets, and ultimately to us. It's a cycle that's been running for nearly 14 billion years, and it will continue for billions more. We are not just observers of this cycle. We are participants, temporary gatherings of ancient stardust experiencing the universe for a brief moment before returning to the cosmic pool. In the beginning, there was simplicity. The universe, just minutes after the Big Bang, contained only the lightest elements. Hydrogen made up about 75% of all matter, helium comprised nearly all the rest, and there were tiny traces of lithium. That's it. No carbon, no oxygen, no nitrogen, no iron. None of the elements that would later become essential for planets, for water, for life itself. Think of the early universe like a cosmic kitchen with only 3 ingredients. Imagine trying to bake a cake with just flour, water, and a pinch of salt. You simply can't create the complex, rich flavors that make a cake delicious. The universe faced the same limitation. To create planets, oceans, and eventually life, it needed a much more diverse pantry of elements. The solution came in the form of the first generation of stars. These ancient giants were massive beyond comprehension, some containing hundreds of times more matter than our sun. When gravity pulled together these primordial gas clouds, something magical began to happen. As the hydrogen and helium collapsed inward, the temperature at the core climbed higher and higher. At around 10 million degrees Celsius, hydrogen nuclei moving at incredible speeds began to overcome their natural repulsion and fuse together. This process, called nuclear fusion, released enormous amounts of energy. The star began to shine, and in doing so, it started the first great cosmic recipe for creating heavier elements. Inside these stellar furnaces, hydrogen fused into helium, helium fused into carbon, carbon into oxygen, oxygen into silicon, and so on up the periodic table. Each step required higher temperatures and pressures. The star was like a master chef, slowly building more complex dishes by combining simpler ingredients under increasingly extreme conditions. But these first-generation stars, the ones astronomers call population 3 stars, faced a fundamental limit. When they tried to create elements heavier than iron, the fusion process began to consume energy rather than produce it. Iron became the endpoint, the element that essentially poisoned the fusion process. Picture a star as a constant battle between two forces. Gravity pulls everything inward, trying to collapse the star. The energy from fusion pushes outward, keeping the star inflated like a balloon. For millions of years, these forces balance perfectly. But when iron builds up in the core, fusion can no longer provide the outward pressure needed to fight gravity. The result is catastrophic and beautiful. In less than a second, the core collapses. The outer layers of the star crash inward at thousands of kilometers per second, then rebound in a spectacular explosion called a supernova. These explosions are so bright they can outshine entire galaxies for weeks. But here's the truly remarkable part. In those final moments of collapse and explosion, the extreme conditions finally become powerful enough to forge the heaviest elements. The gold in your jewelry, the silver in your coins, the uranium in nuclear reactors, all of these were created in the death throes of ancient stars. These stellar explosions scattered their newly forged elements across vast distances, seeding space with the building blocks for future generations of stars and planets. The universe's pantry was finally being stocked with all the ingredients necessary for complexity, for planets, and eventually, for you. The death of those first-generation stars was not an ending, but a beginning. Their explosive final moments sent shockwaves rippling through space, carrying with them the precious cargo of heavy elements forged in their cores. These stellar winds traveled for thousands of years, mixing the new elements with the vast clouds of hydrogen and helium that drifted between the stars. Imagine space as an enormous ocean, and these expanding bubbles of stellar debris as drops of ink spreading slowly through the water. Over millions of years, these drops mixed and blended, creating regions of space enriched with carbon, oxygen, silicon, iron, and dozens of other elements. These enriched regions became the stellar nurseries where the next generation of stars would be born. When gravity began to pull together these element-rich gas clouds, something different happened. The new stars that formed were not just hydrogen and helium giants like their predecessors. They contained the full palette of elements, and this made all the difference. These second and third generation stars could form planets, and those planets could have solid surfaces, atmospheres, and eventually, the chemistry necessary for life. Our Sun is one of these later generation stars, born about 4.6 billion years ago from a collapsing cloud that astronomers call the solar nebula. This nebula contained not just hydrogen and helium, but also carbon from ancient supernovas, oxygen from stellar fusion, silicon from dying stars, and iron from cosmic explosions that happened billions of years before our solar system even existed. As the solar nebula collapsed, it began to spin faster, flattening into a disc shaped like pizza dough being spun by a chef. At the center, where most of the mass concentrated, our sun ignited. But in the cooler outer regions of the disk, something extraordinary was happening. The heavy elements were beginning to stick together. Think of this process like making a snowball. First, tiny particles of dust, made from elements forged in ancient stars, began to clump together through electrostatic forces. These clumps attracted more particles, growing larger and larger. As they grew, their gravity became strong enough to pull in even more material. The temperature in different parts of the solar system determined which elements could condense into solid form. Close to the sun, where temperatures were scorching, only the most heat-resistant materials like iron and nickel could solidify. This is why the inner planets, including Earth, are rocky worlds with metallic cores. Further from the sun, where temperatures were cooler, water could freeze into ice, and lighter elements could condense. This is why the outer planets became gas giants, capturing vast amounts of hydrogen and helium, while their moons became icy worlds rich in frozen water and other compounds. During this period of planetary formation, the solar system was a chaotic place. Planetesimals, ranging in size from pebbles to small moons, crashed into each other constantly. Each collision either built up the growing planets or shattered apart, redistributing material throughout the system. Earth formed through this violent process of accretion. Every impact delivered atoms forged in stellar cores billions of years ago. The iron that sank to form our planet's core came from supernova explosions. The silicon and oxygen that formed our rocky mantle were created in the fusion furnaces of dying stars. The carbon that would later become essential for life was manufactured in stellar interiors through a process discovered by astronomer Fred Hoyle. But the story doesn't end with planetary formation. Even after Earth had mostly solidified, impacts continued. Comets and asteroids, themselves made from stellar debris, crashed into our young planet. These impacts delivered water to our oceans and organic compounds that would later participate in the chemistry of life. Every atom in these cosmic visitors had its own stellar origin story, adding new chapters to Earth's growing library of elements. During Earth's first billion years, the atoms that now make up your body were scattered across our planet. Some were dissolved in the primordial oceans, others were locked in rocks and minerals, still others drifted in our early atmosphere. They waited patiently, these stellar children, for the next chapter in their cosmic journey. For nearly a billion years after Earth's formation, our planet was a world in transition. The stellar atoms delivered by cosmic impacts were slowly reorganizing themselves. Driven by the planet's internal heat and the energy from our young Sunday volcanoes brought elements from deep within the Earth to the surface. Rain and rivers carried dissolved minerals from rocks to the oceans. Lightning and ultraviolet radiation provided energy for the first chemical reactions that would eventually lead to life. Think of early Earth as a vast laboratory where stellar atoms were experimenting with new combinations. The carbon atoms forged in dying stars began linking together in chains and rings. Oxygen atoms, created in stellar fusion, combined with hydrogen to form water molecules that filled our growing oceans. Phosphorus atoms, rare products of stellar nucleosynthesis, became part of energy-storing compounds. In this cosmic laboratory, something extraordinary began to happen around 3.8 billion years ago. The stellar atoms started forming increasingly complex partnerships. Carbon, with its unique ability to form 4 chemical bonds, became the backbone of organic molecules. It partnered with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create amino acids, the building blocks of proteins. These weren't random combinations. The chemical properties of each element, determined by the number of protons in their nuclei, made certain partnerships more favorable than others. Carbon's versatility came from its nuclear structure, created billions of years earlier in stellar cores through the triple alpha process. Nitrogen's ability to form strong bonds was a gift from ancient supernovas. Each element brought its stellar heritage to Earth's growing molecular complexity. The first major breakthrough came when these organic molecules learned to make copies of themselves. RNA molecules, built from stellar carbon, nitrogen, oxygen, and phosphorus, developed the ability to reproduce. This was the moment when chemistry became biology, when stellar atoms transitioned from passive participants to active agents in their own organization. Picture this process like a vast construction site where the building materials suddenly learn to assemble themselves. The calcium atoms, forged in stellar cores, knew how to build structural frameworks. The iron atoms, products of stellar fusion, discovered they could carry oxygen efficiently. The magnesium atoms, gifts from ancient supernovas, found they could help molecules capture and store energy from sunlight. The first simple cells appeared around 3.5 billion years ago. These primitive organisms were little more than bags of water containing concentrated solutions of stellar atoms organized into living systems. But they represented a profound transition. For the first time in cosmic history, stellar atoms were not just reacting to their environment, they were actively changing it. The most important change came when cyanobacteria evolved the ability to perform photosynthesis. Using energy from sunlight, these organisms began splitting water molecules and releasing oxygen gas. This oxygen, made from atoms forged in stellar cores billions of years earlier, began accumulating in Earth's atmosphere for the first time. This period, called the Great Oxidation Event, was actually an environmental catastrophe for most early life forms. Oxygen was toxic to the anaerobic organisms that had dominated early Earth. But this crisis created opportunities for new forms of life that could harness oxygen's chemical power. The stellar iron atoms found new purpose in this oxygen-rich world. Instead of rusting uselessly, they became part of hemoglobin molecules that could bind oxygen reversibly. The stellar carbon atoms discovered they could form more complex partnerships in the presence of oxygen, creating sophisticated organic molecules that stored more energy. Over hundreds of millions of years, the stellar atoms that had been randomly scattered across early Earth became organized into increasingly complex biological systems. They formed the first complex cells, with specialized compartments and sophisticated molecular machinery. They assembled into the first multicellular organisms, creating new levels of organization and cooperation. Each step in this biological evolution was guided by the fundamental properties of stellar atoms. The phosphorus atoms, rare products of stellar nucleosynthesis, became essential components of DNA and RNA. The sulfur atoms, created in stellar cores, formed bridges that gave proteins their complex three-dimensional shapes. The calcium atoms, forged in ancient supernovas, became the building blocks of shells, bones, and cellular communication systems. By the time complex life emerged, Earth had become a living planet where stellar atoms had learned to organize themselves into systems capable of growth, reproduction, and evolution. The atoms in your body had found their calling, transitioning from cosmic wanderers to active participants in the grand experiment of life. As life flourished and diversified over billions of years, the stellar atoms that would eventually become part of you began an intricate dance through Earth's biosphere. They cycled through countless organisms, each one adding new chapters to their biological story. The carbon atom that now sits in your DNA might have once been part of a trilobite scuttling across ancient seafloors, a fern in a carboniferous forest, or a dinosaur roaming Mesozoic landscapes. This great recycling system, powered by the energy of our stellar-born sun, created what scientists call biogeochemical cycles. Think of these cycles as cosmic conveyor belts that move stellar atoms between living organisms, the atmosphere, the oceans, and the rocks beneath our feet. Nothing is ever truly lost, only transformed and relocated. Consider the oxygen atoms you're breathing right now. Some of them were released by prehistoric algae floating in ancient seas. Others were produced by the first land plants as they colonized the continents 400 million years ago. Still others came from the photosynthetic activity of tropical rainforests, grasslands, and marine phytoplankton. Each breath you take connects you to billions of years of biological history. The water molecules in your cells tell equally remarkable stories. The hydrogen atoms in that water are primordial, dating back to the first minutes after the Big Bang. But the oxygen atoms were forged in stellar cores and delivered to Earth through cosmic impacts. Together, these stellar and primordial atoms formed the water molecules that became Earth's oceans, fell as rain, flowed in rivers, and eventually found their way into the biological systems that preceded you. Your calcium atoms have been particularly well-traveled. Before becoming part of your bones and teeth, they may have formed the shells of ancient marine organisms, the limestone cliffs of long-vanished coastlines, or the coral reefs that once teemed with prehistoric life. Each calcium atom carries within its nuclear structure the signature of the stellar explosion that created it, billions of years before Earth even existed. The iron atoms in your blood have their own epic journey. Created in the final moments of stellar collapse, they traveled through space for eons before being incorporated into Earth's formation. They may have spent millions of years locked in iron ore deposits, been extracted and forged into tools by early humans, rusted and returned to the soil, been absorbed by plants, consumed by animals, and finally found their way into your hemoglobin molecules. This biological recycling system reached new levels of complexity with the evolution of ecosystems. Stellar atoms began moving through food webs, passing from photosynthetic organisms to herbivores to carnivores and back again. The nitrogen atoms in your proteins may have been fixed from the atmosphere by bacteria and soil, absorbed by plants, consumed by animals, returned to the earth through decomposition, and begun the cycle again countless times. During the Cambrian explosion 540 million years ago, life discovered new ways to organize stellar atoms. The first organisms with hard shells and skeletons created new reservoirs for calcium and phosphorus. The evolution of more complex nervous systems found new uses for sodium and potassium atoms in electrical signaling. Each evolutionary innovation was essentially a new experiment in organizing stellar matter. The emergence of photosynthetic organisms created a fundamental partnership between stellar atoms and stellar energy. Plants learned to capture photons from our sun and use that energy to build complex organic molecules from simple atmospheric components. This process created the first direct connection between our star's energy and the organization of stellar atoms into biological structures. As life moved onto land, stellar atoms found new environments and opportunities. The phosphorus atoms essential for DNA and cellular energy systems became concentrated in soil and rock formations. The sulfur atoms crucial for protein structures cycled through atmospheric gases, ocean currents, and terrestrial ecosystems. Each element developed its own complex pathways through the biosphere. The most recent chapter in this story began with the evolution of humans and our ancestors. For millions of years, your stellar atoms passed through human lineages, creating the genetic heritage that eventually led to you. The DNA molecules carrying your family's genetic information are built from stellar carbon, nitrogen, oxygen, and phosphorus that have been passed down through countless generations. But the stellar atoms in your body aren't just inherited from your parents. Throughout your lifetime, you're constantly exchanging atoms with your environment. The proteins in your muscles are rebuilt every few months using new amino acids constructed from stellar atoms in your food. Your bones are continuously remodeled using calcium atoms that may have recently been part of other organisms or geological formations. Here you are, a walking, thinking collection of stellar atoms that have journeyed across billions of years and countless cosmic environments to come together in this moment. Every carbon atom in your body was forged in the nuclear furnace of a dying star. Every oxygen atom was created through stellar fusion and delivered to Earth through ancient cosmic collisions. Every calcium atom in your bones was born in a supernova explosion that lit up the cosmos billions of years before our solar system existed. Think about the extraordinary odds of this assembly. The atoms that make up your left hand may have traveled completely different paths through space and time before meeting inside you. Some may have spent millions of years locked in sedimentary rocks, others dissolved in ancient oceans, still others cycling through countless organisms across geological time periods. Yet here they are, cooperating in the complex chemistry that allows you to think, feel, and experience the universe. Your body contains approximately 7 octillion atoms, that's a 7 followed by 27 zeros. Each one has its own stellar origin story. The phosphorus atoms in your DNA were created in the cores of massive stars and scattered through space by supernova explosions. They may have drifted through interstellar space for billions of years before being incorporated into the solar nebula that formed our solar system. The magnesium atoms in your muscles, essential for energy production and protein synthesis, were forged through nuclear fusion in stellar interiors. They participated in the cosmic recycling that created our solar system, became part of Earth's rocky material, cycled through geological and biological processes, and finally assembled into the molecular machinery that powers your daily activities. Even the trace elements in your body tell remarkable stories. The zinc atoms crucial for your immune system and wound healing were created through stellar nucleosynthesis. The copper atoms that help transport oxygen in your bloodstream were manufactured in stellar cores. The iodine atoms essential for your thyroid function were produced in the explosive deaths of massive stars. But perhaps most remarkably, you are not a fixed collection of stellar atoms. Your body is in constant flux, exchanging material with your environment. Scientists estimate that you replace most of the atoms in your body within about 7 years. The atoms that composed you as a child are now scattered throughout the biosphere, while new stellar atoms have taken their place. This means you're more like a temporary pattern that stellar atoms form as they flow through the universe. Like a whirlpool in a river, you maintain your structure and identity even as the material that makes you up is constantly changing. You are a dynamic constellation of stellar matter, organized into the extraordinary phenomenon we call life. The hydrogen atoms in your body water connect you directly to the Big Bang itself. These atoms are among the oldest in the universe, created in the first few minutes after the cosmos began. They've witnessed the entire history of the universe, from the formation of the first stars to the evolution of galaxies, the birth of our solar system, and the emergence of life on Earth. When you look up at the night sky, you're not just observing distant stars. You're seeing the nuclear furnaces where your atoms were forged. The light reaching your eyes was created by the same fusion processes that manufactured the carbon in your muscles, the oxygen in your lungs, and the iron in your blood. You are literally made of star stuff, connected to the cosmos in the most fundamental way possible. This stellar heritage makes every human being a walking piece of cosmic history. The atoms in your body have experienced temperatures of millions of degrees in stellar cores, the vacuum of interstellar space, the violence of planetary formation, and billions of years of geological and biological evolution. They carry within them the entire story of our universe's development from simple hydrogen and helium to complex, self-aware beings. And on that note, we complete our cosmic journey through deep time and space, following the remarkable story of stellar atoms as they traveled from ancient dying stars to become the very substance of your being. From the nuclear furnaces of the first generation of stars, through the formation of our solar system, the evolution of Earth's biosphere, and the long chain of life that led to you, every atom in your body carries the history of the universe itself. The next time you look at your hand, remember that you're seeing stellar material that was forged in cosmic fires billions of years ago. When you breathe, you're inhaling atoms that once drifted through the vast emptiness between stars. When your heart beats, it's pumping blood filled with iron created in supernova explosions that outshone entire galaxies. You are not separate from the cosmos. You are the cosmos, temporarily organized into a form capable of contemplating its own existence. The stellar atoms that compose you will continue their cosmic journey long after your brief moment of self-awareness has passed, perhaps becoming part of future organisms on distant worlds, continuing the universe's long experiment with complexity and consciousness. To understand gravitational waves, we must first grasp the nature of space-time itself. Imagine the universe not as empty void, but as a flexible, invisible fabric stretching in all directions. This fabric, which Einstein called space-time, is the stage upon which all cosmic drama unfolds. Every star, planet, and galaxy sits upon this fabric like bowling balls resting on a stretched rubber sheet. When Albert Einstein published his theory of general relativity in 1915, he revealed that massive objects actually bend this cosmic fabric. Picture dropping a heavy marble onto a trampoline. The marble creates a depression, curving the surface around it. Similarly, the sun creates a depression in space-time, and Earth follows the curved path around this depression, which we experience as orbital motion. Einstein's equations predicted something remarkable. When massive objects accelerate through space, they should create ripples in this fabric, much like a stone thrown into a still pond creates expanding circles of waves. These ripples, moving at the speed of light, would carry information about their source across the cosmos. For decades, these gravitational waves remained purely theoretical. The ripples are incredibly subtle, stretching and compressing space by amounts smaller than a proton's width across distances of several kilometers. Einstein himself doubted whether such tiny distortions could ever be detected. The waves are so gentle that they pass through Earth, through our bodies, through everything, barely interacting with matter at all. Yet these invisible messengers carry profound information. Unlike light, which can be absorbed or scattered, gravitational waves travel unimpeded from their source. They offer us a completely new way to observe the universe, like developing a new sense after being born with only 4. Where optical telescopes show us the universe painted in light, gravitational wave detectors allow us to feel the universe's rhythm, sensing the cosmic heartbeat of colliding giants in distant galaxies. The sources of these waves are among the most extreme environments in the cosmos, pairs of black holes spiraling toward each other, neutron stars colliding in brilliant explosions, and possibly even echoes from the universe's first moments after the Big Bang. Each event creates its own unique signature in the fabric of space-time, a fingerprint written in geometry itself. In the vast darkness between galaxies, some of the universe's most spectacular dances unfold in complete silence. Picture two black holes, each containing the mass of dozens of suns compressed into regions smaller than cities, locked in an eternal gravitational embrace. These cosmic partners orbit each other in an accelerating spiral, their immense gravity gradually drawing them closer together over millions of years. As these black holes orbit, they act like cosmic violins, their motion generating gravitational waves that ripple outward through space-time. Initially, when the black holes are far apart, they create long, slow waves, like the deep bass notes of a cosmic orchestra. The waves carry away energy from the system, causing the orbit to decay ever so slowly. But as the black holes draw closer, something magnificent happens. Their orbital speed increases, following the same principle that makes a figure skater spin faster when pulling in their arms. The gravitational waves grow stronger and more frequent, like a musical pitch rising higher and higher. What began as a barely perceptible bass note gradually becomes a cosmic crescendo. In the final moments before collision, the black holes reach incredible speeds, sometimes circling each other hundreds of times per second. The space-time around them becomes a turbulent sea of gravitational waves. These final seconds, called the inspiral phase, create waves so powerful they can be detected by instruments on Earth, even when the collision occurred billions of light years away. The actual merger happens almost instantaneously. Two separate black holes become one larger black hole in a fraction of a second. This moment, called the chirp, creates the loudest gravitational wave signal. The newly formed black hole wobbles briefly, like a struck bell, before settling into a stable configuration. This final ringing phase, appropriately called the ring down, gradually fades as the system returns to equilibrium. What makes these events truly extraordinary is their energy output. In those final moments of merger, the collision converts several solar masses worth of matter directly into gravitational wave energy, following Einstein's famous equation E=mc². For a brief moment, these distant collisions shine brighter in gravitational waves than all the stars in the observable universe shine in visible light. Scientists have now detected dozens of these black hole mergers, each one telling a unique story. Some involve black holes of similar mass, creating symmetric spirals. Others feature mismatched pairs, where a larger black hole gradually consumes a smaller companion. Each collision adds another note to our growing understanding of the universe's gravitational symphony. While black hole collisions create the universe's deepest bass notes, neutron star mergers contribute their own unique voice to the cosmic symphony. Neutron stars are among the most exotic objects in the universe, the collapsed cores of massive stars, containing the mass of our sun compressed into a sphere only 20 kilometers across. A teaspoon of neutron star material would weigh as much as Mount Everest. These stellar remnants are incredibly dense and perfectly spherical, spinning like cosmic tops at rates that can exceed 700 rotations per second. Their surfaces are smoother than any human-made object, yet their magnetic fields are trillions of times stronger than Earth's. When two of these extreme objects orbit each other, they create gravitational waves with distinctly different characteristics than black hole mergers. Neutron star binaries spiral inward more gradually than black holes, their smaller size allowing them to orbit much closer before merging. This creates gravitational wave signals that last longer, sometimes detectable for minutes before the final collision. The waves gradually increase in frequency and amplitude, like a cosmic siren approaching from the depths of space. But neutron star collisions offer something that black hole mergers cannot: a spectacular light show. Unlike black holes, which trap all electromagnetic radiation, neutron stars can produce brilliant explosions visible across the electromagnetic spectrum. When two neutron stars finally touch, the collision creates what astronomers call a kilonova, an explosion that outshines entire galaxies. These cosmic fireworks serve a profound purpose in the universe's economy. The extreme conditions during neutron star mergers forge heavy elements that cannot be created any other way. Gold, platinum, uranium, and other elements heavier than iron are born in these stellar furnaces. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all were forged in neutron star collisions billions of years ago and scattered across space to eventually become part of planets and life. The gravitational waves from neutron star mergers carry detailed information about these exotic objects. By analyzing the wave patterns, scientists can measure the star's masses, determine their internal structure, and even constrain the behavior of matter under the most extreme conditions possible. Each detected merger provides new insights into the fundamental physics governing these cosmic laboratories. The combination of gravitational waves and traditional electromagnetic observations creates what scientists call multi-messenger astronomy. Instead of relying on light alone, we can now correlate gravitational wave detections with optical, radio, X-ray, and gamma-ray observations of the same event. This provides a far richer understanding of these cosmic phenomena than either approach could achieve alone. Detecting gravitational waves requires some of the most sensitive scientific instruments ever built. The challenge is immense, measuring changes in distance smaller than 1/10,000th the width of a proton across baselines several kilometers long. It's equivalent to measuring the distance from Earth to the nearest star with precision better than the width of a human hair. The solution came in the form of laser interferometry, a technique that uses the wave nature of light to detect incredibly small changes in distance. Picture an L-shaped building with arms stretching 4 kilometers in perpendicular directions. Laser light travels down each arm, reflects off mirrors, and returns to a detector where the beams are combined. Under normal conditions, the two beams arrive perfectly synchronized, canceling each other out in a phenomenon called destructive interference. But when a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction. This changes the travel time for light in each arm by slightly different amounts, causing the laser beams to arrive slightly out of synchronization. The resulting interference pattern reveals the passage of the gravitational wave with extraordinary precision. The Laser Interferometer Gravitational Wave Observatory consists of two identical detectors located 3,000 kilometers apart in Louisiana and Washington state. This separation is crucial for confirming detections and determining the direction from which waves arrive. A true gravitational wave signal will appear at both detectors with a time delay corresponding to the wave's travel time between sites. Building these instruments required solving countless technical challenges. The mirrors must be isolated from all vibrations, suspended by sophisticated systems that filter out everything from earthquakes to traffic passing nearby. The laser systems must maintain incredible stability, and the entire apparatus operates in ultra-high vacuum to prevent air molecules from interfering with the light beams. The detectors are so sensitive they can measure disturbances from ocean waves crashing on distant shores, storms thousands of kilometers away, and even the quiet footsteps of researchers walking near the facility. Sophisticated algorithms help distinguish true gravitational wave signals from this constant background of terrestrial noise. Europe operates its own detector called Virgo in Italy, and additional detectors are planned or under construction in Japan and India. This growing network will provide better sky localization and more detailed studies of gravitational wave sources. Each additional detector improves our ability to triangulate the position of cosmic collisions and alert other telescopes to observe the aftermath. The detection of gravitational waves has opened an entirely new window on the universe, revealing cosmic phenomena that remain invisible to traditional telescopes. In the few years since the first detection in 2015, these cosmic messengers have already revolutionized our understanding of black holes, neutron stars, and the fundamental nature of gravity itself. Before gravitational wave astronomy, our knowledge of black holes came primarily from observing their effects on nearby matter. We could infer their presence by watching stars orbit invisible companions or by observing matter spiraling into accretion disks. But gravitational waves allow us to observe black holes directly, measuring their masses and spins with unprecedented precision. The universe revealed by gravitational waves is more dynamic and violent than we ever imagined. Black hole mergers occur far more frequently than predicted, suggesting that these cosmic collisions have been shaping galactic evolution throughout cosmic history. The detected black holes often have masses larger than expected, challenging our models of stellar evolution and collapse. Neutron star mergers have solved long-standing mysteries about the origin of heavy elements. For decades, astronomers debated whether these elements were created in supernovae or through other processes. Gravitational wave detections of neutron star collisions, combined with optical observations of the resulting kilonovae, have confirmed that these mergers are indeed cosmic forges where gold and platinum are born. Future gravitational wave detectors will be even more sensitive, capable of detecting smaller mergers and more distant events. Space-based detectors like the planned LISA mission will observe different types of sources entirely, including massive black holes at the centers of galaxies and potentially even primordial gravitational waves from the Big Bang itself. These cosmic ripples carry information about some of the most extreme physics in the universe, the behavior of matter at nuclear densities, the properties of spacetime near black holes, and the fundamental nature of gravity itself. Each detection provides a new laboratory for testing Einstein's theory under conditions impossible to replicate on Earth. Perhaps most remarkably, gravitational waves offer the possibility of observing the very early universe directly. Unlike light, which was trapped in hot, opaque plasma for the first 380,000 years after the Big Bang, gravitational waves could have traveled freely from the universe's first moments. Future detectors might glimpse the cosmic dark age before the first stars formed. And on that note, we conclude our gentle exploration of the universe's silent symphony. We've journeyed from the fundamental nature of spacetime itself to the incredible instruments that allow us to feel the cosmic heartbeat of colliding giants. These gravitational waves, rippling through the fabric of reality at the speed of light, carry stories from the most extreme environments in the cosmos, whispering secrets about black holes, neutron stars, and the very nature of existence itself. As we drift towards sleep, consider the profound beauty of this cosmic orchestra that plays constantly around us. Every moment, gravitational waves from countless collisions throughout the universe wash over our planet like gentle tides in an invisible ocean. These waves began their journey billions of years ago, when our solar system was nothing more than a cloud of dust and gas. They have traveled across the vast emptiness of space, carrying their messages through the cosmic dark ages, past the formation of the first stars, through the birth and death of countless galaxies. The universe speaks to us in frequencies far below human hearing, in wavelengths longer than continents, and amplitudes smaller than atomic nuclei. Yet through the ingenuity of human science, we have learned to listen to these cosmic whispers. Each detection is like catching a single snowflake from a blizzard that has been falling since the dawn of time. The gravitational waves we detect today represent just the loudest voices in this cosmic choir, the most dramatic collisions in our cosmic neighborhood. In the coming years, as our detectors become more sensitive and new instruments join the global network, we will hear fainter and more distant voices in this gravitational symphony. We may detect the gentle hum of white dwarf stars orbiting each other in our own galaxy, the thunderous roar of supermassive black holes merging at the hearts of distant galaxies, or perhaps even the primordial echoes from cosmic inflation itself. Each new detection will add another instrument to our cosmic orchestra, revealing harmonies we never knew existed. The universe continues its eternal dance among the stars, weaving space-time into patterns of breathtaking complexity and beauty. Black holes spiral toward their inevitable embrace, neutron stars waltz through space in perfectly choreographed orbits, and somewhere in the distance, new cosmic collisions are creating the gravitational waves that will reach Earth long after we are gone. This is the universe's most patient art form, composing symphonies that play across billions of years, painting with the very fabric of reality itself. To understand the cosmic web, we must first travel back to when the universe was merely 380,000 years old, a cosmic infant by today's standards. At this moment, known as recombination, the universe had cooled enough for the first atoms to form, creating what astronomers call the cosmic microwave background. But hidden within this seemingly smooth afterglow were tiny temperature variations, quantum fluctuations from the Big Bang that would eventually grow into the largest structures we observe today. Think of these early fluctuations like seeds scattered across a vast cosmic garden. Each seed represented a slightly denser region of matter, primarily dark matter, that would begin attracting more material through gravitational pull. Over millions of years, these seeds grew, drawing in surrounding matter like cosmic vacuum cleaners, creating an increasingly complex network of filaments and nodes that would define the universe's architecture for billions of years to come. The cosmic web emerges naturally from the interplay between dark matter's gravitational attraction and the universe's expansion. Over these tens of millions of years, the dark matter assembled into a complex network of intersecting filaments called the cosmic web. Picture how soap bubbles form when you blow them through a bubble wand, creating thin films that connect at various junctions while leaving empty spaces between them. The cosmic web forms similarly, with matter flowing along preferred paths while leaving vast voids relatively empty. These massive, thread-like formations can commonly reach 50 to 80 megaparsecs, with the largest found to date being Kipu at 400 megaparsecs, stretching distances that dwarf even our local group of galaxies. To visualize this scale, imagine the Milky Way as a grain of sand. A typical cosmic filament would stretch from New York to Los Angeles, while the largest known filament, Kipu, would span from Earth to the Moon and back again 16 times. What makes these filaments particularly fascinating is their composition. Dark matter's dominance over everyday matter also means it dominates the filaments of the cosmic web, forming an invisible scaffold along which the universe's structure takes shape. Dark matter, that mysterious substance that doesn't interact with light but comprises most of the universe's mass, creates the invisible highways that guide normal matter, the kind that makes up stars, planets, and ourselves along predetermined paths. The formation process resembles how rivers carve valleys through landscapes over geological time. Just as water naturally flows along paths of least resistance, creating networks of tributaries and main channels, matter in the early universe followed the gravitational landscape created by dark matter, flowing along filaments toward the deepest gravitational wells that would become galaxy clusters. These pathways don't exist in isolation. These filaments and sheets are separated by cosmic voids, vast empty regions that contain very little matter. The relationship between filaments and voids is symbiotic, each defining the other. Filaments exist because matter has been drained from the voids, while voids exist because their matter has flowed into the surrounding filaments. Computer simulations reveal the web's intricate beauty. When astronomers modeled the universe's evolution using supercomputers, dark matter clumped into blobs along narrow filaments with superclusters of galaxies forming a cosmic web at scales on which entire galaxies appear like tiny particles. These simulations show a universe that looks remarkably similar to neural networks in biological systems, suggesting fundamental organizational principles that operate across vastly different scales. The cosmic web's influence extends far beyond its role as cosmic architecture. It actively shapes galaxy formation and evolution, determining where star formation occurs and how galaxies interact with their environment. Galaxies born along filaments experience different evolutionary paths than those in voids, receiving steady streams of fresh gas that fuel continued star formation like cosmic feeding tubes. As we drift through our minds along these invisible highways tonight, consider how the cosmic web represents the universe's attempt to organize itself. From quantum chaos comes cosmic order. From microscopic fluctuations emerge structures visible across billions of light years. The filaments we're exploring represent nothing less than the universe's skeletal system, the hidden framework that supports everything we can see and touch. Mapping something invisible presents unique challenges, like trying to chart ocean currents by watching floating debris or detecting wind patterns by observing how leaves dance through the air. The cosmic web, composed primarily of dark matter that neither emits nor absorbs light, requires similarly indirect methods of detection. Astronomers have become cosmic detectives, piecing together evidence from multiple sources to reveal the universe's hidden scaffold. The most obvious clues come from galaxies themselves. Each bright knot is an entire galaxy, while the purple filaments show where material exists between the galaxies. To the human eye, only the galaxies would be visible, and this visualization allows us to see the strands of material connecting the galaxies and forming the cosmic web. When astronomers map galaxy positions across vast regions of space, they discover that galaxies aren't randomly scattered like stars across Earth's night sky. Instead, they form chains and clusters connected by seemingly empty regions, outlining the underlying dark matter structure like Christmas lights strung along invisible wires. Large-scale galaxy surveys have revolutionized our understanding of cosmic structure. Projects that map millions of galaxies reveal a network of filamentary structures that are analogous to the cosmic web seen in numerical simulations. These surveys show that galaxies trace out the same web-like patterns that computer simulations predict, providing strong evidence that our theoretical understanding matches cosmic reality. But galaxies represent only the tip of the iceberg. The real breakthrough came when astronomers learned to detect the gravitational effects of dark matter filaments. Just as a massive object bends the fabric of space-time, causing light to curve around it, dark matter filaments create subtle gravitational lensing effects that distort the shapes of background galaxies. Think of looking through a bathroom window with textured glass, where the imperfections slightly bend and distort the view beyond. Dark matter filaments create similar distortions, though much more subtle, that require sophisticated analysis to detect. Recent technological advances have enabled direct observations of filament material. After hundreds of hours of observations, an international team of researchers has captured the sharpest ever image of one of these cosmic filaments. These breakthrough observations reveal not just the dark matter scaffold, but also the normal matter, primarily hydrogen gas, that flows along these cosmic highways. Scientists have also discovered ways to detect dark matter filaments using gravitational effects on surrounding galaxies. These are filaments that sit isolated between galaxies and the largest and most hidden portions of the cosmic web. Advanced telescopes and analysis techniques now allow astronomers to measure how the gravity of these invisible structures affects the motion and distribution of nearby galaxies, much like detecting an underground river by observing how surface vegetation grows in patterns above it. The cosmic web reveals itself through temperature signatures as well. Gas flowing along filaments heats up due to compression and gravitational interactions, creating detectable X-ray emissions. Space-based X-ray telescopes can sometimes spot these hot gas trails, revealing the pathways that normal matter follows as it flows along dark matter filaments toward galaxy clusters. Radio telescopes contribute another piece of the puzzle. Astronomers think that cold, dark filaments in deep space snake their way to the galaxies, supplying them with gas, which is fuel for making more stars. Radio observations can detect hydrogen gas in these cold filaments, revealing the fuel supply lines that keep galaxies actively forming new stars. Computer simulations play a crucial role in cosmic web detection. Astronomers create detailed models of how the universe should evolve from initial quantum fluctuations to the present day, then compare these predictions with actual observations. The size of the simulation is a cube with a side length of 134 megaparsecs, or 437 million light-years, allowing researchers to model cosmic web formation across vast scales and verify their theoretical understanding. The most remarkable aspect of cosmic web detection is how multiple independent methods all point to the same underlying structure. Galaxy surveys, gravitational lensing, X-ray observations, radio telescope data, and computer simulations all reveal consistent patterns, like different instruments in an orchestra playing the same cosmic symphony. This convergence of evidence gives astronomers confidence that their maps of the cosmic web accurately reflect the universe's hidden architecture. As we continue our journey along these invisible highways, we begin to appreciate how human ingenuity can reveal the universe's most hidden secrets through careful observation, clever analysis, and patient detective work spanning decades of research. Imagine cosmic rivers flowing through the darkness of space, carrying the raw materials that fuel star formation in galaxies throughout the universe. These aren't rivers of water, but streams of hydrogen gas flowing along dark matter filaments like nutrients through cosmic arteries. Tonight we'll follow these celestial waterways as they deliver the essential ingredients for stellar birth to galactic communities scattered across billions of light years. The process begins in the spaces between galaxies, where primordial hydrogen gas, left over from the Big Bang, drifts through the cosmos at temperatures barely above absolute zero. This intergalactic medium contains roughly half of all normal matter in the universe, waiting to be harvested by hungry galaxies through their dark matter filament connections. Dark matter filaments act like cosmic conveyor belts, channeling this diffuse gas toward gravitational gathering points where galaxies form and evolve. The process resembles how tree roots extend through soil, gathering nutrients from wide areas and concentrating them where they're needed most. This steady supply of fresh material allows galaxies to continue forming new generations of stars for billions of years. The gas doesn't flow gently along these cosmic highways. As it moves toward galaxies, gravitational forces compress and accelerate it, heating the material through friction and gravitational interactions. Think of water flowing down a mountainside, starting as a gentle stream but gaining speed and turbulence as it approaches the valley below. This heating process creates observable signatures that astronomers use to trace the flow of cosmic nutrition. Gas heated to millions of degrees emits X-rays, creating faint but detectable trails that reveal the pathways along which galaxies receive their sustenance. The feeding process varies dramatically depending on a galaxy's environment within the cosmic web. Galaxies located at major filament intersections, where multiple cosmic highways converge, receive abundant supplies of fresh gas and tend to be larger, more massive, and more actively forming stars. These cosmic metropolitan areas bustle with activity and growth fueled by their excellent connectivity to the cosmic supply network. In contrast, galaxies dwelling in cosmic voids, far from major filaments, experience cosmic starvation. These isolated island galaxies must survive primarily on their initial gas reservoirs, like desert settlements cut off from major trade routes. They typically show signs of reduced star formation and may eventually exhaust their fuel supplies. The cosmic web's influence extends beyond simply supplying raw materials. The direction from which gas approaches a galaxy affects its rotation, structure, and ultimate evolution. Gas flowing along filaments tends to approach galaxies from preferred directions, creating the spinning disk structures we observe in spiral galaxies like our Milky Way. Recent observations have revealed the intricate details of this cosmic feeding process. Advanced telescopes can now detect the faint signatures of gas flowing along filaments, showing how galaxies actively draw material from their cosmic web connections. Some galaxies experience feeding frenzies when multiple filaments converge, delivering massive amounts of fresh gas simultaneously. These cosmic banquets can trigger bursts of intense star formation, creating the brilliant starburst galaxies that astronomers observe throughout the universe. At the grandest scales of cosmic architecture, filaments don't simply stretch endlessly through space, but converge at magnificent intersections where the universe's largest gravitationally bound structures take shape. These cosmic crossroads, where multiple dark matter highways meet, create the galaxy clusters that serve as the universe's greatest cities, bustling metropolitan centers where thousands of galaxies gather in gravitational harmony. Picture the intersection of major interstate highways during rush hour, but instead of cars, imagine entire galaxies flowing toward a common destination. These clusters, and the elongated chains of galaxies called filaments which connect them, form a highly complex and anisotropic matter distribution at the megaparsec scale called the cosmic web. These intersections represent the most massive structures in the universe, some containing the equivalent mass of millions of billions of suns concentrated in regions spanning several million light years. The formation of these cosmic intersections follows predictable patterns established by the underlying dark matter distribution. Computer simulations show that nodes naturally develop where multiple filaments meet, much like how cities historically grew at river confluences or mountain pass intersections. The gravitational pull of these developing nodes attracts more matter along the connecting filaments, creating a positive feedback loop that grows increasingly massive structures over cosmic time. As we approach one of these intersections in our imagination, the view transforms dramatically. What began as a journey along relatively sparse filaments suddenly opens into a cosmic megalopolis teeming with galactic activity. Instead of the occasional galaxy encountered along isolated filament stretches, cluster cores contain galaxy densities hundreds of times higher than average cosmic density. The night sky from a planet within such a cluster would blaze with the combined light of thousands of neighboring galaxies, creating perpetual cosmic dawn. The environment within these intersections profoundly affects galaxy evolution. Galaxies entering cluster cores experience gravitational interactions with their numerous numerous neighbors, distorting their shapes and sometimes triggering intense bursts of star formation through close encounters. Think of how traffic patterns change when multiple highway lanes merge into a busy intersection, with vehicles forced into closer proximity and more complex interactions. Cluster cores also contain another remarkable feature: vast clouds of extremely hot gas that fill the space between member galaxies. This intracluster medium, heated to temperatures exceeding 100 million degrees Celsius, emits intense X-ray radiation that makes galaxy clusters among the most luminous X-ray sources in the universe. The gas represents material that has been stripped from member galaxies through gravitational interactions and heated through the cluster's immense gravitational well. The hot intracluster gas creates a hostile environment for star formation in member galaxies. As galaxies move through this superhot medium, the pressure strips away their own cooler gas reserves, like strong cosmic winds removing fuel supplies. This process, called ram pressure stripping, transforms gas-rich spiral galaxies into gas-poor elliptical galaxies over hundreds of millions of years, fundamentally altering their ability to form new stars. Despite the harsh cluster environment, these intersections play crucial roles in cosmic evolution. They serve as laboratories where astronomers can study galaxy interactions, dark matter distribution, and the large-scale structure formation process. The extreme conditions found in cluster cores don't exist anywhere else in the universe, making them natural experiments in extreme cosmic physics. Navigation through these cosmic intersections requires understanding their complex gravitational landscapes. Unlike the relatively straightforward gravitational fields along isolated filaments, cluster cores present chaotic gravitational environments where multiple massive galaxies, dark matter concentrations, and gas clouds all contribute to the total gravitational field. This complexity creates fascinating phenomena like gravitational arcs, where the cluster's combined mass bends light from background galaxies into spectacular curved streaks across the cosmic landscape. Some of the universe's most massive galaxy clusters sit at intersections where 6 or more major filaments converge, creating structures so massive they can bend space-time significantly. These supercluster nodes represent the largest gravitationally bound objects in existence, with masses equivalent to millions of billions of stars concentrated in relatively compact cosmic volumes. The ongoing accretion of matter along filaments ensures that these intersections continue growing throughout cosmic time. Fresh galaxies arrive regularly along the various highways, while streams of intergalactic gas flow toward cluster cores, maintaining these cosmic cities as dynamic, evolving structures rather than static cosmic monuments. As we navigate through these bustling cosmic intersections tonight, we witness the universe's capacity for organization and growth, where the meeting of invisible highways creates visible monuments to gravitational architecture that will endure for cosmic ages. Between the bustling highways of cosmic filaments lie vast territories of almost unimaginable emptiness, the cosmic voids. These immense regions, stretching hundreds of millions of light years across, contain so little matter that a traveler could journey for cosmic ages without encountering a single galaxy. Tonight we drift into these serene cosmic deserts, where the universe reveals its most peaceful and mysterious face. To appreciate the scale of cosmic voids, imagine our local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, as a small pebble. A typical cosmic void would be an empty auditorium large enough to hold millions of such pebbles, yet containing only a handful scattered across its vast volume. These filaments and sheets are separated by cosmic voids, vast empty regions that challenge our understanding of how matter organizes itself on the largest scales. The formation of cosmic voids follows naturally from the same processes that create filaments and clusters. In the early universe, regions that started with slightly lower than average density continued to lose matter as cosmic expansion and gravitational attraction drew material toward denser neighboring regions. Over billions of years, this process carved out enormous cavities in the cosmic web, like soap bubbles forming in cosmic foam, each bubble representing a region where matter has been systematically drained away. The emptiness of cosmic voids is almost beyond human comprehension. While the average density of matter in the universe equals roughly 6 protons per cubic meter, the interiors of cosmic voids contain matter densities 1/10 that value or less. To put this in perspective, the best laboratory vacuums on Earth contain trillions of times more particles per unit volume than the emptiest regions of cosmic voids. Yet cosmic voids aren't entirely empty. Careful observations have revealed sparse populations of void galaxies, isolated island universes that formed in these cosmic deserts despite the challenging low-density environment. These void galaxies tend to be smaller, less massive, and more actively forming stars than their counterparts along filaments and in clusters. They represent cosmic pioneers that managed to gather enough material to form galaxies despite their disadvantageous positions in the cosmic web. The few galaxies that do inhabit cosmic voids experience remarkably different evolutionary paths. Without the steady streams of fresh gas that filament-connected galaxies enjoy, void galaxies must rely primarily on their initial material endowments. However, they also avoid the disruptive galaxy interactions and gas stripping processes common in denser environments, allowing them to evolve in relative isolation like cosmic hermits pursuing independent destinies. Void galaxies often display unusual properties that reveal the importance of environment in galaxy evolution. They tend to be bluer than average, indicating active star formation fueled by undisturbed gas reservoirs. They also show less evidence of past galaxy mergers and interactions, preserving more pristine records of how galaxies form and evolve in undisturbed conditions. The boundaries of cosmic voids aren't sharp walls but gradual transitions where density slowly increases toward the surrounding filaments. These void walls, as astronomers call them, contain elongated chains of galaxies that mark the transition zones between void interiors and the denser filament networks. Think of these boundary regions like coastal areas where ocean meets land, creating unique environments that combine characteristics of both domains. Recent discoveries have revealed that cosmic voids possess their own internal structure. Rather than being perfectly spherical empty bubbles, large voids often contain internal subvoids and connecting tunnels that create complex three-dimensional geometries. Some researchers describe this structure as resembling Swiss cheese, with holes of various sizes connected by tunnels and chambers throughout the cosmic volume. The expansion of the universe affects cosmic voids differently than denser regions. While gravity works to slow expansion in areas where galaxies and dark matter concentrate, cosmic voids experience less gravitational braking and expand faster than the overall cosmic average. This differential expansion gradually makes voids larger and emptier over cosmic time, enhancing the contrast between the densest and most sparse regions of the cosmic web. Cosmic voids also provide unique laboratories for testing theories of gravity and dark energy. The behavior of matter and spacetime in these low-density environments can reveal subtle effects that are masked by stronger gravitational influences in denser regions. Some theories predict that modifications to gravity or dark energy properties would be most readily detectable in void environments. As we drift through these cosmic deserts tonight, we experience the universe's capacity for both organization and emptiness, where the absence of matter creates spaces as magnificent and mysterious as the most densely packed galaxy clusters. Our final destination on tonight's journey brings us home to examine our own cosmic neighborhood and the Milky Way's place within the grand architecture we've been exploring. Far from being cosmic wanderers adrift in empty space, our galaxy and its companions occupy a specific address within the cosmic web, connected to the universe's largest structures through the same dark matter filaments that guide galactic evolution throughout the cosmos. The Milky Way resides within what astronomers call the local sheet, a relatively flat distribution of galaxies that forms part of a larger structure called the local supercluster. Our cosmic neighborhood includes the nearby Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller companion galaxies, all gravitationally bound together in what we call the local group. This family of galaxies occupies a region about 10 million light-years across, a modest cosmic suburb compared to the massive galaxy clusters we encountered earlier. But our local group doesn't exist in isolation. We're connected to the broader cosmic web through filamentary structures that stretch toward the Virgo cluster, a massive galaxy cluster containing over 1,300 member galaxies located about 54 million light-years away. Think of the Virgo cluster as our cosmic downtown, a major metropolitan center connected to our suburban neighborhood through cosmic highways of dark matter and sparse galaxy chains. Recent three-dimensional maps of our cosmic vicinity reveal that we occupy a relatively quiet region of the cosmic web. The local group sits near the edge of what's called the local void, a cosmic desert stretching about 150 million light-years across. This positioning explains some characteristics of our galactic neighborhood. We don't experience the intense galaxy interactions common in cluster cores, but we also don't receive the abundant fresh gas supplies that fuel star formation in galaxies along major cosmic filaments. Our location within this cosmic geography has profoundly influenced the Milky Way's evolution and our existence as conscious observers. The relatively peaceful environment has allowed our galaxy to maintain its spiral structure and continue steady star formation for billions of years. Had we formed in a dense cluster core, gravitational interactions might have disrupted our galaxy's delicate spiral arms and stripped away the gas needed for ongoing star formation, potentially preventing the formation of solar systems like our own. The dark matter halo surrounding the Milky Way connects us to larger cosmic web structures through what astronomers call the cosmic web's feeding filaments. These connections continue supplying our galaxy with small amounts of fresh intergalactic gas, maintaining the fuel supply needed for new star formation. Recent observations using radio telescopes have detected streams of hydrogen gas flowing toward our galaxy along these cosmic pathways, confirming that the Milky Way remains actively connected to the cosmic web's supply network. Our position also affects the night sky we observe from Earth. Because we sit relatively close to the local void, we see fewer bright galaxies in certain directions compared to others. The famous Virgo cluster, visible to telescopes in the constellation Virgo, represents our view toward one of the cosmic web's major nodes. In contrast, looking toward the local void reveals far fewer bright galaxies, creating the impression of empty cosmic desert in those directions. The cosmic web's influence extends to our galaxy's satellite companions. The large and small Magellanic Clouds, visible to southern hemisphere observers as fuzzy patches in the night sky, are small galaxies currently falling into the Milky Way along paths determined by the local dark matter distribution. Their orbits and ultimate fate reflect the gravitational environment created by our position within the cosmic web. Looking toward our cosmic future, the cosmic web will continue shaping our galactic destiny. In approximately 4.5 billion years, the Andromeda Galaxy will collide and merge with the Milky Way, an event orchestrated by the gravitational forces operating within our local group. This cosmic collision, which astronomers have dubbed Andromeda, represents our participation in the ongoing evolution of cosmic web structures. Our journey tonight has taken us from the universe's largest structures down to our own cosmic backyard, revealing how we're intimately connected to the cosmos through invisible threads of dark matter that stretch across billions of light years. The same physical processes that create massive galaxy clusters and cosmic voids also determine our galaxy's characteristics and our existence as observers contemplating the cosmic web's magnificent architecture. From our small planet orbiting an ordinary star in an unremarkable spiral arm, we've discovered our place within the universe's grandest structures, finding that even in cosmic terms, we truly belong to a connected, organized, and wondrous cosmic community. And on that note, our peaceful journey through the cosmic web draws to a close. Tonight we've drifted along invisible highways of dark matter that stretch across billions of light years, connecting every galaxy in existence through a magnificent network that rivals the most complex structures found anywhere in nature. We've witnessed how these ethereal filaments channel the raw materials for star formation, creating cosmic rivers that nourish galactic communities throughout the universe. We've navigated through the bustling intersections where cosmic highways converge into the universe's greatest cities, explored the serene emptiness of cosmic voids, and discovered our own place within this grand architecture. The cosmic web reveals a universe that, despite its apparent chaos, possesses an underlying order and connectivity that links the smallest quantum fluctuations to the largest structures we can observe. Before we can understand how time behaves strangely across the universe, we need to establish the groundwork laid by Albert Einstein in 1905 with his special theory of relativity. This revolutionary framework emerged from a simple but profound observation about light. Einstein recognized that the speed of light in a vacuum is constant for all observers, regardless of their motion. This might seem unremarkable at first, but it leads to extraordinary consequences. Think of it like this. Imagine you're on a train throwing a ball forward. To someone standing on the platform, the ball's speed is your throwing speed plus the train's speed. But light doesn't behave this way. Whether you're standing still or racing through space at tremendous velocity, you'll always measure light traveling at exactly 299,792,458 meters per second. This constancy of light speed forced Einstein to a startling conclusion. If the speed of light never changes, then space and time themselves must be flexible. They form what physicists call spacetime, a four-dimensional fabric that can stretch, compress, and bend. When we move through space, we're actually moving through space-time, and this motion affects how we experience time's passage. The faster you move through space, the slower you move through time. This isn't just theoretical speculation. Particle accelerators routinely observe subatomic particles called muons, which normally decay in microseconds, lasting much longer when accelerated to near light speed. Their internal clocks literally run slower from our perspective. Consider two twins. One stays on Earth while the other travels to a distant star at 90% the speed of light. During the journey, the traveling twin experiences time normally from their own perspective. They eat meals, sleep, and think at regular intervals. However, relative to Earth, their biological processes, their clocks, even their thoughts unfold in slow motion. When they return, they find their Earth-bound sibling has aged significantly more. This time dilation effect becomes more pronounced as speeds approach light speed. At 99% of light speed, time passes about 7 times slower for the traveler compared to a stationary observer. At 99.9%, this factor jumps to over 22. The mathematics are precise and unforgiving. time dilation equals 1 divided by the square root of 1 minus velocity squared divided by light speed squared. GPS satellites orbiting Earth experience this effect daily. They travel at about 14,000 kilometers per hour, causing their onboard clocks to run slightly slower than identical clocks on Earth's surface. Without correcting for this relativistic effect, GPS systems would accumulate errors of several kilometers per day, making navigation impossible. The implications extend far beyond technology. Time dilation reveals that simultaneity, the concept of events happening at the same time, depends entirely on your reference frame. Two events that appear simultaneous to one observer may occur at different times for another observer in motion. This relativity of simultaneity strikes at our deepest intuitions about the nature of time and causality. While motion through space affects time's flow, Einstein's general theory of relativity, published in 1915, revealed an even more surprising truth: gravity itself warps time. This gravitational time dilation occurs because massive objects curve the fabric of spacetime, and time flows more slowly in stronger gravitational fields. Picture spacetime as a stretched rubber sheet. Place a bowling ball in the center, and it creates a depression. Smaller objects placed nearby will roll toward the bowling ball, not because of some mysterious attractive force, but because they're following the curved geometry of the sheet. Similarly, massive objects like stars and planets create curves in spacetime that we experience as gravity. The deeper you are in a gravitational well, the more slowly time passes relative to regions of weaker gravity. On Earth's surface, time runs slightly slower than it does for someone in orbit. The difference is tiny but measurable, about 45 microseconds per day. This might seem negligible, but it's crucial for technologies requiring precise timing. Atomic clocks, accurate to within 1 second over millions of years, can detect these minute differences. In 1976, physicists conducted the Gravity Probe A experiment, launching an atomic clock 22 kilometers high on a rocket. The clock ran faster at higher altitude, exactly as Einstein's equations predicted, confirming gravitational time dilation with remarkable precision. The effect becomes dramatic near extremely massive objects. Consider a neutron star, where matter is compressed to incredible density. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. Near such an object, gravitational time dilation becomes severe. An observer watching someone approach a neutron star would see them moving in increasingly slow motion as they descended deeper into the gravitational field. Black holes represent the extreme case. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from an outside observer's perspective. Someone falling toward a black hole would appear to slow down and freeze at the event horizon, their image growing dimmer and redder as light struggles to escape the intense gravity. Yet from the falling person's viewpoint, they would pass through the event horizon normally, experiencing no unusual time effects locally. This gravitational warping of time has practical consequences throughout the universe. Light climbing out of gravitational wells loses energy and becomes redshifted, its wavelength stretched toward the red end of the spectrum. Astronomers observe this gravitational redshift in light from white dwarf stars, whose intense gravity stretches the wavelengths of photons escaping their surfaces. The Global Positioning System provides a daily demonstration of gravitational time dilation's reality. GPS satellites orbit at about 20,000 kilometers altitude, where Earth's gravity is weaker than at the surface. Their clocks run approximately 45 microseconds per day faster than ground-based clocks due to this reduced gravitational time dilation. Combined with the special relativistic effect of their orbital motion, GPS satellites require constant time corrections to maintain accuracy. Mountain climbers experience gravitational time dilation too, though imperceptibly. At the summit of Mount Everest, nearly 9 kilometers above sea level, time passes about 30 nanoseconds per day faster than at sea level. Over a lifetime, a mountain dweller would age about 90 nanoseconds more than someone at sea level, a difference far too small to notice but perfectly real according to Einstein's equations. One of the most profound implications of Einstein's relativity is that simultaneity, the notion of events happening at the same time, is not absolute but depends entirely on the observer's motion. This relativity of simultaneity fundamentally challenges our intuitive understanding of time and reveals why there's no universal now spanning the cosmos. To understand this concept, imagine 2 lightning bolts striking the ends of a moving train simultaneously, as observed by someone standing on the platform. The platform observer sees both flashes at the same time because they're equidistant from both strikes. However, a passenger on the train, moving toward one lightning bolt and away from the other, will see the forward strike first and the rear strike later. From the train passenger's perspective, the lightning bolts did not strike simultaneously. This isn't merely about the time it takes light to travel. Even accounting for light travel time, the events genuinely occur at different times in the train passenger's reference frame. The relativity of simultaneity means that the temporal order of spatially separated events can differ for observers in relative motion, provided the events are not causally connected. Consider 2 distant stars exploding as supernovae. An astronomer on Earth might observe these explosions as simultaneous events. However, an alien observer traveling at high speed relative to Earth would measure these same explosions occurring at different times. Neither observer is wrong. Simultaneity simply doesn't exist as an absolute concept in our universe. The mathematical relationship governing this effect involves the Lorentz transformation, which describes how space and time coordinates change between reference frames. For 2 events separated by distance and occurring simultaneously in one frame, an observer moving at velocity v will measure a time difference equal to negative velocity times distance divided by the speed of light squared. This formula quantifies how motion destroys simultaneity. This relativity has profound implications for our understanding of causality. Events can only influence each other if they're connected by signals traveling at or below light speed. If 2 events are space-like separated, meaning the distance between them is greater than light could travel in the time between them, then no causal relationship exists. Different observers may disagree about which event occurred first, but this disagreement cannot lead to paradoxes because neither event can influence the other. The concept becomes even more striking when we consider cosmic scales. Imagine an alien civilization in the Andromeda Galaxy, 2.5 million light-years away. If they're moving relative to us at just a few kilometers per second, their notion of simultaneity with events on Earth could differ by thousands of years. What they consider now on Earth might correspond to events in our distant past or future. This relativity of simultaneity explains why faster-than-light communication would create paradoxes. If we could send instantaneous messages across space, different observers would disagree about the order in which messages were sent and received. Some observers might see replies arriving before questions were asked, violating causality and creating logical contradictions. The implications extend to our understanding of free will and determinism. If the future already exists in some reference frames now, what does this mean for our choices and actions? Physicists and philosophers continue debating these deep questions, but the mathematics of relativity clearly shows that simultaneity is observer-dependent, not a fundamental feature of reality. When we expand our perspective to cosmic scales, the relativity of simultaneity and time dilation create a universe where now becomes a meaningless concept beyond our local reference frame. The vast distances between celestial objects, combined with the finite speed of light, mean that our observations of the cosmos are always glimpses into the past, creating a complex temporal landscape across space. Light from the sun takes approximately 8 minutes and 20 seconds to reach Earth. When we observe the sun, we're seeing it as it existed 8 minutes ago, not as it is now. This light travel time effect becomes more dramatic with distance. The nearest star system, Alpha Centauri, appears to us as it was 4 years and 4 months ago. The Andromeda Galaxy shows itself as it existed 2.5 million years in the past. But the situation is far more complex than simple light travel delays. Due to the relativity of simultaneity, different observers throughout the universe would disagree about what constitutes the present moment on Earth. An observer moving toward our solar system at high speed would consider events in Earth's future to be happening now, while an observer moving away would consider events in Earth's past as simultaneous with their present. Consider the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all space. This radiation was emitted when the universe was only 380,000 years old, about 13.8 billion years ago. Every direction we look, we see this ancient light, creating a spherical surface in space-time called the surface of last scattering. This represents the most distant now we can observe, but it's actually the most ancient past accessible to our instruments. Galaxy clusters, the largest gravitationally bound structures in the universe, demonstrate time dilation on cosmic scales. These massive collections of galaxies create significant gravitational fields that slow time relative to the nearly empty voids between them. An observer in a dense galaxy cluster would age slightly more slowly than someone in the cosmic voids, though the effect is small compared to what occurs near black holes or neutron stars. The expansion of the universe adds another layer of complexity to cosmic time. As space itself stretches, distant galaxies recede from us at velocities that increase with distance. The most distant observable galaxies move away at significant fractions of light speed due to cosmic expansion. This motion creates relativistic effects that influence how we observe their evolution and aging processes. Quasars, the brilliant cores of active galaxies powered by supermassive black holes, provide dramatic examples of cosmic time effects. These objects, often billions of light years away, show us the universe as it existed when it was much younger. The light we receive from the most distant quasars began its journey when the universe was less than 1 billion years old, offering windows into cosmic adolescence. The concept of cosmic time, used by cosmologists to describe the universe's age and evolution, represents time as measured by observers at rest relative to the cosmic microwave background. This provides a useful universal reference frame, but it's important to remember that this choice is conventional, not fundamental. The universe itself doesn't have a preferred reference frame or absolute time. Gravitational waves, ripples in spacetime itself, travel at light speed and carry information about cosmic events like black hole mergers and neutron star collisions. When we detect these waves, we're observing spacetime distortions that occurred millions or billions of years ago. The waves themselves experienced no time dilation during their journey, but the sources that created them existed in the distant past of our reference frame. The strange behavior of time across the universe isn't merely theoretical speculation. Modern technology and astronomical observations provide daily confirmation of these relativistic effects. demonstrating how time dilation and simultaneity's relativity shape our understanding of the cosmos and enable crucial technologies we depend upon. The Global Positioning System serves as perhaps the most practical demonstration of relativistic time effects. GPS satellites orbit Earth at approximately 20,000 kilometers altitude, traveling at speeds of about 14,000 kilometers per hour. These satellites experience both special and general relativistic effects that would render the system useless without proper corrections. Special relativity causes the satellite clocks to run slower by about 7 microseconds per day due to their high orbital velocity. Simultaneously, general relativity causes these same clocks to run faster by about 45 microseconds per day because they experience weaker gravity at their orbital altitude. The net effect is that satellite clocks gain about 38 microseconds daily compared to ground-based clocks. This might seem like a tiny discrepancy, but GPS requires nanosecond precision to determine positions accurately. Light travels about 30 centimeters in 1 nanosecond, so timing errors of microseconds would translate to positioning errors of hundreds of meters. Without relativistic corrections, GPS would become increasingly inaccurate, accumulating errors of several kilometers per day. Particle accelerators provide another arena where relativistic time effects are routine. The Large Hadron Collider accelerates protons to 99.999991% of light speed. At these velocities, time dilation factors reach 7,460. Particles that would normally decay in microseconds persist for milliseconds in the laboratory frame, allowing physicists to study their properties and interactions. Muons created by cosmic ray interactions in Earth's upper atmosphere demonstrate natural time dilation. These particles have a mean lifetime of only 2.2 microseconds, which should allow them to travel just 660 meters before decaying. However, muons created 20 kilometers high in the atmosphere regularly reach Earth's surface because time dilation extends their lifetimes in our reference frame. Astronomical observations reveal gravitational time dilation throughout the universe. White dwarf stars, with surface gravities hundreds of thousands of times stronger than Earth's, show gravitational redshift in their spectral lines. Light climbing out of these intense gravitational fields loses energy, its wavelength stretched toward the red end of the spectrum exactly as Einstein's equations predict. Neutron stars provide even more extreme examples. These incredibly dense objects, containing more mass than the Sun compressed into a sphere just 20 kilometers across, create gravitational fields so intense that time dilation becomes readily observable. Pulsars, rotating neutron stars that emit regular radio pulses, show timing variations that include gravitational time dilation effects. The binary pulsar discovered by Russell Hulse and Joseph Taylor provides exquisite confirmation of general relativity. This system consists of 2 neutron stars orbiting each other every 7 hours and 45 minutes. The orbital decay rate, caused by energy loss to gravitational waves, matches Einstein's predictions to within 0.2% accuracy. Very long baseline interferometry, a technique that combines radio telescope observations from around the globe, must account for relativistic effects to achieve its extraordinary precision. The technique can measure celestial positions to microarcsecond accuracy, but this requires careful consideration of time dilation effects at different observatory locations and the relativity of simultaneity across the baseline distances. Atomic clocks have become so precise that they can detect gravitational time dilation over height differences of just centimeters. In 2010, Researchers at the National Institute of Standards and Technology demonstrated that atomic clocks separated by 33 centimeters in height could measure the resulting gravitational time dilation, opening new possibilities for precision tests of relativity and practical applications in geodesy and fundamental physics research. As we reach the culmination of our journey through time's relativistic nature, we must confront a profound truth: the universe has no universal now. This realization fundamentally transforms our understanding of existence, consciousness, and our place in the cosmic order, revealing that our everyday experience of time represents just one local perspective in an infinitely complex temporal landscape. The absence of absolute simultaneity means that events we consider simultaneous on Earth may be separated by vast time intervals when viewed from other reference frames throughout the universe. An alien observer in a distant galaxy, moving at high speed relative to our solar system, might consider events from Earth's Jurassic period to be happening now, while another observer might consider events from our far future as simultaneous with their present moment. This relativity extends to the very concept of existence itself. When we ask whether a distant star exists right now, we're asking a question that has no absolute answer. The star's current state depends entirely on our chosen reference frame and definition of simultaneity. In one frame, the star might have exploded millions of years ago. In another, it continues burning steadily. In yet another, it hasn't even formed yet. The block universe interpretation of relativity suggests that all events, past, present, and future, exist equally in a four-dimensional space-time continuum. From this perspective, time doesn't flow but rather represents a dimension through which conscious observers move, creating the illusion of temporal passage. Your birth, your current moment listening to these words, and your eventual death all exist as equally real events in the space-time block. This view challenges our intuitive understanding of free will and causality. If the future already exists in some sense, are our choices predetermined? Physicists and philosophers continue debating these questions, but the mathematics of relativity clearly indicates that temporal relationships are far more complex than our everyday experience suggests. Consider the cosmic microwave background, that ancient afterglow of the Big Bang visible in every direction we look. This radiation defines a natural reference frame for the universe, allowing cosmologists to speak meaningfully about cosmic time and the universe's age. However, this choice remains conventional rather than fundamental. The universe itself recognizes no preferred reference frame or absolute temporal standard. The expansion of space adds another layer to our temporal confusion. Distant galaxies recede from us not through motion in space, but because space itself stretches between us. This cosmic expansion means that our observable universe represents a sphere of causally connected events, beyond which lie regions that can never influence us or be influenced by us. These causally disconnected regions might as well exist in separate universes from our temporal perspective. Black holes create the most extreme temporal distortions in the known universe. At the event horizon, time dilation becomes infinite from an outside observer's perspective. Information falling into a black hole appears to freeze at the horizon, creating a permanent record of everything the black hole has consumed. Yet from the infalling observer's viewpoint, they pass through the horizon normally, experiencing no unusual time effects until tidal forces tear them apart near the singularity. The search for quantum gravity, a theory unifying general relativity with quantum mechanics, may revolutionize our understanding of time at the smallest scales. Some theories suggest that time itself might be quantized, existing in discrete units rather than flowing continuously. Others propose that time emerges from more fundamental quantum processes, making temporal flow and approximation valid only at macroscopic scales. Despite these mind-bending implications, we must remember that relativity doesn't invalidate our everyday experience of time. Within our local reference frame, causality operates normally, clocks tick steadily, and the future remains unknown until it becomes the present. The strange behaviors of time manifest only when we compare widely separated reference frames or encounter extreme gravitational fields and velocities. The universe's lack of absolute simultaneity ultimately reveals the profound interconnectedness of space and time. We cannot speak meaningfully about cosmic events without specifying our observational perspective. This observer dependence doesn't make physics subjective, but rather highlights the deep relationship between geometry and physical law that Einstein discovered over a century ago. And on that note, we've journeyed through one of the most profound discoveries in human history, the realization that time itself is not the steady, universal constant we once believed it to be. From the time dilation experienced by GPS satellites to the infinite temporal distortions at black hole event horizons, from the relativity of simultaneity that destroys any universal now to the gravitational warping of time itself, we've seen how Einstein's insights continue to reshape our understanding of reality. The next time you glance at a clock or contemplate what's happening right now somewhere else in the universe, remember that you're experiencing just one local perspective in an infinitely rich temporal tapestry. Time flows differently throughout the cosmos, and simultaneity exists only within our limited reference frame. In the grand cosmic perspective, every moment that has ever existed or ever will exist shares an equal claim to reality. To understand how neutron stars create their celestial music, we must first witness their dramatic birth. When a supermassive star with an initial mass greater than about 8 times that of the Sun begins to die, it forms a red supergiant before exploding as a supernova. This explosion is one of the most violent events in the universe, releasing more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. But within this cosmic violence lies the creation of something extraordinary. When the star's core collapses during the supernova, gravity becomes so intense that it crushes protons and electrons together, forcing them to merge into neutrons. Imagine taking all the mass of our Sun and squeezing it into a sphere only 12 miles across. The enormous density of a neutron star means a teaspoon of neutron star material would weigh 10 million tons. To put this in perspective, a normal-sized matchbox containing neutron star material would have a weight of approximately 3 billion tons. This process creates matter so dense that it exists nowhere else in the observable universe. The material becomes what physicists call degenerate matter, where the normal rules of physics as we know them begin to break down. Picture trying to fit all the people on Earth into a single city block, and you begin to approach the level of compression occurring inside these stellar remnants. During this collapse, 2 crucial properties are preserved and intensified. First, the original star's rotation speeds up dramatically, much like a figure skater pulling in their arms during a spin. A star that once rotated every few weeks might become a neutron star spinning hundreds of times per second. The fastest spinning neutron star on record, found in a globular cluster of stars located around 28,000 light-years from Earth, spins around 716 times per second. Second, the star's magnetic field becomes concentrated into an area millions of times smaller, amplifying its strength to incomprehensible levels. Neutron stars have exceptionally strong magnetic fields around them, often billions or even trillions of times stronger than Earth's protective magnetic field. To visualize this, imagine Earth's gentle magnetic field, barely strong enough to move a compass needle, amplified until it could lift a car from miles away. These two properties, ultra-rapid rotation and incredibly powerful magnetic fields, work together to transform the neutron star into something remarkable. A cosmic beacon that sweeps beams of radiation across space with the precision of an atomic clock. The neutron star's magnetic field acts like a funnel, channeling charged particles from its surface into narrow beams that shoot out from its magnetic poles. As the neutron star spins, these beams sweep across space like the rotating beam of a lighthouse. When one of these beams happens to point toward Earth during its rotation, our radio telescopes detect a brief pulse of radio waves. This creates the rhythmic pattern that gives these objects their name, pulsars, short for pulsating stars, though they are not actually pulsating at all but simply rotating. The birth of each neutron star represents a cosmic recycling program of extraordinary proportions. The heavy elements foraged in the original star's nuclear furnace are scattered across space by the supernova explosion, eventually becoming the building blocks for new stars, planets, and perhaps even life itself. Meanwhile, the collapsed core continues its eternal dance, spinning and pulsing, creating a cosmic metronome that can keep more accurate time than our most precise atomic clocks here on Earth. Understanding how neutron stars create their signature pulses requires examining their remarkable internal structure and the invisible architecture of their magnetic fields. These objects are far from simple. They are among the most complex and exotic structures in the universe, with physics that pushes the boundaries of our understanding. The combination of intense gravity, high temperature, and extreme density makes neutron stars like nothing we can produce on Earth. At their surface, gravity is so strong that if you could somehow stand there, you would weigh about 1 billion times more than you do on Earth. The surface itself is thought to be a crystalline lattice of atomic nuclei, creating what might be the strongest material in the universe, trillions of times harder than diamond. Beneath this surface lies a landscape that defies imagination. The outer crust contains nuclei arranged in a crystal lattice, immersed in a sea of electrons. As we journey deeper, the density increases so dramatically that normal atomic nuclei begin to merge and elongate into structures that physicists poetically call nuclear pasta, forming shapes that resemble lasagna sheets, spaghetti strands, and gnocchi balls, depending on the precise conditions. The core of a neutron star remains one of physics' greatest mysteries. Here, matter exists in forms that we cannot replicate or fully understand. Some theories suggest the presence of exotic particles that exist nowhere else in the universe, strange quarks, hyperons, or even more exotic forms of matter that challenge our understanding of the fundamental building blocks of reality. But it is the neutron star's magnetic field that creates the cosmic music we observe. Pulsars have very strong magnetic fields which funnel jets of particles out along the two magnetic poles. These accelerated particles produce very powerful beams of light. Often, the magnetic field is not aligned with the spin axis, so those beams of particles and light are swept around as the neutron star rotates. Picture a bar magnet spinning inside a globe filled with charged particles. The magnetic field lines stretch from one pole to the other, but they are not aligned with the rotation axis. Instead, they are tilted at an angle, creating a complex, twisted structure that rotates with the star. This misalignment is crucial because it creates the lighthouse effect that allows us to detect these objects from across the galaxy. The magnetic field acts as a cosmic particle accelerator. A gamma-ray pulsar is a compact neutron star that accelerates charged particles to relativistic speeds in its extremely strong magnetic field. Near the magnetic poles, particles are accelerated to nearly the speed of light, creating intense beams of radiation that extend far into space. These beams are not simply points of light, but rather complex cones of radiation that include radio waves, optical light, X-rays, and gamma rays. The radio waves that we detect on Earth are just one small part of this electromagnetic symphony. The beams are so narrow and intense that they can remain detectable across thousands of light years, like cosmic searchlights cutting through the darkness of space. The precision of these rotating beams is extraordinary. Some pulsars maintain timing accuracy that rivals or exceeds our best atomic clocks. This reliability comes from the neutron star's immense rotational inertia. Once spinning, these objects resist any change to their rotation with tremendous persistence. Their enormous density means that even tiny changes in their structure or magnetic field take enormous amounts of energy to accomplish. The magnetic field structure itself is dynamic and evolving. Over millions of years, the field gradually weakens as energy is radiated away, and the pulsar's rotation slowly decreases. This creates an evolutionary sequence where young, rapidly spinning pulsars with strong magnetic fields gradually age into slower, quieter objects that eventually fade from our ability to detect them. The cosmic music of neutron stars manifests most clearly in the radio waves that sweep across our galaxy, creating patterns of extraordinary beauty and precision. Pulsars are magnetized neutron stars that appear to emit periodic short pulses of radio radiation with periods between 1 and 4 milliseconds and 8 and 5 seconds. This range encompasses a remarkable variety of cosmic rhythms, from rapid-fire drumbeats to slow, stately pulses that mark time like a grandfather clock in the cosmos. The mechanism behind this radio emission remained a mystery for decades after the first pulsar was discovered in 1967. In 1967, shortly before the discovery of pulsars, Franco Pacini suggested that a rotating neutron star with a magnetic field would emit radiation, and even noted that such energy could be pumped into a supernova remnant around a neutron star, such as the Crab Nebula. Recent research has finally begun to unravel this cosmic mystery. The wobbling electric fields in the presence of the pulsar's powerful magnetic fields then result in electromagnetic waves that escape into space. Using plasma simulations, the researchers found that these electromagnetic waves match radio waves observed from pulsars. This breakthrough helps us understand how the immense magnetic fields and rapid rotation work together to generate the radio signals we detect. The process begins in the neutron star's magnetosphere, a region of space dominated by the star's magnetic field. This invisible structure extends thousands of miles into space, creating a complex playground for charged particles. As the neutron star rotates, it drags this magnetic field with it, creating electric fields that accelerate particles to incredible speeds. Near the magnetic poles, conditions become extreme. The rotating magnetic field creates gaps where particles can be accelerated to nearly the speed of light. As these relativistic particles spiral along magnetic field lines, they emit synchrotron radiation across the electromagnetic spectrum. The radio waves we detect are created through a complex cascade process, where high-energy particles create pairs of electrons and positrons, which in turn produce the radio emission through collective plasma effects. The resulting radio pulses carry detailed information about their journey through space. As radio waves travel from the pulsar to Earth, they encounter the thin plasma that fills interstellar space. This plasma causes different radio frequencies to travel at slightly different speeds, creating a phenomenon called dispersion. Lower frequency radio waves arrive at Earth slightly later than higher frequencies from the same pulse. By measuring this time delay, astronomers can calculate exactly how much plasma the radio waves encountered on their journey, providing a direct measurement of the density of interstellar space. This technique has revealed the structure of our galaxy's interstellar medium in exquisite detail, showing bubbles of hot gas blown by stellar winds and the aftermath of ancient supernovae. The radio signals also reveal the pulsar's motion through space. As the neutron star moves toward or away from us, the Doppler effect shifts the arrival time of pulses, allowing astronomers to measure velocities with incredible precision. Some pulsars are moving through space at hundreds of miles per second, kicked into motion by the asymmetric explosion that created them. Perhaps most remarkably, the timing of pulsar signals is so precise that they can be used as cosmic clocks. A millisecond pulsar is one with a rotational period between 1 and 10 milliseconds, or from 60,000 to 6,000 revolutions per minute. These rapidly spinning objects maintain their rhythm with such accuracy that they can be used to detect gravitational waves, minute ripples in spacetime itself that cause tiny changes in the arrival times of pulsar signals. The radio symphony of pulsars thus provides us with a window into some of the most fundamental aspects of physics and astronomy, from the structure of matter at nuclear densities to the nature of space and time itself. The magnetic fields of neutron stars orchestrate some of the universe's most spectacular phenomena, creating structures and processes that exist nowhere else in nature. These fields are not static entities but dynamic, evolving systems that shape the space around the neutron star and control the flow of matter and energy in ways that continue to astound astronomers and physicists. To appreciate the scale of these magnetic fields, consider that Earth's magnetic field, which protects us from harmful solar radiation and guides compass needles, measures about half a Gauss at our planet's surface. A typical neutron star's magnetic field ranges from 1 billion to 1 trillion Gauss, with some exotic objects called magnetars reaching fields of up to 1 quadrillion Gauss. At such intensities, the magnetic field contains enough energy to power our sun for millions of years. These fields create a complex three-dimensional structure around the neutron star called the magnetosphere. Unlike Earth's relatively simple dipole field, which resembles the pattern around a bar magnet, neutron star magnetospheres are twisted, dynamic regions where the normal rules of physics are pushed to their limits. The rapidly rotating magnetic field drags plasma along with it, creating currents that flow along invisible field lines like traffic on cosmic highways. The interaction between rotation and magnetic field creates distinct regions within the magnetosphere. Close to the neutron star, within the light cylinder, a theoretical boundary where the rotational velocity would equal the speed of light, the magnetic field forces plasma to rotate with the star. Beyond this boundary, field lines stretch and reconnect, creating open zones where particles can escape into space. At the magnetic poles, the field lines converge and create natural particle accelerators. Here, the combination of the strong magnetic field and the electric field generated by rotation creates gaps where particles gain enormous energies. Electrons and positrons are accelerated to speeds approaching that of light, creating cascades of secondary particles through interactions with intense gamma rays. The magnetic field also controls how matter falls onto the neutron star. In binary systems where a neutron star orbits a companion star, material from the companion can be captured by the neutron star's gravity. However, this material cannot fall directly onto the surface. Instead, the magnetic field funnels it toward the magnetic poles, creating hot spots where the infalling matter crashes into the neutron star's surface at tremendous speeds. This process creates some of the most energetic phenomena in the universe. As matter accelerates toward the neutron star, it heats up to temperatures of millions of degrees, emitting X-rays and gamma rays. The hot spots at the magnetic poles create beams of high-energy radiation that sweep across space as the neutron star rotates, much like the radio beams, but at much higher energies. The magnetic field structure is not permanent but evolves over time through several mechanisms. All pulsars slow down gradually as they age. The radiation emitted by a pulsar is jointly powered by its magnetic field and its spin. As energy is carried away by electromagnetic radiation, both the rotation rate and magnetic field strength gradually decrease over millions of years. Some neutron stars experience sudden changes in their magnetic field configuration through events called magnetar flares. These are thought to occur when the neutron star's crust suddenly cracks under magnetic stress, allowing field lines to reconnect in a new configuration. The energy released in these events can be detected across the galaxy, briefly outshining all other X-ray sources in the sky. The magnetic field also plays a crucial role in the neutron star's long-term evolution. Young pulsars with strong magnetic fields eventually evolve into millisecond pulsars through a process of magnetic field decay and spin up by matter accretion from a companion star. This evolutionary pathway connects the rapid pulsars we observe to the slower, older objects that represent their eventual fate. The rhythmic pulses of neutron stars have transformed our understanding of time itself, creating cosmic chronometers that surpass even our most precise atomic clocks in their stability and accuracy. These celestial timepieces provide insights not only into the nature of neutron stars themselves, but also into fundamental physics and the structure of the universe around us. The discovery that pulsars could serve as extraordinarily precise clocks came as a surprise to early astronomers. The first pulsars were discovered through their extremely regular pulses of radio waves, but it took time to realize just how regular these signals could be. Some millisecond pulsars maintain timing accuracy that allows astronomers to predict the arrival of pulses years in advance with precision measured in microseconds. This extraordinary regularity stems from the neutron star's immense rotational inertia. The star's incredible density means that once it is spinning, enormous forces are required to change its rotation rate. Think of trying to slow down a massive flywheel versus stopping a spinning coin. The neutron star's rotation is so stable that even earthquakes on its surface, involving the sudden rearrangement of matter weighing as much as mountains on Earth, produce only tiny, measurable changes in the pulse timing. These timing variations tell fascinating stories about the neutron stars themselves. Occasionally, a pulsar will suddenly speed up slightly in an event called a glitch. These glitches are thought to occur when the neutron star's crust, which rotates slightly slower than its interior, suddenly cracks and readjusts to match the faster rotation of the core. The resulting change in pulse timing provides direct evidence of the neutron star's internal structure and the exotic physics occurring within. The precision of pulsar timing has opened up entirely new fields of astronomy. By carefully monitoring the arrival times of pulses over years or decades, astronomers can detect incredibly subtle effects. When a pulsar is part of a binary system, orbiting around another star, the gravitational field of the companion causes small but measurable changes in the pulse arrival times as the pulsar moves toward and away from Earth in its orbit. These orbital measurements have provided some of the most stringent tests of Einstein's theory of general relativity. The first indirect evidence for gravitational waves came from observations of a binary pulsar system, where the two stars are spiraling inward as they lose energy to gravitational radiation. The rate of orbital decay matched Einstein's predictions with remarkable precision, earning the discoverers a Nobel Prize and confirming one of the theory's most subtle predictions. Pulsar timing arrays, networks of telescopes monitoring dozens of millisecond pulsars simultaneously have become instruments for detecting gravitational waves directly. When gravitational waves from distant sources pass through our region of space, they cause tiny changes in the distances between Earth and the pulsars, showing up as correlated timing variations across multiple pulsars. This technique is sensitive to gravitational waves with much longer wavelengths than can be detected by ground-based instruments. The variety of pulsar rhythms spans an enormous range. Young pulsars typically rotate every few seconds, their powerful magnetic fields gradually slowing their rotation as energy is radiated away. Middle-aged pulsars may pulse once per second, while the fastest millisecond pulsars complete hundreds of rotations in a single second. Each category provides different insights into neutron star physics and evolution. Some pulsars exhibit complex timing behavior that reveals additional layers of physics. Intermittent pulsars switch on and off unpredictably, while others show gradual changes in pulse shape and intensity. These variations reflect changes in the magnetospheric processes that create the radio emission, providing laboratories for studying plasma physics under conditions impossible to recreate on Earth. The study of pulsar timing continues to yield surprises and discoveries. Recent observations have revealed pulsars with timing noise, random fluctuations that may result from turbulence in the neutron star's magnetosphere or changes in its internal structure. As we reach the end of our journey through the realm of neutron star music, we find ourselves contemplating objects that represent some of the most extreme physics in the universe while simultaneously providing us with tools to explore the cosmos with unprecedented precision. These gentle giants, despite their violent births and incredible densities, offer us a peaceful, rhythmic connection to the fundamental processes that govern reality itself. The radio telescopes that capture pulsar signals are among humanity's most sensitive listening devices. They can detect signals so faint that the total energy collected from all pulsars ever observed would not be enough to lift a feather. Yet within these whisper-quiet signals lies information about physics at the edge of our understanding. Each pulse carries data about the neutron star's magnetic field, its rotation, its motion through space, and even the structure of the interstellar medium through which the radio waves have traveled. Modern pulsar astronomy continues to reveal new wonders. Recent observations have found at least 2 neutron stars with a mass about twice the mass of the Sun, perhaps even more. These massive neutron stars challenge our understanding of how matter behaves at nuclear densities and provide crucial constraints on the equation of state of ultra-dense matter. The discovery of neutron star mergers through gravitational wave detections has opened another chapter in understanding these objects. The gravitational waves produced in a merger of 2 neutron stars provide rich information on the structure of these exotic objects, in which a mass roughly comparable to that of the Sun is squeezed into a sphere with a radius of about 6 miles. These cataclysmic events create conditions even more extreme than those inside individual neutron stars, forging heavy elements and providing laboratories for studying matter under the most intense conditions possible. The relationship between neutron stars and their environment continues to surprise astronomers. The magnetic fields channel matter surrounding the neutron star into light-emitting jets, much like those we see near some black holes. This similarity between neutron star and black hole phenomena suggests deep connections in how compact objects interact with their surroundings, despite their very different natures. Looking toward the future, next-generation radio telescopes promise to detect thousands of new pulsars, creating a galactic network of cosmic chronometers. These surveys will map the structure of our galaxy in 3 dimensions, trace the history of stellar formation and death, and perhaps detect exotic objects like pulsar black hole binary systems that could provide even more stringent tests of fundamental physics. The search for extraterrestrial intelligence has also adopted pulsar timing as a potential communication medium. The incredible precision and stability of millisecond pulsars could, in principle, be used to encode information in timing variations detectable across interstellar distances. Whether nature or intelligence might employ such methods remains an open question, but it illustrates the profound impact these objects have had on our thinking about communication and information in the cosmos. As space-based telescopes become more sophisticated, we are beginning to observe pulsars across the entire electromagnetic spectrum simultaneously. This comprehensive view reveals the full complexity of neutron star magnetospheres and the processes that create their multi-wavelength emissions. Future missions may even detect individual neutron star oscillations, opening up neutron star seismology as a new field of study. The gentle giants we have explored tonight represent more than scientific curiosities. They are natural laboratories where the laws of physics are tested under conditions we can never hope to recreate artificially. They are cosmic lighthouses guiding our understanding of space-time, gravity, and the fundamental nature of matter itself. And they are timekeepers, marking the passage of cosmic ages with precision that humbles our greatest technological achievements. And on that note, we conclude our peaceful exploration of neutron star symphonies. These cosmic musicians will continue their ancient songs long after our sun has faded, their radio pulses carrying messages about the deep physics of our universe to any who have the technology and patience to listen. When you look up at the night sky, you're not seeing the universe as it is right now. You're witnessing a cosmic museum where every point of light represents a different moment in the universe's past. This is because light, despite traveling at the fastest speed possible in our universe, still takes time to journey across the vast distances between stars and galaxies. Think of light like a message in a bottle, cast into the cosmic ocean billions of years ago. When we catch these bottled messages with our telescopes, we're reading letters from the universe's distant past. The nearest star to our sun, Proxima Centauri, sends us light that's already 4 years old by the time it reaches our eyes. But this is nothing compared to the ancient messages we receive from distant galaxies. The speed of light is approximately 300,000 kilometers per second. While this seems incredibly fast, the universe is so enormously vast that even light takes billions of years to travel from the most distant observable objects to our telescopes. A light year, the distance light travels in 1 year, equals about 9.5 trillion kilometers. When astronomers say a galaxy is 10 billion light years away, they mean we're seeing that galaxy as it appeared 10 billion years ago. This cosmic time delay creates what astronomers call a light travel time effect. It transforms our telescopes into time machines, allowing us to observe the universe at different epochs simply by looking at objects at different distances. The farther away an object is, the further back in time we're seeing it. This principle forms the foundation of cosmic archaeology, where light becomes our primary tool for excavating the universe's history. The most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old, compared to its current age of about 13.8 billion years. These ancient galaxies show us a cosmos that was dramatically different from today, filled with active star formation and cosmic violence that shaped the large-scale structure we observe in the modern universe. Modern telescopes function as sophisticated time machines, each one designed to capture and analyze the ancient photons that have traveled across cosmic distances. The Hubble Space Telescope, launched in 1990, revolutionized our ability to peer deep into cosmic history. Its position above Earth's atmosphere allows it to collect pristine images of galaxies as they appeared billions of years ago. When astronomers point Hubble toward a seemingly empty patch of sky and collect light for days or weeks, something magical happens. What initially appears as cosmic darkness gradually reveals itself to be filled with thousands of galaxies, each one an island universe containing hundreds of billions of stars. These deep field observations, like the famous Hubble Deep Field taken in 1995, show us galaxies so distant that their light has been traveling toward us for most of the universe's lifetime. The James Webb Space Telescope, which began operations in 2022, has pushed our cosmic vision even further into the past. Its massive mirror and infrared sensitivity allow it to detect the faintest whispers of light from the universe's first galaxies. Webb can observe galaxies that formed when the universe was only a few 100 million years old, during what astronomers call the cosmic dawn. Ground-based telescopes also contribute to this cosmic archaeology. Observatories like the Atacama Large Millimeter Array in Chile can detect radiation from dust and gas in distant galaxies, revealing the raw materials that fuel star formation across cosmic time. The Keck Observatory in Hawaii uses adaptive optics to peer through Earth's turbulent atmosphere, creating images so sharp they rival those from space. Each telescope observes different wavelengths of light, providing unique insights into cosmic history. Optical telescopes reveal the starlight from ancient galaxies, while radio telescopes detect the signatures of hydrogen gas that fuels cosmic evolution. Infrared telescopes can peer through cosmic dust clouds, revealing hidden star formation in the universe's past. Together, these instruments create a comprehensive picture of how the universe has evolved from its earliest epochs to the present day. Every galaxy carries within its starlight a detailed biography of its formation and evolution. Astronomers have developed sophisticated techniques to decode these stellar stories, reading the cosmic equivalent of tree rings in the light spectra of distant galaxies. This process, called stellar archaeology, reveals not just when stars formed, but under what conditions and from what materials. The color of a galaxy tells us about the ages of its stars. Blue galaxies are typically filled with young, hot stars that burn brightly but briefly, indicating ongoing star formation. Red galaxies, by contrast, are dominated by older, cooler stars, suggesting that their most vigorous star-forming days are behind them. By studying how the colors of galaxies change with cosmic time, astronomers can trace the universe's star formation history. Spectroscopy allows astronomers to dissect galactic light into its component wavelengths, revealing the chemical fingerprints of stars and gas within distant galaxies. Each element absorbs and emits light at specific wavelengths, creating a unique signature that astronomers can identify even across billions of light years. These spectral lines tell us about the metals forged in ancient stars and scattered into space by stellar explosions. The chemical composition of distant galaxies reveals the gradual enrichment of the universe with heavy elements. The first stars in the universe were made almost entirely of hydrogen and helium, the primordial elements created in the Big Bang. As these stars existed and died, they forged heavier elements in their cores and scattered them into space through stellar currents and supernova explosions. Each successive generation of stars inherited this chemical legacy, gradually building up the periodic table of elements we see today. By comparing the chemical compositions of galaxies at different cosmic times, astronomers can trace this process of cosmic chemical evolution. Distant galaxies show us a universe with much lower concentrations of heavy elements, while nearby galaxies reveal the cumulative result of billions of years of stellar nucleosynthesis. This chemical archaeology helps us understand not just how galaxies evolved, but how the universe itself became capable of forming the complex chemistry necessary for planets and life. The universe's large-scale structure resembles a vast cosmic web, with galaxies strung along filaments of dark matter like dewdrops on spider silk. This cosmic architecture emerged from tiny density fluctuations in the early universe, which grew over billions of years through gravitational attraction. By studying how galaxies are distributed across cosmic time, astronomers can trace the growth of this cosmic web and understand how it shaped galactic evolution. Dark matter, an invisible substance that outweighs ordinary matter by more than 5 to 1, provides the gravitational scaffolding for galaxy formation. Although we cannot see dark matter directly, we can observe its effects on the distribution and motion of galaxies. Computer simulations that include dark matter successfully reproduce the observed large-scale structure of the universe, confirming its crucial role in cosmic architecture. In the early universe, small fluctuations in dark matter density began to collapse under their own gravity, forming what astronomers call dark matter halos. Ordinary matter fell into these gravitational wells, where it cooled and condensed to form the first stars and galaxies. This process of hierarchical structure formation means that smaller objects formed first, then merged and grew into larger structures over cosmic time. The cosmic web continues to influence galaxy evolution today. Galaxies located in dense galaxy clusters experience environmental effects that can shut down star formation, while galaxies in the sparse cosmic voids continue forming stars at a steady rate. By studying how galaxy properties depend on their environment at different cosmic epochs, astronomers can understand how the cosmic web shapes galactic evolution. Gravitational lensing provides another window into cosmic structure formation. When light from a distant galaxy passes near a massive foreground object, the gravity of that object bends the light rays, creating distorted or multiple images of the background galaxy. This cosmic magnifying glass effect allows astronomers to study galaxies that would otherwise be too faint to observe, extending our view even deeper into cosmic history. Strong gravitational lenses can magnify background galaxies by factors of 10 or more, revealing details about star formation and structure in the very early universe. At the hearts of most galaxies lurk supermassive black holes, cosmic giants containing millions or billions of times the mass of our Sun. These enigmatic objects play a crucial role in galactic evolution, regulating star formation and shaping the properties of their host galaxies across cosmic time. The discovery of supermassive black holes in distant galaxies has revealed their importance in the cosmic story. When material falls into a supermassive black hole, it forms an accretion disk that heats up and glows brilliantly, creating some of the most luminous objects in the universe. These active galactic nuclei, or quasars, can outshine their entire host galaxies, making them visible across enormous cosmic distances. The light from quasars provides a beacon that allows astronomers to study galaxy formation in the very early universe. The most distant quasars, observed when the universe was less than 1 billion years old, pose a puzzle for astronomers. How did supermassive black holes grow so large so quickly in the young universe? This question drives ongoing research into the formation of the first black holes, which may have formed directly from the collapse of massive gas clouds in the early universe, bypassing the normal stellar evolution process. Supermassive black holes and their host galaxies appear to evolve together in a cosmic dance. Observations reveal tight correlations between black hole masses and properties of their host galaxy bulges, suggesting that black hole growth and galaxy formation are intimately connected. This relationship appears to hold across cosmic time, indicating that the coevolution of black holes and galaxies has been ongoing since the early universe. The energy output from active supermassive black holes can have profound effects on their host galaxies. Powerful jets and currents driven by black hole accretion can heat and expel gas from galaxies, shutting down star formation in a process astronomers call feedback. This mechanism may explain why the most massive galaxies in the universe are typically red and dead, having exhausted their star-forming fuel through black hole-driven currents. By studying how this feedback process has operated across cosmic history, astronomers gain insights into one of the key mechanisms that shapes galactic evolution. The period known as cosmic dawn represents one of the most fascinating chapters in the universe's history, when the first stars ignited and began to illuminate the cosmic dark age. This epoch, occurring roughly 100 to 500 million years after the Big Bang, marks the transition from a universe filled only with dark matter and neutral hydrogen gas to one beginning to sparkle with the light of newborn stars. Before the first stars formed, the universe existed in what astronomers call the Dark Age. During this time, the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen atoms, making the universe transparent to light for the first time since the Big Bang. However, there were no stars yet to produce that light, leaving the universe in a state of cosmic twilight, illuminated only by the fading afterglow of the Big Bang itself. The first stars, known as population 3 stars, were unlike any stars we see today. These primordial giants formed from gas clouds composed almost entirely of hydrogen and helium, lacking the heavier elements that help modern stars regulate their formation. Without these cooling agents, the first stars grew to enormous sizes, perhaps 100 to 300 times more massive than our Sun. These stellar behemoths burned brilliantly but briefly, existing only a few million years before exploding as spectacular supernovae. When these first stars ignited, they began the process of cosmic reionization, gradually transforming the neutral hydrogen gas that filled the universe back into ionized plasma. Picture the universe as a cosmic fog slowly being burned away by the light of the first stars. This process took hundreds of millions of years to complete, creating bubbles of ionized gas around early star-forming regions that gradually merged until the entire universe became transparent to ultraviolet light. The James Webb Space Telescope has provided our clearest glimpses yet of this cosmic dawn period. Webb's infrared vision can penetrate the dust that often obscures early star formation, revealing galaxies that formed when the universe was only 3 to 4% of its current age. These observations have revealed that galaxies formed and grew more rapidly in the early universe than many theoretical models predicted, suggesting that the processes of star formation and galaxy assembly were more efficient in the cosmic past than astronomers initially thought. The chemical signatures left by the first stars continue to influence cosmic evolution today. Every element heavier than lithium in the periodic table was forged in the nuclear furnaces of stars or created in stellar explosions. The first supernovae scattered these newly created elements into space, enriching the gas clouds that would form the next generation of stars. This process of cosmic chemical evolution continues today, with each stellar generation building upon the elemental legacy of its predecessors. The field of cosmic archaeology stands at the threshold of revolutionary discoveries, as new telescopes and techniques promise to push our cosmic vision even deeper into the universe's past. The James Webb Space Telescope has already begun to transform our understanding of early galaxy formation, revealing mature galaxies at cosmic times when the universe was supposed to be filled only with small, irregular star-forming systems. Future ground-based telescopes will dwarf current observatories in their light-gathering power. The extremely large telescope, currently under construction in Chile, will have a mere 39 meters across, providing unprecedented resolution and sensitivity for studying distant galaxies. This cosmic giant will be able to directly observe the first stars that formed in the universe, ending the cosmic dark age and beginning the process of cosmic reionization. Space-based missions planned for the coming decades will open new windows into cosmic history. The Nancy Grace Roman Space Telescope will survey enormous volumes of space, mapping the cosmic web and measuring how dark energy has affected cosmic expansion over time. The proposed Large Ultraviolet Optical Infrared Surveyor mission would provide even greater sensitivity than Webb, potentially capable of studying the atmospheres of Earth like planets around nearby stars. Gravitational wave astronomy represents a completely new approach to cosmic archaeology. As Advanced Laser Interferometer Gravitational Wave Observatory and similar detectors become more sensitive, they will detect mergers of black holes and neutron stars throughout cosmic history, providing insights into stellar evolution and compact object formation that complement traditional electromagnetic observations. The planned space-based Laser Interferometer Space Antenna mission will detect gravitational waves from supermassive black hole mergers, revealing how these cosmic giants grew and merged across cosmic time. Multi-messenger astronomy, which combines observations of light, gravitational waves, and cosmic rays from the same sources, promises to provide a more complete picture of cosmic evolution. Future surveys will automatically identify transient events across the entire sky, enabling rapid follow-up observations that can capture the fleeting signatures of cosmic catastrophes. Machine understanding algorithms will sift through this flood of data, identifying patterns and anomalies that human astronomers might miss. And on that note, we complete our gentle journey through cosmic archaeology, where ancient light serves as our guide to understanding the universe's vast history. We've explored how telescopes become time machines, how galaxies carry the stories of their formation written in starlight, and how the cosmic web provides the stage upon which the cosmic drama unfolds. From the chemical evolution traced in stellar spectra to the coevolution of supermassive black holes and their host galaxies, we've seen how astronomers have become cosmic detectives, piecing together the universe's biography from the faintest whispers of ancient light. The future promises even more remarkable discoveries as new telescopes and techniques push our cosmic vision ever deeper into the universe's past. As we stand at this moment in cosmic history, we find ourselves uniquely positioned to witness the universe's story unfolding before our eyes. Each night, ancient photons that began their journey when the cosmos was young finally reach our world, carrying with them the secrets of stellar nurseries, galactic collisions, and the birth of the very elements that make up our bodies. We are quite literally made of stardust, forged in the nuclear furnaces of ancient suns and scattered across the cosmos by stellar explosions that occurred billions of years before our solar system even existed. The profound beauty of cosmic archaeology lies not just in its scientific discoveries, but in how it connects us to the greater cosmic story. When we observe a galaxy 10 billion light-years away, we're not just seeing distant stars, we're witnessing our own cosmic ancestry. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all were created in the hearts of stars that died long before our sun was born. This cosmic perspective reminds us that we are not observers standing outside the universe looking in, but rather participants in an ongoing cosmic evolution that spans nearly 14 billion years. Perhaps most remarkably, through cosmic archaeology we've discovered that the universe itself is still writing its story. Star formation continues in distant galaxies, black holes still merge and grow, and the cosmic web continues to evolve under the influence of dark energy. We exist during a brief but magnificent chapter in this cosmic tale, blessed with the intelligence and curiosity to read the universe's memory written in starlight. In studying the cosmos, we ultimately study ourselves, for we are the universe becoming aware of its own existence, capable of looking back through time and marveling at the incredible journey that brought us to this moment of cosmic consciousness. The story of the Great Attractor begins in the 1970s, when astronomers were meticulously mapping the cosmic microwave background, the ancient light that fills our universe. Think of this background radiation as a gentle glow left over from the universe's infancy, like the warm embers of a cosmic fire that burned 14 billion years ago. As scientists studied this ancient light, they noticed something peculiar. The temperature of this background radiation wasn't perfectly uniform. In one particular direction in space, it was slightly warmer, by less than 1/100th of a degree. This tiny temperature difference might seem insignificant, but it revealed something profound about our cosmic motion. When we move toward a source of light, that light appears slightly bluer and warmer due to a phenomenon called the Doppler effect. It's the same principle that makes an approaching ambulance siren sound higher in pitch. The warmer cosmic microwave background in one direction meant our entire local group of galaxies, including the Milky Way, was racing towards something at an extraordinary speed. The discovery presented a puzzle that would take decades to fully understand. Here was clear evidence of an enormous gravitational influence, yet when astronomers pointed their telescopes in that direction, they couldn't see what was causing it. The mystery deepened when they realized the scale of what they were dealing with. This wasn't just our galaxy being pulled along, but thousands of galaxies spanning incredible distances, all moving in a coordinated flow toward this enigmatic destination. By the 1980s, scientists had confirmed that our entire local group of galaxies was racing through space at extraordinary velocities toward an unseen gravitational source. This invisible force became known as the Great Attractor, named for its ability to gravitationally attract vast collections of galaxies across hundreds of millions of light years of space. The reason the Great Attractor remained invisible for so long lies in an unfortunate cosmic coincidence of perspective. Picture yourself trying to see through a thick forest. Even if something massive exists on the other side, the trees block your view completely. This is precisely what happens when we try to observe the Great Attractor from Earth. It lies directly behind what astronomers call the zone of avoidance, a region where our own Milky Way's disk, thick with dust and stars, obscures our view of the distant universe. The Great Attractor is obscured by the Milky Way's galactic plane, lying behind the zone of avoidance, so that in visible light wavelengths, the Great Attractor is difficult to observe directly. Imagine trying to study a distant mountain while standing in the middle of a dense fog. The dust and gas in our galaxy's disk absorb and scatter light from objects beyond, making direct optical observation nearly impossible. However, astronomers are resourceful. They began using different wavelengths of light that could penetrate the cosmic dust. Radio waves and infrared light became their tools of choice, able to pierce through the veil that visible light could not. Through these observations, they began to piece together the structure of what lay hidden. They discovered not just one massive object, but a complex region filled with galaxy clusters and vast amounts of dark matter. The observed attraction suggests a localized concentration of mass having the order of 10 to the 16th power solar masses. To put this in perspective, imagine the mass of 10 million billion suns concentrated in a relatively small region of space. This enormous concentration of matter creates a gravitational well so deep that it influences the motion of galaxies hundreds of millions of light years away. The gravitational pull from this region is so strong that it overcomes the natural expansion of the universe in our local cosmic neighborhood. The challenge of studying something you cannot directly see required astronomers to become cosmic detectives, using indirect evidence to map the invisible. They studied the motions of galaxies they could observe, tracking their velocities and directions to map the underlying gravitational field. Like following breadcrumbs through a dark forest, each galaxy's motion provided clues about the massive structure pulling them along their cosmic journey. Understanding how galaxies move through space requires us to think beyond the familiar motions we experience on Earth. In our cosmic neighborhood, galaxies aren't simply floating randomly through space. They flow like rivers, following invisible currents created by gravity. These cosmic streams carry galaxies along predictable paths toward regions of higher mass density, much like how water flows downhill toward valleys. In 1986, a group of astronomers observing the motions of the Milky Way and neighboring galaxies noted that the galaxies were moving toward the Hydra and Centaurus superclusters. This discovery marked a crucial step in understanding our cosmic motion. Astronomers found that our galaxy and its neighbors weren't just drifting aimlessly through space, but were part of a vast, organized flow of thousands of galaxies all heading in the same general direction. Picture a massive river system viewed from space, with countless tributaries flowing into larger streams, which eventually converge into a mighty river flowing toward the sea. This is essentially what happens with galaxies on cosmic scales. Small groups of galaxies merge into larger flows, which join even more massive streams, all eventually flowing toward regions of concentrated mass like the Great Attractor. The velocities involved are staggering. Our local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, moves through space at approximately 600 kilometers per second relative to the cosmic microwave background. To put this in perspective, at this speed, you could travel from Earth to the Moon in just 11 minutes. Yet despite these incredible velocities, the distances involved are so vast that this cosmic journey unfolds over hundreds of millions of years. Astronomers discovered that this motion isn't unique to our local region. Similar flows exist throughout the observable universe, with galaxies streaming toward various massive attractors. However, the Great Attractor stands out because of its proximity to us and its enormous influence on our cosmic neighborhood. By mapping these galactic flows, scientists began to understand the large-scale structure of the universe, revealing a cosmic web of matter connected by gravitational threads spanning billions of light years. As observational techniques improved, astronomers gradually began to peer through the cosmic dust and identify the actual structures responsible for the Great Attractor phenomenon. The breakthrough came when they focused on a region in the constellation Norma, where infrared and radio observations revealed something remarkable. Hidden behind the galactic dust was one of the most massive galaxy clusters in our cosmic vicinity. The Norma cluster is the closest massive galaxy cluster to the Milky Way and lies about 220 million light-years away. The enormous mass concentrated here and the consequent gravitational attraction mean that this region of space is known to astronomers as the Great Attractor. Imagine discovering a hidden metropolis behind a mountain range. The Norma cluster represents just such a cosmic city, packed with hundreds of large galaxies and surrounded by vast halos of dark matter. Galaxy clusters are among the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of individual galaxies, all held together by gravity and embedded in enormous reservoirs of dark matter. The space between galaxies in these clusters fills with hot gas, heated to millions of degrees by the intense gravitational environment. This gas glows brightly in high-energy wavelengths, providing another way for astronomers to study these massive structures despite the optical obscuration. The Norma cluster, however, represents just one component of the Great Attractor region. As observations became more sophisticated, astronomers realized that this area contains multiple galaxy clusters, groups, and vast filaments of dark matter, all contributing to the total gravitational influence. It's like discovering that what you thought was a single mountain is actually part of an entire mountain range, each peak contributing to the overall topography of the region. The gravitational field created by this concentration of matter extends far beyond the visible clusters themselves. Dark matter, which makes up approximately 85% of all matter in the universe, forms invisible scaffolding that amplifies the gravitational effects. This dark matter doesn't interact with light, making it invisible to our telescopes, but its gravitational influence shapes the large-scale structure of the universe and guides the motion of galaxies across vast distances. The story of the Great Attractor took a remarkable turn in 2014 when astronomers made a discovery that revolutionized our understanding of our place in the universe. Using sophisticated mapping techniques that trace the flow of galaxies across hundreds of millions of light years, they discovered that our Milky Way galaxy belongs to an enormous structure called the Laniakea supercluster. The Laniakea supercluster encompasses approximately 100,000 galaxies stretched out over 520 million light years. To comprehend this scale, imagine trying to visualize a structure so vast that light itself takes over 500 million years to cross it. Within this cosmic metropolis, it has the approximate mass of 10 to the 17th power solar masses, or 100,000 times that of our galaxy. The name comes from Hawaiian, meaning immense heaven, a fitting description for this cosmic structure that serves as our galactic neighborhood. This study also clarifies the role of the Great Attractor, a gravitational focal point in intergalactic space that influences the motion of galaxies within the supercluster. Rather than being a mysterious external force pulling us toward an unknown destination, the Great Attractor represents the gravitational center of our own cosmic home. Think of the supercluster as a vast cosmic watershed. Just as rivers flow toward the ocean following the topography of the land, galaxies within the supercluster flow along gravitational currents toward its center of mass. The Great Attractor region represents the lowest point in this gravitational landscape, the cosmic equivalent of a valley where all the streams converge. This discovery fundamentally changed our cosmic perspective. Instead of being pulled towards some distant, alien structure, we're actually part of a vast gravitational family. The galaxies around us, including our Milky Way, are all siblings in this enormous cosmic structure, connected by invisible threads of gravity that have guided our dance through space for billions of years. Our motion toward the Great Attractor isn't a journey to a foreign destination, but rather a homecoming to the heart of our own cosmic neighborhood. The cosmic journey toward the Great Attractor unfolds on timescales that dwarf human imagination. To understand this motion, we must think in terms of cosmic time, where millions of years pass like moments and the stately dance of galaxies plays out over billions of years. Our local group's motion toward the Great Attractor began shortly after the formation of large-scale structure in the universe, when gravity started pulling matter together into the cosmic web we observe today. At our current velocity of over 1 million miles per hour, you might expect this cosmic journey to end relatively quickly. However, the distances involved are so staggering that this apparent speed becomes almost imperceptible on cosmic scales. The Great Attractor lies approximately 250 million light-years away, meaning that at our current rate of approach, we wouldn't reach it for many billions of years. To put this in perspective, this journey will take longer than the entire history of life on Earth. But the universe doesn't remain static during this long voyage. The expansion of space itself works against gravitational attraction, stretching the fabric of space-time and increasing distances between distant objects. This cosmic expansion, driven by dark energy, acts like a cosmic headwind that slows our approach to the Great Attractor. In regions where gravity is strong enough, like within galaxy clusters and superclusters, this expansion can be overcome, allowing structures to grow and merge. As we journey through space, we're also part of other cosmic motions. Our solar system orbits the center of the Milky Way every 230 million years, while the Milky Way itself rotates and slowly approaches the Andromeda Galaxy. These multiple motions combine to create a complex trajectory through space, like a cosmic ballet where multiple dancers move in intricate patterns simultaneously. The ultimate fate of this journey depends on the balance between gravitational attraction and cosmic expansion. Current models suggest that while we'll continue moving toward the Great Attractor for billions of years, the accelerating expansion of the universe will eventually halt and reverse this motion. In the distant future, the components of the supercluster may begin to drift apart as cosmic expansion overwhelms even the strongest gravitational bonds, leaving each galaxy to face an increasingly lonely universe. The Great Attractor phenomenon has become one of our most important windows into understanding dark matter, the mysterious substance that makes up approximately 85% of all matter in the universe. While we cannot see dark matter directly, its gravitational effects are written across the cosmic landscape in the form of galactic motions and large-scale structure. The Great Attractor region serves as a natural laboratory for studying how this invisible matter shapes the evolution of the universe. Think of dark matter as the invisible scaffolding of the cosmos. Just as a building's framework determines its shape and stability even though we cannot see it through the walls, dark matter provides the gravitational skeleton that holds together massive structures like galaxy clusters and superclusters. In the Great Attractor region, computer simulations suggest that vast halos of dark matter, each containing trillions of times the mass of our Sun, create the gravitational wells that trap and concentrate normal matter into the galaxies we observe. The distribution of dark matter in the Great Attractor region follows a complex three-dimensional web of filaments and nodes. These cosmic highways of dark matter stretch across hundreds of millions of light years, connecting galaxy clusters and guiding the flow of normal matter along their gravitational currents. Where these filaments intersect, we find the most massive galaxy clusters, like beads on an invisible cosmic string. Recent studies using gravitational lensing have begun to map this dark matter distribution directly. When light from distant galaxies passes through regions of concentrated dark matter, the gravitational field bends and distorts the light, creating subtle changes in the appearance of background galaxies. By carefully analyzing these distortions, astronomers can create maps of dark matter density, revealing the hidden architecture that drives the Great Attractor phenomenon. The Great Attractor also helps us understand how dark matter and normal matter interact during the formation of cosmic structure. While dark matter can only interact through gravity, normal matter can radiate energy and cool, allowing it to collapse more efficiently into dense structures. This difference means that dark matter forms the large-scale framework first, and normal matter subsequently flows along these gravitational channels to form the galaxies and clusters we observe. Understanding the dark matter connection has implications far beyond the Great Attractor itself. The same physical processes that created this massive structure operate throughout the universe, shaping the cosmic web on the largest scales. By studying how dark matter concentrates in regions like the Great Attractor, astronomers gain insights into the fundamental nature of this mysterious substance and its role in cosmic evolution. discovery and study of the Great Attractor has profound implications for our understanding of the universe's structure and evolution. This cosmic phenomenon reveals that the universe is far more organized and interconnected than early astronomers could have imagined. Rather than galaxies moving randomly through space, we see evidence of vast, coherent flows that trace the underlying gravitational architecture of the cosmos. The Great Attractor, rather than anything to be afraid of, is where our local galaxies are heading to hang out, the central gravitational point of our local area of the universe. This perspective transforms our understanding of cosmic motion from something alien and threatening to something familiar and comforting. We're not being pulled toward an unknown fate, but rather flowing along the natural currents of our cosmic neighborhood. The study of the Great Attractor has also advanced our understanding of dark matter and its role in shaping cosmic structure. The gravitational effects we observe require far more mass than we can account for with visible matter alone. This invisible dark matter provides the gravitational scaffolding that holds together massive structures like Laniakea and creates the flows that guide galactic motion. Understanding these dark matter distributions helps astronomers map the invisible architecture of the universe. Furthermore, the Great Attractor phenomenon demonstrates how local gravitational effects can overcome cosmic expansion on certain scales. While the universe as a whole continues to expand, regions of sufficient mass density can resist this expansion and even contract under their own gravity. This balance between expansion and contraction shapes the evolution of cosmic structure and determines the fate of different regions of the universe. From a philosophical perspective, the Great Attractor reminds us of our deep connection to the cosmos. We often think of Earth, our solar system, or even our galaxy as isolated islands in space. However, the reality is that we're part of vast cosmic currents that connect us to structures spanning hundreds of millions of light years. Our motion through space isn't random or purposeless, but follows ancient gravitational pathways that have been shaping cosmic structure since the universe was young. And on that note, we conclude our journey through the mystery of the Great Attractor. We've discovered that what initially appeared as an invisible cosmic force pulling our galaxy toward an unknown destination is actually the gravitational heart of our own cosmic home, the supercluster that contains us. This enormous structure, spanning over 500 million light years and containing 100,000 galaxies, represents our address in the vast cosmic web. The Great Attractor teaches us that the universe is far more interconnected and organized than we might have imagined. We're not isolated wanderers in an empty void, but participants in a grand cosmic dance that has been choreographed by gravity over billions of years. Our Milky Way, along with thousands of neighboring galaxies, follows ancient gravitational currents toward the center of our cosmic neighborhood, a journey that will continue for billions of years to come. This cosmic phenomenon also highlights the remarkable detective work of astronomers who pieced together this story despite the challenge of studying something hidden behind our own galaxy's dust. Through ingenuity, persistence, and the use of multiple wavelengths of light, they revealed one of the most significant structures in our local universe and helped us understand our place within it. And so, our journey through the cosmos comes to a gentle close. We've traveled billions of light years together, from stellar nurseries where stars take their first breath, to the edge of everything our universe allows us to see. We've drifted alongside rogue planets in the darkness, listened to the songs of neutron stars, and followed the invisible currents of the cosmic web that connects all things. You've witnessed how your atoms have journeyed through stellar generations, how time itself bends and flows, and how our little galaxy drifts toward mysteries we're only beginning to understand. Through it all, I hope you felt what I feel when I look up at the night sky, a profound sense of belonging, of being part of something vast and beautiful and endlessly curious. The universe will still be here tomorrow, full of wonders waiting to be explored. But for now, rest easy knowing you are made of the same substance as stars, that you carry the cosmos within you, and that in the grand sweep of cosmic time, this moment of peace you found is just as remarkable as any supernova.